Welcome to week 1. This week has 2 lessons. In the first lesson, you will learn how to calculate probability for different types of random events using rules of probability and Bayes' theorem. And in lesson 2, I will introduce you to the concept of a probability distribution and some examples of commonly used probability distributions. But what exactly is a probability? This is what we're going to be looking at in this video. Simply put, probability is the measure of how likely an event is to occur. So for example, if I throw a fair coin, the probability that it lands in heads is 50% or 1/2. And if I throw a dice, the probability of it landing in the number 4 is 1/6. Want to know more? Let's get started. So to get us started, we're going to explore an intriguing problem that will test your probability skills. Imagine you're in a school with 10 kids and you want to randomly pick a kid from the population. In this school, 3 kids play soccer and 7 don't. The question is, what is the probability that the kid you picked at random plays soccer? So are you ready to find out the answer? Let's dive into the world of probability and learn how to solve this problem together. Recall that you want to find the probability that a child picked at random plays soccer. In math, we have a way to denote this statement. We will use P of soccer to denote the probability that a kid plays soccer. To find the probability that a child plays soccer denoted by P soccer, first we need to know the number of kids who play soccer and the total number of children in the school. We will express this in the probability formula, number of kids who play soccer divided by the total number of kids. So the probability of a random kid playing soccer is 3/10 or 30%. Can be also written as 0.3. The numerator is represented by the event, the outcomes favorable to the experiment, which in this case is the kids who play soccer. So the number of kids who play soccer is 3. That's the size of the event. The denominator corresponds to the sample space, the total possible outcomes, and the number of those is 10. That's the size of the sample space. And there you have it. We successfully solved the problem using the basic principles of probability. By understanding this simple problem, you will be able to apply these concepts in more complex real-world situations in machine learning and data science. Now, using the concepts of Venn diagrams, the total population, all the children are represented here by the green rectangle. This will be 100% of the population. The green rectangle, including the kids who play soccer and those who don't, is the sample space. 30% of the kids who play soccer will be in this circle. This is the event, the group of items you're interested in. And the kids who do not like soccer will be outside the circle, but still in the green rectangle because they're still part of the population. So we can calculate the probability by dividing the number of favorable outcomes by the total number of possible outcomes. In our next example, we're going to be flipping a coin. And when we do that, the coin can land in heads or tails. Because this activity of flipping a coin producing an outcome that is uncertain, we're going to call this the experiment. In probability, an experiment is any process that produces an outcome that is uncertain. Thus, in our content, throwing a coin is an experiment, and we'll determine the probability of the coin landing in heads denoted by P of heads. We're going to be flipping a fair coin, meaning that each outcome, heads or tails, is equally likely to occur. So both of them occur with 50% probability. P of heads is equal to the event of landing in heads divided by the total number of outcomes, and that's 1/2 or 0.5. Now let's make the problem a bit more complex and throw 2 coins. What will be the probability of both of them landing heads? To answer this question, let's walk through the experiment to determine the total number of outcomes. The first coin can land in heads or tails. Now for each outcome of the first coin, the second one can land in heads or tails. So our final outcomes are heads, 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 tails, tails, heads, and tails, tails. Those are 4 outcomes. Now, with these outcomes, what is the probability of both coins landing in heads? That is the upcoming quiz. Out of these 4 possible outcomes, we're interested in the one where both coins land in heads. So there's only one such outcome, which is heads, heads. So the probability of both coins landing in heads, denoted as P of HH, is the number of favorable outcomes, which is 1, divided by the total number of outcomes, which is 4. So that's 1/4 or 0.25, also called 25%. That's the probability of both coins landing in heads. Now what if we flip 3 coins? Well, let's calculate the probability of the 3 of them landing in heads when you throw 3 coins. We can throw the first coin and it can land in heads or tails. Now the second coin, for each outcome of the first coin, can land in heads or tails. And the third coin, for each outcome of the first and second coins, can land in heads or tails. So how many total outcomes we have? We have 8 of them. All heads, 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 tails, heads, tails, heads, heads, tails, 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 heads, heads, tails, heads, tails, 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 heads, and tails, tails, tails. That is 8 outcomes. And now the question for you is, what's the probability of landing on heads 3 times? Well, out of these 8 possible outcomes, we're interested in the one where the 3 of them land in heads. That is 1 divided by the total number of outcomes, which is 8. And therefore the answer is 1/8 or 0.125. Now let's reinforce the concept of probability, but this time around we're going to use the experiment of rolling a fair 6-sided dice. Here's a question for you. What is the probability that if you roll this dice you obtain a 6? Well, given the fact that 6 things could happen and all of them are equally likely, that's the sample space, and one of these outcomes is favorable, so that's the event, then the probability P of 6 is 1 divided by 6, or 1/6. Now, what if we roll 2 dice? What is the probability of obtaining 6/6? That's the next quiz for you. Well, let's look at the entire sample space. For each roll of the first die, we can have 6 possibilities for the second die, and we get 36 in total. 1, 1, 1, 2, 1, 3, etc., all the way to 6, 6. That's the sample space of size 36. And the event is just this one over here. That's the only favorable outcome. So the probability of 6, 6 is 1 divided by 36. That's the answer. Next up is an interactive tool that will reinforce some of the ideas you've been learning about probability. You can flip a coin or roll a dice repeatedly to see how the frequency of each outcome approaches the theoretical probability with more flips or rolls. Give it a shot, and once you're ready, move on to the following video. So in the last video, you learned about how to calculate the probability of the occurrence of an event. So in this video, we're going to talk about the complement of an event and its probability. So this is the probability that the event does not occur. For example, if an event has a probability of occurring of 75%, then the complement event, or the probability that the event does not occur, is 25%. Let me elaborate. So let's go back to our school with 10 kids, where 3 of them play soccer and 7 don't. Here's a question for you. What is the probability that a child does not play soccer if they are picked at random? Well, to find the probability that a child does not play soccer, that's denoted as P of not soccer, then we do the same thing as before. We count the number of kids who don't play soccer and divide it by the total number. And that's going to be 7 divided by 10. That is the answer, 0.7. However, you may have noticed that that is related to the probability that the kid plays soccer, because the probability of not soccer is 0.7 and the probability of soccer was 0.3, and they add to 1. Turns out this always happens, and we can rewrite this as 1 minus 0.3. This is essentially the complement rule. The complement rule states that the probability of an event A not occurring is equal to 1 minus the probability of A occurring. So the probability of not soccer is 1 minus the probability of soccer. That's going to be the complement rule. And we can formalize this rule as follows. P of A prime is 1 minus P of A, where A prime represents the complement of the event A. That's when the event A does not happen. So using this formula, we can calculate the probability of an event not happening in a more straightforward manner. Now, as a Venn diagram, you can see this in a similar way as before. Here you have the sample space. Here you have the event of playing soccer inside the circle. And the event of not playing soccer is everywhere outside that circle, which is 70% if the circle is 30. Now, using the experiment of flipping 3 coins, here's a question for you. What's the probability of not obtaining 3 heads? Well, by the complement rule, the probability that none of the coins land in heads, that's P of not 3 heads, is equal to 1 minus the probability of 3 heads. And as you saw in a previous video, this probability is 1/8. So we have 1 minus 1/8, and that is simply 7/8. You can also see it as the 7 good cases, which are all minus the 3 heads, divided by the 8, which is the total number of cases. Now let's apply the complement rule to the dice experiment. If you throw 1 die, what is the probability of obtaining anything different than 6? Well, we know there are 6 outcomes, and the probability of not 6 is equal to 1. This 1 is 6/6, minus 1/6, the probability of landing in a 6. So the 6 is over here. Here we remove one of them, which is landing in a 6, and the answer is 5/6. So in this video, you're going to learn about the sum of probabilities, which is quite simple. Consider the roll of a die. If you know the probability of getting a 2 and the probability of getting a 3, and you want to know the probability of getting a 2 or a 3, then all you do is you add these probabilities. However, there's a caveat. This doesn't work all the time. We need to know if the events are disjoint. Let me explain. So let's go back to the school, but now we have more information. We have a school where kids can only play one sport. This is going to be important. And the sport can be soccer or basketball. The probability that a kid plays soccer is 0.3. The probability that a kid plays basketball is 0.4. So here's a question. What do you think is the probability that a kid plays soccer or basketball? And remember, at this school, kids can only play one sport, not 2 or more. If you want a hint, imagine that there's only 10 kids in this school and do your calculations like that. So let's remember that the kids can only play one sport. So let's say there's 10 kids, and if there's 10 kids, then 30% play soccer, that's 3 of them, and 40% play basketball, that's 4 of them, and that makes 70% of the kids. So the probability that a kid plays soccer or basketball is the number of kids who play soccer or basketball divided by the total number of kids. That is 3 plus 4 divided by 10, or 0.7. Notice that we added the probabilities. The probability of soccer was 0.3, probability of basketball was 0.4, and the probability of soccer or basketball was 0.7, which is 0.3 plus 0.4. Now this can be seen in the Venn diagram as follows. We're going to use the letter U for union, and if all the children are here and 30 of them play soccer, that's over here, and 40 of them play basketball, then the union is the ones that play soccer or basketball. So it's the ones that play soccer and the ones that play basketball. So it's written like this, A union B, and the probability of A union B is the sum of the probabilities P of A and P of B. Now let's see how the concept of sum of probabilities reflect in a dice example. Let's say that you roll a fair 6-sided dice once. What is the probability of obtaining an even number or a 5? So there are 2 events here. Event A is rolling an even number, that's 3 of them, and event B is rolling a 5, so that's 1 of them here. And because the probabilities get added, then we have 3/6 plus 1/6, and so the probability of even number or 5 is probability of even number plus the probability of 5, 3/6 plus 1/6, and that is 4/6, which in lowest terms is 2/3. Now here's another question. If I roll 2 dice, then what's the probability of obtaining a sum of 7 or a sum of 10? Well, let's consider 2 events. The event A is that you get a sum of 7, and the event B is that you get a sum of 10. So out of the 36 possibilities, how many have a sum of 7? Well, there's this 6 over here. And out of the same 36 possibilities, how many have a sum of 10? There's this 3 over here, 6, 4, 5, 5, and 4, 6. So when you look at the union, so a sum of 7 or a sum of 10, then we are looking at all these events that are colored red or yellow. So sum of 7, that is 6/36, and the sum of 10 is 3/36. When we add them, we obtain 9/36, which in lowest terms is 1/4. So this one over here is a probability that the sum is 7. This one over here is a probability that the sum is 10, and we just added them. Now let's see yet another example. What's the probability of obtaining a difference of 2 or a difference of 1? Well, again, we have the two events. A is the event that difference is 2, and B is the event that the difference is 1. Which pairs have a difference of 2? These pairs over here. 1, 3, 2, 4, 3, 5, 4, 6, 3, 1, 4, 2, 5, 3, and 6, 4, because the difference can be in any direction. It can be the first minus the second, or the second minus the first. And similarly, for the difference of 1, we have all these pairs over here. And now, when we look at the union, they are over here. It's this many. So the probability that the difference is 2 or the difference is 1 is equal to the sum of the two. So this one over here plus this one over here. The first one, there's 8 cases out of 36, so it's 8 over 36. The second one is 10 cases out of 36, so it's 10 over 36. And when you add them, we get 18 over 36. That first one is the probability that the difference is 2. The second one is that the difference is 1. And as you can see, 18 over 36 in lowest terms is 1/2, so it's actually 50%. Welcome back. In our previous lessons, we talked about the sum of probabilities for disjoint events. But what happens when the events are not disjoint? Well, a problem may happen. Let me give you an example. Let's say that the probability of rain is 80% and the probability of being windy is 70%. So what's the probability of rain or wind? Well, if you add them, you get 80% plus 70%, and that's 150%. That is way too much, and it's completely wrong, because the events are not disjoint. See, you could have rain and wind at the same time, and that's the key. In real-world situations, events are not often disjoint, and we need to account for this possibility of overlapping outcomes. The sum rule for joint events allows us to do this and to calculate the probability of combined events. So get ready to dive deeper into the world of probability and learn how to use the sum rule for joint events. So we're back to the school from the previous example, except in this one, kids can play as many sports as they want. They don't have that restriction that they can only play one sport. And the options are still soccer and basketball. Here's a question for you. If the probability of a kid playing soccer is 0.6 and the probability of a kid playing basketball is 0.5, what's the probability that a kid plays soccer or basketball? And again, if you need a hint, imagine that there's only 10 kids in the school and do the math like that. So let's see, this one's a bit more complicated. Here are the 10 kids, and 60% that play soccer are, for example, this 6, and the 50% that play basketball are, for example, this 5. But these could change. There could be an overlap. And when that happens, then we don't really know how many children play multiple sports. So let's look at it in a Venn diagram. Here's 100% of the kids, and here's the 60% that play soccer, and here is the 50% that plays basketball. So originally we had this equation, P of S union B is P of S plus P of B, but that doesn't work. As a matter of fact, even if you try to add them, you would get 110%, which is more than the number of kids in the school. So there's something we're overcounting. And what we're overcounting is this intersection here. That is this one kid who plays both sports. That is P of S intersection B. The intersection of two events is when both of them happen at the same time. So the kids who play soccer and basketball. And it could be 1, but it could also be a different number. It could be 3, for example. And so what we need is we need the information of how many kids play both soccer and basketball in order to solve this problem. So here's the information. Same school, and the kids can play soccer or basketball. And now let's actually do it with numbers. 6 kids play soccer. 5 kids play basketball. And 3 kids play both sports. So the question for you is, how many kids play soccer or basketball? So it could be soccer or basketball or both. Well, let's break the problem down. 6 of them play soccer, 5 of them play basketball, and that's all the kids over here. Now we know that 3 play both, so that's 8. Because these 2 over here don't play soccer or basketball. In the Venn diagram, it's like this. Here's 100% of the kids. Here's the ones that play soccer. Here's the ones that play basketball. And the ones that play both are in this intersection here. That's the ones that play soccer and basketball. And we have the following formula. the size of the set S of kids that play soccer union the set B of kids that play basketball is the size of the set S, that is this 6 over here, plus the size of the set B, which is this 5 over here, but we've overcounted. Notice that those 3 kids that play both sports were counted twice, so we need to subtract them. We need to subtract these 3 over here, and now we have a count of how many kids play soccer or basketball. That's 6 plus 5 minus 3, and that's going to be 8. This is also known as the inclusion-exclusion principle. And now we can represent the same thing except with probabilities. Again, the same problem with soccer and basketball, but now we're not going to say that 6 kids play out of 10. We're going to say that the probability of a kid playing soccer is 0.6, and the probability of a kid playing basketball is 0.5, and the probability that a kid plays both is 0.3. So given this information, so what is the probability that a child plays soccer or basketball? And just like before, we can do a Venn diagram. We can look at the ones that play soccer and the ones that play basketball, and the probabilities follow the same inclusion-exclusion rule as before. We have P of S union B is P of S plus P of B, but we're overcounting the intersection, so we're overcounting P of S intersection B, so we have to subtract it because we're counting it twice. And that's 0.6 plus 0.5 minus 0.3, which is 0.8. So illustrating our 2 examples visually, in the problem in the left, the kid can only play one sport, so the events are disjoint. It's much easier to calculate probabilities here because all we have to do is add them. They don't overlap. In the case over here, they overlap, so in order to calculate the probability of the union of the events, we need to take the intersection into account. So the case in the left is called disjoint events or mutually exclusive, and for this case, the probability of the union is the sum of the probabilities. And for the case in the right, this one is called joint and also called non-mutually exclusive, and for this we have to follow the formula P of S union B is P of S plus P of B minus P of S intersection B. Notice that the case in the left follows from the case in the right because S intersection B is just the empty set, so the probability is 0. But to be more precise, we can look at both cases. Now let's see this for a pair of dice. Question is, what is the probability of obtaining a sum of 7 or a difference of 1? Well, let's take a look. The sum of 7 is all these cases over here, as you've already seen. And the difference of 1 is all these cases over here. Now, before we used to just add them, but this time is a little more difficult. So we're going to call the one on the left A and the one on the right B, and we're going to say that A or B is these ones over here, except that we have double counted these two. The sum equals 7 and the difference is 1 are double counted. So in order to not double count them, we have to subtract that probability. So the probability of sum equals 7 or difference is 1 is this 6 over 36 for the sum is 7 plus this 10 over 36 where the difference is 1 minus what we're overcounting, because 4, 3, and 3, 4 are counted twice, so we have to subtract 2 divided by 36. So we get 6 over 36 plus 10 over 36 minus 2 over 36, and that's 14 over 36, and that's P of sum equals 7 plus P of difference equals 1 minus P of sum equals 7 and difference equals 1. So 14 over 36, which in lowest terms is 7 over 18. In this video, we're going to look at the concept of independence. Independence happens when the occurrence of one event does not affect the probability of the occurrence of another event. For example, if I toss a coin twice, whatever happened on the first throw does not affect the outcome of the second one. On the other hand, if I'm playing chess, whatever happened on the 10th move affects what happens on the 11th move. So these are not independent, but the coin throws are independent. Understanding independence is very important in probability and in machine learning, because assuming that things are independent actually helps us simplify calculations and make predictions. So let's calculate one more probability. In a school, there are 100 kids. Half of them, so 50 of them, like playing soccer, and the other half do not like playing soccer. The kids are randomly split into 2 equal rooms, each one of them of size 50. That's room 1 and room 2. So for this question, you're not required to make any calculations. The question is, based on your knowledge, what is your best estimate about the number of kids in room 1 who would like soccer? And remember, the kids were randomly split into 2 equally sized rooms. So the split will most likely look as follows. Roughly 25 kids in the first room will like soccer and roughly 25 in the second room because they were randomly split. There was no reason to go to room 1 versus room 2. And so that is 25 each. Obviously something different would have happened, but our best estimate is 25 because if roughly half of the kids play soccer and they're split into 2 rooms half-half, then roughly half of the kids in each one of the rooms play soccer. Now imagine another school with 100 kids, but in this school only 40 of them like playing soccer, which means 60 of them don't like playing soccer. The kids are randomly split into 2 sides, this time of different size. Room 1 can fit 30 kids and room 2, 70 kids. So same question as before. Based on your knowledge, what is your best estimate about how many kids in room 1, the smaller room, like to play soccer? Or at least what would you expect this number to be? Well, since the split is 40-60 for soccer and not soccer, we expect that since we separated the kids randomly, then in each of the rooms the split's going to be 40-60 again. So we expect 40% of the kids in room 1 to like soccer, and that's exactly 12 kids because 40% of 30 is 12. More clearly, we have 40% of 100 kids playing soccer. That is 40 kids, and the probability of a kid playing soccer is 0.4. And then there's 60 kids who don't play soccer, so the probability of a kid not playing soccer is 60% or 0.6. Now we can split them into 2 rooms. There's 30% of the kids in room 1, so the probability of room 1 is 0.3. And the question is, what is the probability that a kid plays soccer and is in room 1? So we have P of soccer, which is 0.4, and P of R1, room 1, which is 0.3. And we're looking for this probability over here. So probability of soccer intersection room 1. And as you can see, that's the probability of soccer times the probability of room 1, which is over here. That's 0.4 times 0.3. In other words, remember that we took 40% of 30%. That means we're multiplying them and we get 12% or 0.12. What we're talking here is the intersection of 2 events. When you see the word and, that's intersection. So the probability that a kid plays soccer and is in room 1 is, because those events are not related, are independent of each other, then it's the product of the 2 probabilities, P of S and P of R1. So we get to the product rule. The product rule simply says probability of A intersection B is probability of A times the probability of B. This is going to be very useful, but remember, the events have to be independent, and we're going to see more details about this later. To continue illustrating the intersection of independent events and the probability of that, we're going to look at a coin example again. So let's consider tossing a fair coin 5 times. Here's a question for you. What is the probability that the coin lands in heads all 5 times? Well, note that each event is independent from all the other ones because one coin landing in heads does not affect any of the other ones. Therefore, the probability is the probability that the first one lands in heads, which we know it's 1/2 times the same thing for all the other ones. So it's 1/2 times 1/2 times 1/2 times 1/2 times 1/2, and that is going to be 1/32 because it's 1/2 to the 5, and that is 1/32. So this product rule can be extended. It's not just 2 events, but if you have many independent events, all independent from each other, then the probability that they all happen is the probability of all of them happening separately. So now let's look at some dice. Recall that when a dice is rolled, the probability of obtaining a 6 is 1/6. So now when 2 dice are rolled, what's the probability of obtaining 6/6? Well, we've calculated this before, but we can actually do it with the product rule. This was 1/36 because we have 1 here and 36 cases. However, if we look at both events separately, they're independent events because one rolling of the dice does not affect the other one. And what's the probability that the first one lands in 6? Well, it's 1/6. And for the second one, it's again 1/6. So we multiply them and we get 1/6 squared, which is 1/36. Now, what is the probability that if I roll 10 different dice, all of them fair, I get 10 sixes? Well, as you can imagine, the probability is the probability of getting 1/6 to the power of 10 because all these rolls are independent. That's 1/6 to 10, which is a very, very, very small number. So as you've learned in this video, the probability rule says that if you have independent events, the calculation of the probability of all of them happening at the same time is easy. It's just the product of all of them. Great work so far. In this lesson, we're going to talk about one of the most fascinating problems in probability, the birthday problem. So let's say you are with 3 random people and you're wondering what's the probability that 2 of you have the same birthday. It's probably very low. Now, what if you were with 200 random people? You would say it's very likely that some 2 of them have the same birthday. What about 30 people? What about 50 people? 100 people? Well, let me show you what happens and the results may surprise you. So here's the problem. You have 30 friends at a party. Among those 30 friends, excluding yourself, among those 30 friends, what do you think is more likely? That there exist 2 people who have the same birthday, or that no 2 of them have the same birthday? And let's assume that this year only has 365 days, so there's not going to be any February 29 birthdays, just for the sake of this problem. So the answer, believe it or not, is that it's more likely that 2 people have the same birthday. And in fact, the probability of no 2 people having the same birthday is only around 0.3. So let me show you the math. And that's non-intuitive, right? Because if you think of 30 people, it doesn't look that likely that 2 of them have the same birthday, but there's a 70% probability that 2 of them have the same birthday. So let's see why. Since it's way easier, we're going to focus on the probability that no 2 people have the same birthday. Remember that the probability that at least 2 people share the same birthday can be obtained by taking the complement. So here is the entire year. Let's imagine that there's 365 boxes here, even though there's less, but let's pretend there are. And let's look at the first friend. So we're going to keep track of the probability that among the group that we're looking at, everybody has a different birthday. So if it's one person, obviously they will not have the same birthday as anyone else because the group only has one person. So the probability is 365 over 365, that's a 1. Let me repeat that last thing I said. So the probability is 365 divided by 365, which is 1. In other words, this person can have a birthday any day of the year and it's not going to overlap with anyone else. Now let's add a second person. What is the probability that the 2 of them have a different birthday? So what's the probability that among these 2 there's no repeated birthdays? Well, the other one has to have pretty much a birthday on any day that's not the same day of the first one. So we multiply by 364 divided by 365. So it's still pretty high because it's unlikely that if you take 2 people, they will have the same birthday. Now let's add one more person. And we want that person not to have a birthday at the same time as any of the other 2. So they can have a birthday in any of the remaining 363 days out of 365. And so the probability that these 3 have all different birthdays, now it's 365 times 364 times 363 divided by 365 cubed, because every time we have a new event and we multiply by this probability. If we add a 4th person, well, now they can have a birthday in any of the days that are not taken. That's 362 divided by 365. And if we add a new person, they again can have a birthday in any of the days that are not taken. So we multiply by 361 over 365, and if we add one more person, then we multiply by 360 over 365, and one more, we multiply by 359, and so on and so forth. So if we have this group of 9 people, then what is the probability that they all have birthdays on different days? It's the product of all these numbers, and that's actually 0.905. In other words, if I have a group of 9 people, the probability that there's no overlapping birthdays is roughly 90%. So it's very high because among 9 people, most likely there are no repeated birthdays. But now let's actually do the plot for this probability with more people. So as we saw, among a group of one person, the probability that no repeated vertex is 1. For 2 people, remember that it was 364 divided by 365, that's 0.997. And we kept multiplying this by other factors, right? 363 over 365, etc., etc. So when we keep track of this product, then as you can see, the number starts decreasing. For 20 people, it's already 0.589. For 23 people, it's 0.493. So for 23 people, it's already more likely to have a birthday in common than no birthdays in common. For 30 people, it's 0.294. And for 50 people, it's already 0.03. So among 50 people, it's very, very likely that 2 of them have the same birthday. And for 100 people, it's already very, very, very small. And for 366 people already, it's 0, because by then you have to have 1 repetition. And the plot is on the right, where in the horizontal axis we have the number of people, and in the vertical axis the probability. Notice how quickly it drops. And it stops being bigger than 0.5 around here, which is exactly at 23 people. So if you are ever in a party with 23 people, you can bet that there's a repeated birthday and you would win more than half of the time. So as you see, this was quite non-intuitive. However, we calculated the probabilities and that's what we got. Welcome back. You've seen a lot of fascinating concepts of probability so far. In this lesson, we will take a look at the concept of conditional probability. Conditional probability is all about calculating the probability of an event happening, given that another event has already happened. For example, let's say you are wondering about the probability that today is humid. That is some number. However, if you found out that yesterday was raining, the probability that today is humid changes. That is a conditional probability. So in a previous lesson, we established the probability of obtaining 2 heads when you throw 2 coins as follows. Let me recap very quickly. The first head can be heads or tails, and for each option of these 2, the second one can be heads or tails. So we have 4 possibilities: heads, heads, head, tails, tail, heads, and tails, tails. And the probability of heads, heads, well, the sample space was of size 4 and the event was of size 1, so it was 1 over 4. Now let me ask you a question. What is the probability that both coins land on heads if you know that the first one landed in heads? So now you have more information. I came and told you that the first coin landed in heads. Now, what is the probability that both of them landed in heads? Well, if the first one landed in heads, then we live here. This is the new sample space. The bottom part doesn't count anymore because the first coin landed in heads, not tails. So now the denominator is not 4, but it's 2, because now there's 2 cases instead of 4. And we still have 1 favorable outcome. So the new answer is 1 over 2. This over here is called a conditional probability, and we denote it with a vertical bar. So the probability of heads, heads, given that the first is heads. That given that is denoted by a vertical bar, and this is a conditional probability. This can be seen in a table as follows. If the first coin is on the left and the second coin is on top, then these are the 4 possibilities: heads, heads, head, tails, tail, heads, and tails, tails. And we're going to look at the probability of landing on heads twice, given that the first one is heads. So we live in this first row, and when we live in the first row, our sample space now has size 2 and our event has size 1. Therefore, the probability is not 1/4 anymore, it's now 1/2. Now, let me ask you another question. What is the probability of landing in heads twice, given that the first coin landed in tails? So slightly different question, give it a try. Well, if the first coin landed in tails, now we live here. This is our sample space and the top is not valid anymore. So the denominator is now 2, but the numerator is 0 because now there's no heads, heads. So the answer is 0 over 2, which is 0. And this makes sense, right? Because if one of them landed in tails, there's no way that they're both going to land in heads. So this condition really changed the probability from 1/4 all the way to 0. And again, we can see it as a table where we have the 4 cases, and we want to calculate the probability of landing in heads twice, given that the first one's tails, means we live in the second row, not in the first one. And the probability here is now, well, on the bottom we have a sample space of size 2, but on the top we have nothing because there's no heads in this sample space, and therefore the number is 0. So as you can see, a condition can change the probability of an event, and this is what we study with conditional probability. So let's recall the product rule for independent events. It said that the probability of A intersection B is P of A times P of B, but this only happened when A and B were independent. That doesn't always happen. Let me give you an example of something where the events are not independent. Let me ask you a question. What is the probability if I roll 2 dice that the first one lands on 6 and that the sum is 10? Well, we have a space of 36 possibilities because it's pairs of numbers, and the only favorable one is 6, 4, because if the first one is 6 and the sum is 10, the second one has to be 4. So the probability is 1 divided by 36 total ones, and that's 1 over 36. Now, let's look at it in a slightly different way. Let's try to apply the product rule. So we want the probability that the first one is 6 and that the sum is 10. And we would like to have the probability of the first one is 6. Well, that is over here. So that is 6 divided by 36. Now, what do I have to multiply this to obtain the probability that the first is 6 and the sum is 10? Well, I need the probability that the sum is 10, but among the ones for which the first is 6. So that is this event over here, the 6, 4, divided by the 6 where the first one is 6, and that is 1 over 36, which is what we obtained here previously. So to summarize, we have that the probability of A intersection B, that's that the first is 6 and that the sum is 10, is the probability of the first one, that the first is 6, times the probability of the second one given the first one. We need that given the first one, because we need to multiply by the probability of the sum is 10 given that the first is 6. So we get a slightly different formula. Probability of A intersection B is the probability of A times the probability of B given A. Now, when they're independent, then probability of B given A is the same as probability of B, because A doesn't make any difference on the occurrence of B. So when they're independent, it actually translates to P of A times P of B. But in the general case, it's P of A times P of B given A. And that is the general product rule that works every time. That means when the events are independent and when they're not independent. Now let's look at a dice example. Here's a question that you've seen before. What is the probability that the sum of 2 dice that I throw randomly is 10? Well, there's 3 cases divided by the total 36 of them. So the answer is 3 divided by 36. Which in lowest terms, it's 1 over 12. Now, let's put a condition. I'm telling you that I looked at the first one, and the first one is a 6. So, what is the probability that now the sum is 10 given that the first one is 6? Well, let's calculate it. Because the first one is 6, now we live on this bottom row. The top 5 rows don't matter anymore because our new sample space is just this bottom row. And among this bottom row, well, there's 6 cases and one of them is favorable. So the probability is now 1/6. So the probability changed from 1/12 to 1/6. Now let's look at another problem. What is the probability that the sum is 10, but now the condition is that the first one was a 1. So I looked and the first one was a 1. Now what is the probability that the sum of them is 10? Well, if the first one is a 1, then now we live on this row over here, the first one. And on this row, there's 6 elements, and none of them satisfy that the sum is 10, because the ones where the sum is 10 are on the very bottom. Therefore, the probability is 0. And it makes sense, right? If the first one is a 1, there's no way I can add to 10, because the second one can at most be a 6. So this probability changed to 0. So let's apply this rule. In a school with 100 kids, again, let's say 50 of them play soccer and the other 50 don't play soccer. Now we're going to split them into 2 rooms of size 50. And now they can go to any room they want. But here is more information. The first room has a TV that is showing the World Cup. And the second room has a TV that is showing a movie that is completely unrelated to soccer. And each room fits 50 kids. Now, out of your intuition, how many kids in room 1 do you expect to like soccer? And I'll remind you, the first room has a TV playing the World Cup and the second one doesn't. So how many kids in room 1 do you expect will like soccer? Well, all things being fair, we can imagine that all the kids who like soccer went to the room with the TV that's playing the World Cup, as illustrated. Maybe this didn't happen, but we can assume that that happened. So these two events, soccer and room 1, are dependent. Before they were independent, but now they are dependent. In the example that we did previously, the kids were split randomly. That made the events independent. But here, this is not the case. They're dependent, so the probabilities change. Now let's do a slightly different problem. Let's say we have a school of 100 kids, 40 of them play soccer and the rest don't. And among the kids that play soccer, we've noticed that on any given day, 80% of them like to wear running shoes. So now help me estimate how many kids play soccer and wear running shoes. So 40 kids are shown here, and let's say that 80% of them are wearing running shoes. So let's split them into groups of 20% each, and 4 of these sections are wearing running shoes. So that's 32, because 80% of 40 is 32. And 32 is our estimate for how many kids like soccer and are wearing running shoes. So let's look at the same problem from a different lens. The probability that a kid plays soccer is 40%. That means if we have 100 kids, 40 of them play soccer. And that's P of soccer equals 0.4. Now, the probability of not soccer is 0.6 or 60%. That means that among these 100 kids, 60 of them don't like soccer. Now, among the kids that play soccer, 80% of them are wearing running shoes. Therefore, the probability of running shoes given soccer is 0.8. Now, we want the probability of soccer and running shoes. Well, for that we need the probability of soccer, so that's this 40 over here, times the probability of running shoes given soccer, which is this 80% over here. So 80% of 40, or 0.4 times 0.8. That's probability of soccer times probability of running shoes given soccer, and we get 0.4 times 0.8, and that's 0.32. That is the 32% that we expect that will play soccer and wear running shoes. So we say that the probability of S intersection R is 0.32. Now let's look at something else. Let's say that somebody tells me the following information. The probability that a kid wears running shoes when they don't like soccer is 50%. That means that among the kids that are not playing soccer, half of them wear running shoes. So what's the probability of not soccer and running shoes? Well, P of not soccer intersection running shoes, that means the kids who don't play soccer and are wearing running shoes, is equal to P of not soccer, which is this 60% over here, times P of running shoes given not soccer, which is this 50% over here. And so that's 0.6, 60%, times 0.5. It's 50% of 60. And that's 0.3. And that is the probability that a kid does not like soccer and is wearing running shoes. Another way to see things is with a tree of probability. So two things can happen. The kid can play soccer or not play soccer. Plays soccer with a probability of 40% and doesn't play soccer with a probability of 60%. Now, among the ones that play soccer, wears running shoes with a probability of 80%, that's P of R given S, and doesn't wear running shoes with a probability of 20%. And among the ones that don't play soccer, wear running shoes with a probability of 50% and doesn't wear running shoes with a probability of 50%. So there's 4 scenarios. When they play soccer and wear running shoes, play soccer and don't wear running shoes, doesn't play soccer and wears running shoes, doesn't play soccer and doesn't wear running shoes. And the probabilities are S intersection R 32%, which is 80% of 40%, or the product. 8% for probability of S intersection R prime, that's not R. That is the ones that play soccer and don't wear running shoes. That's 20% of 40%, or the product of 20% and 40%, which is 8%. For the ones that don't play soccer and wear running shoes, that's 30% because it's 50% of 60%, or 0.6 times 0.5. And the same thing for the ones that don't play soccer and don't wear running shoes. So these are all the possibilities. So now let's recap the cases that we've seen before since the very beginning. First, we split the kids into 2 rooms randomly, and that created 2 independent events. Independent events can be seen graphically when the 2 lines, the one that splits the kids from the room 1 and room 2 and the kids that play soccer don't meet at a point. So these events are independent. Then we had the case when they were running shoes or not wear running shoes, and those events were dependent because it's more likely that the kid wears running shoes if they are playing soccer than if they're not. So those events are dependent. And another case was when we sent them into 2 different rooms, but one of them had a soccer game and the other one didn't. Those cases were very dependent too, because it's much more likely that the kid will go watch the soccer game if they like soccer. Now, this may not be exactly the same numbers we had before, but just to show you that this case is also dependent. And so when the lines cross, the cases are independent like in the left, and when they don't cross, they're dependent like in the right. In the following ungraded lab, you'll have a chance to see some of the ideas you've already learned about probability in action. You'll use Python to simulate the birthday problem I showed you earlier and compare the results you get from those simulations to the results you would get if you solve these problems analytically. You will examine several different variations of the birthday problem, see visualizations of the simulations used to address each problem, and get walked through how to analytically approach them as well. I hope you enjoy reinforcing what you've learned, and I'll see you when you're done in the next video. So imagine the following scenario. There's a rare disease going on, and you want to get tested for it. So you go to the doctor, and the doctor says, I have a very effective test, which is correct most of the time. You take the test and then go home, and then the doctor calls and said you tested positive. So maybe it's time to panic, but before panicking, I always do some math. So the idea is to calculate the probability that you have the disease given the fact that you tested positive. This is an example of Bayes' theorem. Bayes' theorem is one of the most important theorems in probability, and it's used all over the place, including in machine learning. It is used for spam recognition, speech detection, and many other things. So let's take a look at Bayes' theorem in this example with some numbers. So let's put some numbers. Let's say there's 1 million people in the population, and let's say that the illness only affects 1 of every 10,000 people. Now, the test that the doctor gives you is 99% effective. What does that mean? That means 2 things. That out of every 100 sick people, 99 get correctly diagnosed as sick, and 1 gets incorrectly diagnosed as healthy. And among every 100 healthy people, 1 gets misdiagnosed as sick and 99 get correctly diagnosed as healthy. Now, you went to the doctor and you tested sick. So now the question is, are you really sick or not? More specifically, what is the probability that you're sick given that you tested sick? Let's try to find this probability before panicking. So here's a quiz to test your intuition. Where do you think that probability lies? So let's look at the 1 million people to find out the probability. Among the 1 million people, only 1 out of every 10,000 is sick. So 999,900 are healthy and only 100 are sick. Now let's test every single person. So here on the left, we're going to have the ones that were diagnosed sick, and on the right, the ones that were diagnosed healthy. Now, since the test is 99% effective, then among the many healthy ones, it only made a mistake in 1% of them, and that's this 9,999 here. So those were healthy people who were diagnosed as sick. This group over here was 99% of the healthy people that were correctly diagnosed as healthy. This group over here on the bottom now is the sick ones. And since the test, again, is 99% healthy, that means the test correctly diagnosed these 99 out of 100 sick ones, and it misdiagnosed this one person here as healthy while the person is sick. Now let's look at the people who are diagnosed sick. We have to figure out the probability that you're sick given that you were diagnosed sick. So we're only looking at the left two rectangles. The probability that you're sick, given that you diagnose sick, means you only live here because these are the people who were diagnosed sick. And what is the probability that you're sick among this group? Well, in this group, only 99 people are sick. And what's the total? 99 plus 9,999. So most of them are actually healthy. Can you see again? Most of the people who were diagnosed sick are actually healthy. There's 9,999 of them and only 99 who were actually sick. So the probability that you're sick when you belong to this group is simply 99 divided by 99 plus 9,999. That's 99 divided by 10,098, which is 0.0098, which is actually less than 1%. So isn't that astonishing? You were diagnosed sick, but the probability that you're actually sick is less than 1%. The probability that you are sick and diagnosed sick is the number of people who were sick and diagnosed sick divided by the total number of people who were diagnosed sick. But a lot of people were diagnosed sick because that 1% of the healthy people who were diagnosed sick is a lot bigger than the 1 out of every 10,000 who were actually sick and diagnosed sick. And what you saw here was just an example of Bayes' theorem. We can look at it as a tree. Let's say here's 1 million people. Here are the 100 sick ones, there's not too many, and the 999,900 healthy ones. Now among the sick ones, some of them are diagnosed sick, that is 99% of them, and some of them are diagnosed healthy, which is 1% of them. Now among the healthy ones, 1% are diagnosed sick, that's misdiagnosed, and 99% of them are diagnosed as healthy. So we have 4 groups. The sick and diagnosed sick, that's 99 people. The sick and misdiagnosed as healthy, that's 1 person. The healthy and diagnosed sick, which is a misdiagnosis, there's 9,999 of them. And the healthy and diagnosed healthy, which is the majority of the population. Now, since you went to the doctor and got diagnosed sick, then you are in one of these 2 groups. These are the diagnosed sick. So those are the groups that matter. And if you're in these groups, most of them are healthy and misdiagnosed. So the probability that you are actually sick is 99 divided by 10,098, which is less than 1%. So a little surprising, but that's Bayes' theorem in action. Now let's look at some formulas. So remember that we're trying to find out the probability that you're sick given that you tested sick. And here's all the information that we had before. So we're going to look at the people who were actually sick and diagnosed sick, because we want the probability that you're sick given that you tested sick. So what's the probability that you're sick given that you were diagnosed sick? Well, given the fact that there's 1 million people, 1 out of every 10,000 is sick, then the probability of being sick is 1 divided by 10,000. That's 0.01%. That's a very, very small sector of the population. And that's the key of this problem, that not many people are sick. More people are misdiagnosed than the people that are sick. So what's the probability of not being sick? Well, it's 100% minus this. So 99.99. That's the probability of being healthy. Now let's throw in the test. The test is 99% effective, both for sick and for healthy people. So the probability that you are diagnosed sick, given that you're sick, is 99%, because that's the probability of a correct diagnosis. And 100 minus that is the probability that you're diagnosed sick, given that you're not sick. That's the probability of a misdiagnosis. So that's 1%. Now we want to find the probability that you're sick, given that you diagnosed sick. So we need to do some math. Let's use some variables. A is sick and B is diagnosed sick. So what we want is the probability of A given B. Now, from the conditional probability formula, P of A given B times P of B is P of A intersection B. So if we divide by P of B, we get that P of A given B is P of A intersection B divided P of B. Let's remember what things are. P of A given B is P of sick and diagnosed sick divided by P of diagnosed sick. Let's remember this. Now, we want to find P of sick and diagnosed sick, and we also want to find P of diagnosed sick. and we're going to use Bayes' theorem. So how do we find these two expressions, the top one and the bottom one? Well, let's look at conditional probability again. Probability of A and B is probability of A times probability of B given A. So the probability of sick and diagnosed sick is going to be the probability that you're sick times the conditional probability that you're diagnosed sick given that you're sick. That's simply the conditional probability formula. So that's what's going to go on the top. Now, what's going to go on the bottom is a little more complicated, but not that much. Let's go back to the tree of possibilities. We have this one over here, which is probability of sick and diagnosed sick. This one over here is the product of these two. That's exactly the conditional probability formula. So therefore, when we try to find P of diagnosed sick, we have to look at this group over here. Notice that the people that are diagnosed sick belong to two groups, the ones that were sick and correctly diagnosed sick, or the ones that were healthy and misdiagnosed as sick. And this is the formula for the union. Because the people that are diagnosed sick are the union of those that are sick and diagnosed sick and those that are healthy and diagnosed sick. And because these groups are disjoint, because you can't be sick and not sick, then the probabilities are going to add. So the probability of being diagnosed sick is the sum of these two things, and that goes in the denominator. And now all we have to do is apply the conditional rule one more time. Probability of sick and diagnosed sick is probability of A intersection B. We can use this formula over here, which actually gives us exactly this thing over here, which is P of sick times P of diagnosed sick given sick. Now we can do the exact same thing for P of not sick and diagnosed sick. That's also an intersection. It's just A prime intersection B. And that's probability of not sick times probability of diagnosed sick given not sick. So those things can go in the denominator, and that's exactly Bayes' theorem. Now, when we plug in the numbers, what do we get? This is 0.01%, this is 99%, this over here is 99.99%, and this is 1%. So, what do we get here? Well, it's going to be the following numbers. This over here is P of A, this is P of A prime, this is P of B given A, and this is P of B given A prime. And those go over here in the formula. And now, when we plug in the numbers, we get 0.0001 times 0.99 divided by 0.0001 times 0.99 plus 0.9999 times 0.01. And that gives us exactly the number that we wanted. So that formula in the middle, P of A given B equals P of A, P of B given A, divided by P of A, P of B given A, plus P of A prime, P of B given A prime, that is Bayes' theorem. And that may look confusing, but don't worry, we'll see it again and it'll be very clear. Next, you'll find another lab in Python that lets you experiment with the Monty Hall problem, a classic problem from probability. This is a great chance to continue to deepen your understanding of conditional probability, as well as another chance to compare the results you get from simulation to those you get from approaching a problem analytically. Enjoy! Let me show you another example of Bayes' theorem. This time we're trying to find if emails are spam. So let's say that we have a big data set of 100 emails and 20 of them are actually spam. So we want to build a classifier. The easiest classifier that we can find is one that says that everything is spam with a 20% probability, because that's all we know so far. So that's a pretty simple classifier. We want to find something more elaborate. And so we're going to look at a feature. We're going to start noticing that the spam emails tend to have words like lottery. So we're going to try to put the word lottery into our spam detector. We're going to do the following. We're going to see how many emails among the spam ones contain the word lottery, and we notice that there's 14 of them. Now we're going to look at how many of the emails that are not spam, that we're actually calling ham, that's a way to call them, have the word lottery. So there's 10 of them. So now, what is the probability that an email containing the word lottery is spam? In other words, what's P of spam given lottery? Well, take a look at something. We only care about the emails that contain the word lottery. So all of these emails don't matter. We only care about these 24 emails that contain the word lottery. And remember that we want to find the probability of spam given lottery. That's going to be, well, among the 24 emails, how many of them are spam divided by how many of them are in total. And 14 of them are spam, and there's 24 in total. So the probability in lowest terms is 7 divided by 12, or 0.583. This is exactly Bayes' theorem, and if you were to apply the formula from the previous video, you would get exactly 0.583. But I really want to make this clear. What you're doing when you use Bayes' theorem is deleting all the emails that don't really matter, taking a look only at the ones that have the condition, which is the word lottery, and among those, the probability calculation is easy. You simply take the number of spam emails that contain lottery divided by the total number of emails that contain lottery. But let's do it with some math. We want to find the probability of spam given lottery. Recall that Bayes' theorem says this, where A means the email is spam, B means the email contains lottery. So in other words, this is the formula we want to find. So let's calculate all these numbers in this formula and plug them in and get the same number we found before. So what is the probability of spam? Well, we don't know the word lottery yet, and so all we know is that among 100 emails, there's 20 spam ones, and therefore the probability of spam without knowing anything about the email is 20 over 100, or 0.2. This is called the prior. This is the original probability that you calculate without knowing anything. This is the most basic piece of knowledge you have in this problem. Now, what is the probability of not spam? Well, it's 1 minus the probability of spam, so that's 80 over 100, or 0.8. Now, what is the probability of lottery given spam? Well, we are only looking at the spam emails. There's 20 of them, and 14 of them contain the word lottery. So the probability of lottery given spam is 14 divided by 20, which is 0.7, or 70%. And now, what is the probability of lottery given not spam? Well, there's 80 not spam emails. 10 of them contain the word lottery, and therefore the probability of lottery given not spam is 10 over 80, which is 1/8, or 0.125. So now let's plug in these numbers. P of spam is 0.2, P of lottery given spam is 0.7, P of not spam is 0.8, and P of lottery given not spam is 0.125. And we're going to plug them into this formula. So we get P of spam given lottery is 0.2 times 0.7 divided by 0.2 times 0.7 plus 0.8 times 0.125, which is exactly 0.583. So that coincides with what we got at the very beginning. Now, this is something I mentioned before, but let me formalize it. We have something called the prior. That is the original probability that you can calculate not knowing anything else. Then something happens, and that's the event. The event gives you information about the probability. And with that information, you can calculate something called the posterior. So we had that the prior was P of A. An event can be called E, and the posterior is P of A given E. Now let me give you some examples. In the spam email, the prior was 20%. The prior was the number of spam emails divided by the total number of emails. The only thing I know about an email, if I know nothing else, is that it has a 20% probability of being spam, because I know how many emails are spam in total. That is a very basic unit of information, and I need to know a little more. So we come up with a condition, an event. It says that the email contains the word lottery. So now the posterior changes. Now the probability that the email is spam, given that it contains the word lottery, is no longer the number of spam emails divided by the total number of emails, but it's now the number of spam emails with the word lottery divided by the total number of emails with the word lottery. And that's a much better probability. That's a much more accurate probability. So the posterior is always a better estimation than the prior because we have that event that gave us information. In the medical example, there was also a prior, an event, and a posterior. The prior was the original probability of being sick. The event is the fact that you diagnosed positive, and the posterior was the probability that you were sick given that you diagnosed positive. Now let's look at another example. Let's say you're rolling 2 dice and you want to find the probability that the sum of the values is 10. We know that that's 3 divided by 36. Now, if the event says that the first dice is a 6, then all of a sudden your posterior changes. Now it's 1/6 because you live in a different space. So that is the posterior. And in another example, the coin example, if you want to find the probability that both coins land in heads, then that's 1/4. But the event says that the first coin landed in heads. Therefore, in the posterior, you no longer have the second row, and the new probability is 1/2. So let's go back to the Bayes' theorem example where we had the prior, the probability that an email is spam, the event that gives us information about the email, and the posterior, which is a new, better probability that the email is spam given the event, which is that it contains the word lottery. Now, obviously, we're not going to build a classifier with only one word. We're going to use it with many, many, many words. So let's look at another one. Let's say that we use the word winning, and we calculate the posterior probability of an email being spam given the fact that it contains the word winning. Now, how would we combine these two? How would we make a stronger classifier with the words lottery and winning? The idea would be to find the posterior here. So we can do it in a simple way by simply calculating the probability that an email is spam given the fact that it contains lottery and winning by dividing the number of spam emails that contain lottery and winning by the number of total emails that contain lottery and winning. In other words, if this is Bayes' theorem, we'd be calculating this number as the number of spam emails that contain the two words divided by the total number of spam emails. But can you see a problem there? Well, imagine if I don't want to do this with 2 words, but with 100 words, W1 up to W100. So here's Bayes' theorem. And if I want to calculate this, then I need to divide the number of emails that contain all 100 words divided by the number of spam emails. However, asking for an email to contain 100 words is very hard. Maybe there's no emails like that in our database. And so we get 0 over 0. And that's not a good calculation. So what can we do? Well, let's go back to the problem with 2 words. And the idea is that we really want to calculate these. And if we can't calculate them, then we can at least estimate them. And we're going to estimate them using a naive assumption. The naive assumption is the key to naive Bayes, and that's why it's called naive Bayes. And the assumption says that the appearances of the words lottery and winning are independent from each other. Now, this is obviously not true. Words are not independent from each other. Words depend on each other. If I have the word good appearing, well, the word morning is more likely to appear because good morning tend to appear together. So words are dependent. But if we assume that they're independent, then the math works out much, much better. And we actually can get some pretty good results by making this naive assumption. So that's why we build a naive Bayes classifier. So when you look at probability of lottery and winning given spam, that's the probability of an intersection of 2 things. And if they happen to be independent, then their probability is the product of the 2 things. So all of a sudden, we don't have probability of lottery and winning given spam. We have probability of lottery given spam times probability of winning given spam. And the same thing for the denominator for spam and for ham. And the same thing happens with n words. N can be huge, but the probability of an email containing all these words given that is spam can be estimated as the product of all these probabilities of the email containing each one of the words given that it's spam. And that is the naive Bayes algorithm. That is the calculation for naive Bayes. Let's look at an example. Let's go back to the previous example where we had that there's 20 spam emails out of 100 and therefore the prior is that the probability of spam is 20%. The probability of ham, which is not spam, is 80% because it's 100 minus 20%. And because among the 20 spam emails, 14 of them contain the word lottery, then the probability of lottery given spam is 14 over 20, which is 0.7. And because there were 10 ham emails containing the word lottery out of 80 total ham emails, then the probability of lottery given ham is 10 over 80 or 0.125. When we do the same thing with the word winning, we see that there are 15 spam emails that contain the word winning and only 8 ham emails that contain the word winning. So P of winning given spam is 15 over 20 or 0.75, and P of winning given ham is 8 over 80, which is 0.1. So with these numbers, we are going to do the calculation. So here is what we had for naive Bayes. And when we get the calculation with these numbers, we get that the probability of an email being spam, given that it contains the words lottery and winning, is 0.2 times 0.7 times 0.75 divided by 0.2 times 0.7 times 0.75 plus 0.8 times 0.125 times 0.1, which is 0.913. And as you can imagine, if an email contains the words lottery and winning, it's much more likely to be spam. So this 91.3% is much higher. So that is the naive Bayes algorithm. Is very useful and very powerful. And in a lab, you're going to be able to play with it. So you may be wondering, why are we talking so much about probabilities and what do they have to do with machine learning? Well, it turns out that machine learning is a lot about probabilities. Many times in machine learning, what you want to do is you want to calculate a probability of something given some other factors. So for example, in spam detection, you try to calculate the probability that an email is spam based on the words on the email or the recipients or the attachments or other features of the email. This is a conditional probability because probability of spam given some features. Another example is sentiment analysis, where you want to determine if a piece of text is happy or sad. In this case, you want to find the probability that the piece of text is happy given the words it contains. Let's do another example, image recognition. In here, you try to find out if an image has a particular thing or not. Let's say that you want to recognize if there's a cat in an image or not. So you calculate the probability that there's a cat in the image based on the pixels in the image. So these are all conditional probabilities. However, pure probabilities also appear a lot in machine learning. There's another big area of machine learning called generative machine learning, and it's a part of unsupervised machine learning, where you want to maximize probabilities. So for example, image generation, if you've seen these great images of faces, for example, that are generated by computers, in here you want to maximize the probability that a bunch of pixels form a human face. Or in text generation, you want to maximize the probability that a bunch of words are sensical text and that it talks about a certain thing. So all of these are examples of machine learning that use a lot of probability, and let me elaborate on them now. So in the previous videos, you got to see Bayes' theorem in action, where first you find the prior, the probability that an email is spam, but just the initial probability, namely dividing the number of spam emails divided by the total number of emails. Then there was an event, for example, the email contains the word lottery, and then a posterior which refined this probability by creating a tree of possibilities. This gave us 4 possibilities: that the email was spam and lottery, that it was spam and no lottery, that it was ham and lottery, and that it was ham and no lottery. And then you further calculated the probability of spam and lottery by forgetting all the emails that don't contain the word lottery and doing the calculation there. Then the probability of spam given lottery is equal to the probability of spam and lottery divided by the sum of the probabilities of spam and lottery and ham and lottery, and that was the posterior. But when you look at this in high level, what really happened is that you created a machine learning classifier by something that gives you a calculation of a probability of a thing given another thing. And that is what machine learning is in many cases. Imagine image recognition. Let's say that an image recognition classifier tells you if an image contains a cat or not. What this is really doing is telling you the probability that you have a cat in an image based on some events, and the events are the pixels in the image. So a classifier will tell you the probability of cat given pixel 1, pixel 2, all the way to pixel n. This is an image classifier. Another example would be in the medical field. Let's say that you have a bunch of demographics and symptoms of the patient and a lot of metrics, and you want to know if the patient is healthy or not. So what you do is you calculate the probability that the patient is healthy based on their symptoms and their history. So you build a model that calculates this conditional probability. So here's another example, sentiment analysis. In sentiment analysis, what you do is you train a model that will tell you if a given sentence is happy or sad. And what you're doing here is calculating the probability, the conditional probability that an email is happy based on some events. And the events are the words in the sentence. So let's consider the image recognition problem to see how this works. What you do is you train some model, and this is the model. And the model, what it does is it takes an image, so a bunch of pixels, and tells you the probability that the image has a cat given the pixels. In this case, it would be 0.9 because it's a cat. And if you give it something different, say a car, then it says, well, the probability that you have a cat here given the pixels is going to be very small. So let's say 0.1. So you determine that this is not a cat. So as you see, machine learning is all about finding conditional probabilities. In particular, this is supervised machine learning because you're answering questions about the data. For example, does the image contain a cat? Is the sentence happy? Is this email spam, etc. Another very interesting example of conditional probabilities are generative models. For example, face generation models. The idea is to train a model that can generate a group of pixels that result in an image that looks like a human face. This is done by trying to achieve a high probability of the image being a face given the generated pixels. For example, the image on the right is not a real person. It was generated by a model called the style GAN. I don't know about you, but this really fooled me. That face looks very real. Welcome to lesson 2. Now we get to one of the most important concepts in probability, which is the concept of a random variable. And it's not something that new. You've seen variables before. For example, in algebra, you may have learned the variable x equals 3. It always has the same value. Random variables are different. They can take many values. For example, the temperature is a random variable that can take many values. Another random variable is the number of heads I obtain if I toss a coin 10 times. That is another random variable. So in this video, I'm going to show you all of our random variables. So let's go back to the coin flipping experiment. When you flip a coin, let's say you can obtain heads or tails. And let's say that you can obtain them both with a probability of 1/2, like before. Now, let's change this around a little bit. Let's take a variable x and call it the number of heads. So what happens now? When you flip a coin, how many heads can we obtain? Well, if we obtain heads, then we obtain 1 head. And if we obtain tails, then we obtain 0 heads. If we look at x, then x can be 1 if we obtain heads once, and x can be 0 if we obtain heads 0 times. And the probability of x equals 1 is the same probability of obtaining heads, which is 0.5. And the probability of x equals 0 is the same probability of obtaining tails, which is 0.5. X is called a random variable and is one of the most important concepts in probability and statistics. You can think of x as a variable that not always has the same value. Half of the times it takes a value of 1 and half of the time it takes a value of 0 roughly. Now let's look at another random variable. Let's look at the number of heads we obtain in 10 coin tosses. So let's say we flip it 10 times and all of them are heads, so x equals 10. Or we flip them and one of them is tails, so we obtain x equals 9. And we can obtain x equals 9 in many different ways. And let's say we stick to probability of heads equals 0.5. So what are the probabilities of these events? Well, since all of them are independent, all of them have probability 1/2, then this is 1/2 to the 10th. What about the second one? Well, it's also 1/2 to the 10th, but we can write it as 1/2 to the 9 for all the heads and 1/2 for the remaining tail. And the same thing for the next one. However, a harder problem is to actually ask what's the probability that we obtain 0 heads in total, p of x equals 0, or p of x equals 1, or all the values until p of x equals 10. Because on the left, we have a particular scenario, a particular way to obtain the heads and tails. But on the right, we're grouping them all. As you can see, the first one is the same. P of x equals 0 is the same as obtaining all the heads, which is 0.5 to the 10. But the others are a little harder. So when I want to calculate things, the first thing I do is run an experiment. So let's run an experiment. So let's say we run this experiment many times and we obtain x equals 5, x equals 6, x equals 5 again, and we run it many times. And what are the possible outcomes? Well, the possible outcomes are 0 all the way to 10, because you can obtain 0 heads, 1 heads, all the way to 10. And if we stick to probability of heads equals 0.5, and let's say we're going to repeat this 500 times, and let's see what we obtain. The histogram we obtain is this one over here. Notice this is just a histogram. It's not the actual probabilities, but it gives us a good estimate of the probabilities because we ran it a bunch of times. Notice that the probability of x equals 0 or x equals 10 are the smallest ones because it's not likely that we're going to obtain 10 heads or 10 tails. The highest one is over here, p of x equals 5, because it's likely we're going to get roughly half-half. And we can see all the other ones. For example, here's p of x equals 8. That's when you obtain 8 heads and 2 tails. So this is a random variable. Why do we care about random variables? Because they allow us to model the entire experiment at once. And most problems in probability can be expressed as random variables. So for example, if you flip a bunch of coins, as we saw, and x is the number of heads, that's a random variable. You can roll a bunch of dice and define x as the number of times you obtain a 1. Or you can see a bunch of patients and say that x is the number of sick patients. Or you can just define random variables. Let's say I define one that is 1 with probability 1/2, but it's also -7 with probability 0.2, and it's also 3.14159 with a probability of 0.3. I can come up with any random variable I want that takes any values. As long as the probability is set to 1, I'm good. Now, here are other random variables. For example, if you're waiting for the bus, the wait time until the next bus arrives is a random variable. It could take many different numbers. The height of a gymnast jump is also a random variable that has some range of values. The number of defective products in a shipment is also a random variable. And let's say the number of millimeters of rain in November is also a random variable. You may be noticing that they behave in different ways. And that's because there's two big types of random variables. There's discrete and continuous random variables. Discrete ones are the ones we've been seeing so far. The number of ones or sixes if I roll the dice, the number of heads if I flip coins, the number of kids in a specific group with a particular height or a particular age. And the continuous ones could be, for example, the amount of time till the next bus arrives, the height of a gymnast jump, the number of millimeters of rain in a particular month. Why are they different? I encourage you to take a look and tell me why you think they're different. And one thing that happens is that the one on the left can take a finite number of values. I can flip a coin 10 times and I could obtain 0 all the way to 10 heads. On the other hand, the ones on the right can take an infinite number of values because the time can be 1 minute, but it can also be 1.01 minute or 1.000123 minutes. There's an infinite number of values they can take. But actually, this is not true. The discrete ones can also take an infinite number of values. I'll give you an example. If I start flipping a coin until I obtain heads, I could do it 1 time or 2 times or 3 times or 4. I could do it 500 or 1,000,000 and perhaps not obtain heads. The probability is very small, but I have an infinite range of values. So what really happens is that the discrete ones can only take a countable number of values, whereas the continuous one take values on an entire interval. So the values that a discrete random variable can take can be put in a list 1, 2, 3, 4, 5, etc. Whereas the values that a continuous random variable take cannot be put in a list because it's an entire interval. Now you may be thinking, what's the difference between these random variables and the ones that you see in algebra and calculus? And the difference is that the ones you see in algebra and calculus are deterministic and the ones we see here are random. What is deterministic? For example, x equals 2, or for example, the input of the function f of x equals x squared. They always take the same value. Once it's defined, it's like that forever. However, the random variable is not like that. It can take, for example, many values. They're associated with an uncertain outcome. So deterministic variables are associated with a fixed outcome, and random variables with an uncertain outcome. And that's the main difference. In lesson 1, you learn how to calculate individual probabilities and how to do math with them. But imagine that you have all the possible scenarios that can happen. Put them on this horizontal axis. And for each one of them, look at the probability that they happen. This forms a probability distribution. And that's the topic for this lesson. So imagine now that you're tossing 3 coins and you're interested in the number of heads. This will be your random variable. How does each outcome of the experiment affect the random variable? Well, the first possibility is that you get no heads. The second one is that you get 1 out of 3 heads, but here you can see that you actually have 3 options to obtain 1 heads, either on the first, the second, or the third coin. The same is true if you get 2 heads out of 3, where you can get tails either on the first, second, or the third coin. And again, there's only 1 option to obtain all 3 heads. Now let's reorder this a bit. You can see that you just have 1 way of getting 3 tails and 1 way of getting 3 heads. However, there are 3 ways in which you can obtain 1 heads and 2 tails, or 2 heads and 1 tails. Now you can divide this number by the total number of possible outcomes, which is 8, and what we get are probabilities for each of the outcomes. And from this image you can clearly see why it is much more likely to obtain 1 or 2 heads than 0 or 3. And it is because of how many different outcomes contribute to each of these options. And now we can look at this as just a normal histogram. Now let's look at another slightly more complex example where you flip 4 coins. Your new variable is the number of heads in 4 coin tosses, and you can see that something similar has happened. There's only 1 option when you have all heads or all tails. However, there are 4 ways in which you can obtain 1 heads or 1 tails. And finally, this one's a bit more complex, but you have 6 possibilities where you see 2 heads and 2 tails. This gives you a total of 16 possible outcomes for how your coins can land. So you assign 1/16 to 1 and 4 heads, 4/16 to 1 and 3 heads, and finally 6/16 to seeing 2 heads, and those are your probabilities. And this is the histogram we obtain for 4 coin tosses. Now let's look at another variable, the number of heads in 5 coin tosses, and again with all heads or tails there's 1 option out of 32 total. With 1 head or 1 tail, there's actually 5 options out of 32. With 2 or 3 heads, there's actually 10 options. Now, it's easy to figure out that for all heads, there's only 1 possibility, or for only 1 head, there's as many possibilities as flips, because the head can be any of the 5 flips. But how would you calculate that there are 10 options for 2 heads? Luckily, there's just a method for that. Stay with me in the next video to find out how it works. Each bar represents the probability that the variable x3 takes each of the possible values 0, 1, 2, 3, 4, and 5. Now for each x from 0 to 5, you have the probability that x3 is x. This is called the probability mass function of x3, and we use a lowercase p to represent it. All discrete random variables can be modeled by their probability mass function, also abbreviated as PMF, since it contains all the necessary information to understand how the probability distributes among all the possible values of the variable. Now, what are the requirements for the PMF? First of all, since it's defined as the probability that the random variable takes at a particular value, then it always has to be positive. Now note that when you sum the PMF over all possible values, they all sum to 1. This makes sense since you're considering the probability of all possible outcomes of the experiment. The second condition for the PMF is that the sum of all its values must be 1. By the way, x1, x2, and x3 are very similar. They're all counting the number of heads in a fixed number of coin tosses. It was 3 for x1, 4 for x2, and 5 for x3. Also, the way the probability is distributed over all possible values follows a similar pattern. Could there be a single model to represent all these random variables? It turns out there is, and it's called the binomial distribution. You'll learn about that in the next video. So let's start with one of the simplest distributions out there, the binomial distribution. I like to imagine it with coin tosses. Let's say I toss a coin 10 times. How many heads can I obtain? Well, it could be 0, 1, 2, 3, all the way up to 10. Each one comes with its own corresponding probability. So we draw the histogram of probabilities, and that's the binomial distribution. The binomial distribution is an example of a discrete distributions, which are the simplest ones that we'll see first. Later in the course, we'll learn the continuous ones too. But let's get to the binomial distribution now. So what is the probability to obtain 2 heads when you flip 5 coins? For each flip, there's a 1/2 chance to get heads or tails. And if you multiply these together, you get 1/32, which is the probability of this specific outcome. But there are more ways to obtain 2 heads out of 5. For example, this one here. And this one has exactly the same probability to be obtained as the one on top. And it turns out that there are actually 10 possibilities to get 2 heads out of 5. If you look at the ways you can order 2 heads and 3 tails, you will see that there are actually 10 ways to do that. Each of these sequences of heads and tails has the same probability, 1 over 32. Now, is there some general way to find the number of possible combinations? This is just ordering a sequence on 2 heads and 3 tails. So 5 factorial is the number of ways you can order 5 coins, but this is overkill because these 5 coins have repeater numbers, so you need to account for that. Divide 5 factorial by 2 factorial to remove all the cases where you have simply swapped the 2 heads, and now also divide it by 3 factorial to remove all the cases where you have simply swapped the 3 tails. This is called the binomial coefficient, and it counts the number of ways you can order 2 heads and 3 tails. In general, the coefficient n choose k counts all the combinations in which you can have k heads in n coin tosses. One fun property is that n choose k is the same as n choose n minus k. And the reason for this is because obtaining k heads is the same thing as obtaining n minus k tails. And this is why the PMF of a fair coin has a symmetrical shape. Now, can you find a general way to write the PMF for the number of heads in 5 coin tosses? Well, for more generality, suppose that the probability of heads is p. Consider the event capital X equals lowercase x, where capital X is the random variable and lowercase x is the number of heads in 5 tosses, which can be 0, 1, 2, 3, 4, or 5. What is the probability of this event? Well, you will need to have x heads, so that has probability p to the x. This is the probability of one particular order, and the remaining 5 minus x tails with probability 1 minus p to the 5 minus x. However, this is just the probability for one particular ordering, so you need to take into account all the possible orders, which is 5 choose x. You're missing just one thing. This expression is of course valid for x equals 0, 1, 2, 3, 4, and 5, since you can have more than 5 heads in 5 coin flips. This is the PMF for x, and we say that x follows a binomial distribution. We denote it as binomial of 5 and p, where 5 is the number of flips and p is the probability of heads. And in general, this tilde symbol means that the variable x follows the distribution to the right of the expression. If p is 0.5 and n equals 5, then you get the following PMF. Remember that here you're flipping 5 coins and the probability of heads is 1/2. And the graph is here. Notice that since p is 1/2, then the PMF is symmetrical. In the case where we have a different p, so we have a biased coin, for example p equals 0.3, then you have greater chances of seeing a small number of heads, and this is reflected in the PMF. Now in the example, you were tossing 5 coins, but if you were tossing the coin any number of times, then the model should be the same. You're simply changing a parameter. In the case that we toss n coins, then we have a PMF like this, where the probability mass function is n choose x, p to the x, 1 minus p to the n minus x, and we call that binomial of n and p, where n and p are the parameters of the binomial distribution. N is the number of tosses, and p is the probability of obtaining heads. Now try to answer this question. What is the probability of throwing a dice 5 times and getting 3 ones? The order doesn't matter. Well, when you throw a dice, you can get a 1 or not a 1, which is not that different from a coin. In a coin, you can get heads or tails, and you can think of the die as a biased coin, where you get heads if you throw a 1, and tails if you throw anything else. So it's a biased coin. Now, for a dice, the probability of each value is 1/6. So now this coin will have a probability of heads of 1/6 and tails of 5/6, because that's all the remaining values. And you can draw a similar histogram as before for a different p, but the same n. This time you have n equals 5 and p equals 1/6. So in other words, we can look at a dice as a biased coin for this experiment. Now let's look at another case. Let's throw the dice 10 times, and just like before, we record the number of ones. This is again a binomial probability distribution. Can you tell me what are the parameters of this distribution? Well, the above problem can be represented with the binomial distribution where n equals 10, and 10 represents the number of dice throws, and p represents the probability of obtaining a 1, and that is 1/6. Therefore, the parameters are 10 and 0.1666. Now this works more generally when you need to pick k out of n numbers. You start by picking the first one, where instead of 5 options, we have n options. Then you need to pick the second, where we have one less option, and it's one less because you've already picked one number. So for each of the n numbers chosen in the first step, you can pick n minus 1 in the second step. Same thing for the third step, where you can only pick out of n minus 2 numbers, and so on. Until the kth step, where you can only pick from k minus 1 numbers less than n. This gives you unordered sets of length k, just like in the previous case. So how many sets are actually there? Well, it's a product of all the number of choices you had to make. So that's n times n minus 1 times n minus 2 and all the way to n minus k minus 1. And the reason is that all these can be taken as independent events. But as you saw previously, many of the combinations actually repeat. But how many of them repeat? Let's figure this out for a simple case. Let's say that the size of the set, which we named k, is 4. And these are some of the possible ways to arrange the numbers in the set. How many ways are there to order this set? Well, the problem is actually very similar to the one we did before, except that we don't have to go that far. So let's start by picking the first number, and then we pick the second one, and then we pick the third, and then we pick the fourth. For the first number, we have 4 options. For the second one, 3 options, because we've already picked the first. For the third one, we have 2 options, and for the fourth one, we have 1 option. So in total, we have 4 times 3 times 2 times 1 equals 4 factorial options. For 5 numbers, we would have the same thing but times 5. That's a 5 factorial. In general, the solution is k factorial. If you haven't seen that number, k factorial is very, very, very important in probability and combinatorics. And it's simply just a rolling product from k all the way down to 1. And k factorial is simply the number of ways of ordering k numbers, or k different objects. So now let's go back to where we were. We had that the number of ways of picking k numbers in an ordered fashion was n times n minus 1 all the way to times n minus k minus 1. But that picked every set many times. How many of them? Well, k factorial times, because k factorial is the number of ways to order that set of numbers that we picked. So since we want them unordered, then we have to divide by k factorial. And thus we obtain something that can be rewritten as n factorial over n minus k factorial. If you look carefully, that's the blue part, because n factorial is a product of n all the way to 1. And if I divide by the product of n minus k all the way to 1, that's n minus k factorial, then I obtain the product that I have in the numerator, n all the way to n minus k minus 1. And the denominator still has a k factorial here. So that is the expression for n choose k, for the binomial coefficient n choose k, the number of ways to obtain k elements out of a set of n in an unordered way. Now going back to our graphics, we can rewrite all these numbers. In the case of 0 heads, we have 5 choose 0, which is 5 factorial divided by 5 factorial times 0 factorial. Now 0 factorial is 1. Why is 5 choose 0 1? Because it's the number of ways of picking 0 things out of 0. And there's only one way to do that, which is not picking any. Therefore, in general, anything choose 0 is always 1. Now let's see how this changes if the coin is unfair or biased. Let's recall the case of throwing 5 coins. You remember we're counting the possible outcomes when we get 0 heads, 1 head, and all the way to 5 heads, and then divided by 32, which was the total amount of possible outcomes. Well, this was possible because all the outcomes were equally likely. But as you remember, the probability of all these outcomes was 1 over 32. However, if the coin is biased, and let's say it's padded, so it lands on heads with a probability of 30% and on tails with a probability of 70%, then all these outcomes have a different probability. The first one has 0.3 to the 5, which is 0.00243, whereas the second one has a higher probability because it's 0.3 squared for the 2 heads and 0.7 cubed for the 3 tails. And these are all the probabilities: 0.3 to the 5, 0.3 to the 4 times 0.7, 0.3 to the 3 times 0.7 squared, all the way to 0.7 to the 5. And so let's write them in general. So if we obtain heads k times, then the probability is 0.3 to the k times 0.7 to the n minus k. So here we have 0.3 to the 5 times 0.7 to the 0. And here we have all the other ones: 0.3 to the 4 times 0.7 to the 1, all the way to 0.3 to the 0 times 0.7 to the 5. So this is the general expression for the probability of each one of these scenarios. However, we need to account for all the possible orderings of heads and tails, not just heads at the beginning, tails at the end, and that's where n choose k comes in. So now we can take a look at how this thing looks in practice. You have your biased coin, which lands on heads with a probability of 0.3, and you flip it n times, which is 5. And you can again plot the histogram for the probabilities for each k, just like before, except that now you can calculate these probabilities using the formula that you have learned in the previous slide. And that's the binomial distribution. So let's go back to the coin flipping experiment. Remember that you used a variable x to denote the number of heads, and that's a random variable. So when you flip a coin, you can obtain heads or tails, and the number of heads can be 1 with probability 0.5 or 0 with probability 0.5. We're going to call that an experiment where we get a success if it lands on heads and a failure if it lands on tails. Now, we can make different experiments and also have success and failures. If we roll a dice and we consider success when it falls on 1 and failure when it falls on anything different, that means our variable is the number of ones, then the probability of success is 1/6 and the probability of failure is 5/6. And we can also have other experiments. For example, if a patient is sick or healthy, we can say that if X is the number of sick patients, then a success is when the patient is sick, which is slightly contradictory, but since we're counting the number of sick patients, then in this case, X equals 1 is a success. And the probability for a sick patient, let's say it's P, and for the healthy patient is 1 minus P. These are all examples of the Bernoulli distribution, a very important distribution in probability and statistics, which has one parameter, and the parameter is P, the probability of success. So now that you know about discrete distributions, let me tell you about continuous ones. And there's a difference between the two. In the discrete distributions, your events always form a list. For example, if I toss a coin 3 times, I could get heads 0 times, 1 time, 2 times, or 3 times. I could also think of the number of people in a town. It can be 0, 1, 2, 3, a million, etc. But I can always make a list of it. What is something that cannot be listed? An interval. For example, if my random variable is the amount of time that I wait on the phone or the amount of time I wait for the bus, that cannot be listed because I could wait 1 minute, but I could also wait 1.01 minute or 1.2237 or pi minutes. All these numbers cannot be listed. So when your events are a list, you have a discrete distribution. And when your events are an interval, you have a continuous distribution. Let me elaborate more on that. So imagine you're on a call with tech support and you're trying to find the probability that you will not wait too long. Let's say the call can take 1 minute, 2 minutes, or 3 minutes, for example, and we can try to plot the probabilities, say like this, where the heights of the bars are the probabilities that the call takes 1, 2, or 3 minutes. But they can also take something like 1.01 minutes to respond, right? Or 2.43. And you can quickly see that there's infinitely many values that call could take. And these values are everywhere between the ones you already have and also to the left and to the right. And if you remember from the last video, the sums of heights of all of them have to be equal to 1. But you can quickly see that by adding more and more and more of them, they have to get smaller and smaller and eventually become 0. So what did we do wrong here? Well, we did nothing wrong. The answer is that this distribution is fundamentally different, as it's not discrete, but it is continuous. So this approach will not really work. To try to understand this, think of how you would answer the following question. What is the probability that a call would take exactly 1 minute to the dot? And I encourage you to think about this. The answer is 0. Because there are simply too many values for the amount of time a call can take. There's actually uncountably many of them. It's a whole interval. And we're forced to say that the probability that a call takes exactly 1 minute, 0.00000 forever is 0. So we need to describe this problem in a slightly different way. So instead of asking what is the probability of the call taking a fixed amount of time, let's think of it in terms of windows. So we're thinking of what's the probability that the call lasts some time between a certain window, say between 0 and 1. And for that, we can have a probability and we can put it as the height of this blue bar over here. Then we can think of what's the probability that the call lasts between 1 and 2 minutes, and that's this other height, or between 2 and 3 minutes, or 3 and 4 minutes, and 4 and 5 minutes. And let's assume that the call never takes more than 5 minutes. And now we have a discrete probability distribution where the blue area, so the sum of the heights of these bars, add to 1. And notice that the majority of the calls take between 1 and 2 minutes, or between 2 and 3 minutes. Not a lot of them go all the way to 5 minutes, and that's what this probability distribution is telling us. Now imagine that we want a little more information, so we want to make these intervals a little more granular, so we make them 30 seconds instead. And now we have this distribution over here, where we now know the probability that the call is between 0 and half a minute, between half a minute and 1 minute, all the way to between 4 minutes and a half and 5 minutes. And if we want to make them still more granular, we can make them of 1/4 of a minute, 15 seconds basically. And now we have all this information between 0 and 1/4 of a minute, between 1/4 and a half minute, all the way to between 4.75 minutes and 5 minutes. And we can continue splitting these intervals and getting discrete distributions. And if we were to do this infinitely many times, then what we get is this. This is how a continuous distribution looks like. Imagine just a bunch of very, very, very skinny bars, infinitely many of them, that become just a curve. Now in the discrete distribution, we had that the sum of heights have to be equal to 1. The sum of heights was the same as saying the blue area. So in the continuous distribution, we have the same condition. The area under the curve is equal to 1. And that is a continuous probability distribution. So when you learned discrete distributions, you learned that each event had a probability. For example, the probability that I throw a coin 10 times and 3 of them land in heads is a certain number. When we talk about continuous distributions, we cannot talk about those probabilities in the same way. For example, if I make a phone call, the probability that the phone call lasts exactly 2 minutes to the dot is 0. But I can still talk about intervals. I can talk about the probability that a phone call lasts between 2 minutes and 3 minutes, or between 2 minutes and 2 minutes 30. These probabilities are encoded in something called the probability density function. Let me show you how. So before we return to the plot from the previous video, let's take a look at another simple case. Let's say that the call center answers with equal probability at any time window between 0 and 5 minutes. So, as you can see here, if we divide this area in 5 different parts, then the probability that the length of the call lands in any of the 5 rectangles is exactly the same. So given this information, what is the probability that the call is between 2 and 3 minutes long? Well, if you said 0.2 or 20%, that is correct. It's also 1/5, because there are 5 equal parts and this area adds to 1 because it's a probability distribution. So the area of that little rectangle is 1/5, and that's the probability that the phone call lasts between 2 and 3 minutes. Now, let me ask you another question. We're going to split it now in 10 small intervals of 30 seconds. What is the probability that the call lies between 2 and 2.5 minutes? Well, for the same reason, it's 0.1 because it's 1/10. This time the intervals are shorter, so the probability that it lies between that interval is smaller. So what you can notice here is that the height of the towers doesn't change at all, but their width was halved, and therefore the probabilities have also been halved. This is because now we're not looking just at heights, but at actual areas, and the base is no longer 1. So now we can't think of heights of towers. Instead, we need to think about areas. Now let's return to the previous example of the call center, where the calls are not equally likely to be of the same length. Now, the call is more likely between 1 and 2 minutes, or between 2 and 3, and not so likely to be between 4 and 5 minutes. So what's the probability that the call lasts between 1 and 2 minutes? Well, it's this area over here. And the probability that it lasts between 1 and 1 minute 30 is this area over here. Now, if I have the areas much more granular like this, what's the probability that's between 2 and 3 minutes? Well, it's going to be the sum of all the shaded areas between 2 and 3 minutes. So we're getting to the continuous distribution. What is the probability that the call lasts between 1 and 2 minutes? Well, now it's going to be this area over here. If we were interested in the probability that the call is exactly 2 minutes, then we'd be talking about the area of this segment over here. That is a line segment and it has no area. So that's why we say that that probability is 0. So now we can only think of probabilities between different windows of time, no longer one particular time. So to recap, as we divide the intervals into smaller and smaller, also the areas get smaller and smaller until they get to 0. So that's why we have to look into intervals and not just heights. So as I told you before, this function is called the probability density function, or PDF for short, and it's usually denoted as a lowercase f. It is the equivalent of the lowercase p in the discrete distribution. The equivalent of the mass function is now it's called probability density function. And for added clarity, you can add a subscript of the variable is representing. That's the capital X. PDFs are a function defined only for continuous variables, and it represents the rate at which you accumulate probability around each point. You can use the PDF to calculate probabilities. How do you do that? Simply by getting the area under the PDF curve between points A and B. Now, what does a function need to satisfy in order to be considered a PDF? Well, first, it needs to be defined for all the numbers in the real line. That means that it can actually be 0 for many values. For example, before 0 or after the cutoff at the right, but it doesn't need to. It could be positive for all the numbers and the area still being 1 if it gets really tiny at the tails. And it also needs to be positive or 0 for all values. This is reasonable because otherwise it would get placed in negative probabilities, and you know that probabilities cannot be negative. And finally, the area under the curve has to be 1. Again, this restriction comes from the probabilities. The area under the curve is simply the probability of all possible outcomes of the variable, and it always needs to add to 1. So here's a small summary. Let's take a look at discrete random variables, and remember that they can only take a finite or at most a countable number of values, while continuous random variables are used to model experiments where the outcome can take any value in an interval. Because of this difference between discrete and continuous random variables, each kind will have their own way of describing the behavior and computing probabilities. To measure the probability of events, in the case of a discrete random variable, you have a probability mass function, which is defined as the probability that x takes on a particular value. For the continuous random variable, you have the probability density function. And remember that for this type of variable, the probability that the variable takes on a particular value is always 0. So you need to look at areas on this side. So now that you've learned the probability mass function for discrete distributions and the probability density function for continuous distributions, let me show you what the cumulative distribution function is. Let's look at the example of the phone call. In this example, you actually had to calculate areas underneath a curve in order to find the probability that a call is between, let's say, 2 and 3 minutes. This is not convenient. We don't want to be always calculating areas. The cumulative distribution function is one that shows the actual probability that the call is between 0 and a certain number of minutes. So it's just much more convenient to calculate. There's also a cumulative distribution function for discrete distributions. So let me show you more about it. So let's have a look at another concept, and it's the cumulative probability. Cumulative probability tells you what is the probability that an event happened before some reference point. For example, let's return to the call center and let's start thinking about the discrete simplification of the problem. So the one where we looked at the probabilities being between 0 and 1 minute, 1 and 2, all the way to between 4 and 5 minutes. And then as usual, we'll slowly move to the continuous one. But for now, let's look at this one. Now, let's take a look on the right at what's called the cumulative probability. So the probability that the call is between 0 and 1 minute. And that's exactly the same as the one in the left, because that first little rectangle is the probability that the call is between 0 and 1 minute. Now, let's look at the probability that the call is between 0 and 2 minutes. What do you think that is? Well, on the left, it's going to be the sum of these two areas. And the reason is because being between 0 and 1 minute is the same as being between 0 and 1 or 1 and 2. So we're adding those two areas. And on the right, we're going to get this. So remember, on the right, we're looking at the probability being between 0 and 1, then between 0 and 2. The next one is between 0 and 3. So between 0 and 3 is the sum of these three areas. So we plot them here. Then between 0 and 4, the sum of these areas. And then finally between 0 and 5, which is all the areas. And obviously we know that this is 1, because the probability that the call is between 0 and 5 minutes is 1. And now we can draw the cumulative probability for this discrete distribution to the left. and it's this red curve over here. Notice two things. It always starts at 0. For example, it is clear where 0 should be. There are no calls that take negative time. In general, the cumulative distribution is 0 up to the point where we expect no outcomes at all. And secondly, the value at the very right is 1, because we know that all the calls will be 5 minutes or less, so the probability that the call is between 0 and 5 minutes is 1. This cumulative distribution function always starts at 0 and ends at 1. So for continuous distributions, we have something very similar. You go over the PDF from the beginning until the end, and you simply add up the pieces to create the CDF curve. Except in the continuous case, you're not adding together the heights of the bars, but you're plotting the sum of the area under the curve. It's the same as the discrete case. The point at the very left is 0, because you haven't added any area. The point at the very right is 1, because that's where you've added all the area. Now, this is a particular case where the curve starts and ends at finite points, but the blue curve in the left, the density function, could go infinitely to the left or infinitely to the right, in which case so does the other curve, and that means that it has a limit at 0 to the left and a limit of 1 to the right. And finally, at some point x, this area, this black area over here, it's going to be this height over here. So for example, the probability that the call is less than or equal to 2 minutes, let's say it's 1/2, then on the right we have that the height at the point x, at the point 2, is 1/2, because that's the probability that the call is less than or equal to 2 minutes. So in other words, these two curves give us the same information except written different. On the left, we have to calculate areas to find probabilities, and on the right, we simply have to look at heights. So far you've got a pretty good intuition about the cumulative distribution function. So let's look at some notation and some formalism. The CDF is a function that tells you how much probability a random variable accumulates up to a certain value. So the CDF is actually the probability that a random variable x is smaller than or equal to some value x. This is defined for each and every value on the real line from -infinity to +infinity. This function is normally denoted with a capital F. Please be mindful not to use lowercase f, because that's the one reserved for the probability density functions of continuous distributions. So exactly as with PDFs, we add a subscript with the random variable for extra clarity. In this case, it's capital X. If your variable was called capital Y, for example, then you would call the cumulative distribution function f sub capital Y. So notice that if your variable is discrete, like the one on the left, then the CDF will have jumps. Why does this happen? Well, consider this point over here in the CDF where the function planks. This means that this particular point is not a possible outcome of the variable you're modeling, so it doesn't accumulate any probability. However, at the values that are a possible outcome, you see a jump in the CDF. The height of that jump is exactly the probability that the variable has taken on that particular value. For continuous variable, the CDF shape changes a lot and you get a continuous function. Why is this? Because each point doesn't have probability mass on its own, and once you don't have points with mass, then you don't see any jumps, so the CDF curve is smooth. Now, what properties does the CDF need to satisfy? First, since by definition it's a probability, all values have to be between 0 and 1. Also, at the left point of the CDF needs to be 0. In some cases it's a fixed number, in some cases it's a -infinity, but nonetheless it has to be 0. The right endpoint, where all the probability has been accumulated, the CDF has to be 1. Finally, the CDF can never decrease. Since it's accumulating probabilities and probabilities can never be negative, then this is a must. So to really summarize, on the left you have a PDF, which is written as a function f of x, let's say, and it's a function that's always positive and has a total area of 1 underneath the curve. And the CDF has a left endpoint of 0, a right endpoint of 1, and it's always positive and it's always increasing. So sometimes you're going to be using the PDF and some other times you're going to be using the CDF, depending on which one's more convenient at the moment, but it's good to know both really well. To help you better understand the relationship between the probability mass or density functions and the cumulative distribution function, after this, you'll find another interactive tool. You'll be able to choose different PMFs or PDFs and simulate results from each type of sample. Afterwards, you'll be able to generate the CDF for the distribution you've chosen. Spend some time exploring the tool, and once you're done,
move on to the next set of videos.
So now you're ready to learn the simplest continuous distribution of all, which is the uniform distribution. I like to imagine it as a bus. For example, let's say that a bus passes every 10 minutes, but I don't know the schedule, so I just walk outside and wait for the bus. What do you think happens with all the values of the times I wait for the bus? Sometimes I take 1 minute, sometimes 5, 9, 7, 4.5, 3.52, etc. And when you look at all these numbers, they're pretty homogeneous in the interval from 0 to 10 minutes. That's how a uniform distribution looks like. Let me elaborate.
So imagine again the example of a support call center. Previously we've looked at some different histograms of probability of their answer at different times. Now let's name some of these examples and start with the uniform distribution. Imagine that the call center can answer in any time from 0 to 15 minutes with equal probability, and if they don't answer within 15 minutes, the call is disconnected. The last 200 times you called them, you made a note of how much time you had to wait. And notice that the points seem to be more or less equally distributed over the y-axis. That means that there is no particular wait time or window of wait times that seems to appear more times than the rest. In fact, this is what the histogram looks like. While it seems that one of the bars is slightly taller than the rest, let's not forget that this is based on measurements, so some deviation is expected. Call t the time in minutes that you have to wait. And any value between 0 and 15 should have roughly the same frequency of occurrence. Which means that the PDF must be constant on the interval 0-15, so no value is favored over the others. The question is, which is the constant? Well, remember that the area over the curve of the density must be 1. So that times 15, which is the length of the interval, must be 1, and therefore the height is 1 over 15, or 0.06. And we can draw it over here. In general, a continuous variable is said to follow a continuous distribution if all possible values have the same frequency of occurrence. It has two parameters which are associated to the interval where the variable can take values. A is the beginning of the interval and B will be the end of it. And the probability density function will be then 1 over b minus a, which is 1 over the length of the interval, since the interval has length b minus a as it goes from a to b, and it's 0 otherwise. So it is that orange line that is always 0, except it's 1 over b minus a at the points between a and b. This animation shows what happens when we change the parameters, more specifically the starting and ending point. You can see that when the interval AB is bigger, then the PDF is smaller, the height of the PDF is smaller, and it quickly increases as the interval gets short. Now let's see what the CDF looks like, and let's take a simple example, the uniform distribution between 0 and 1. But you can see that this applies to the uniform distribution between A and B just by changing the parameters a little bit. So first let's start by considering some x less than 0. In this case, the area under the PDF until that point, from the left until that point x, is 0. Therefore, for any value that is less than 0, the CDF is 0. Now take any x between 0 and 1. The probability of the variable being smaller than a particular x is this area over here. Since it's a rectangle, you need to multiply the length of the base, which is x, by the height, which is 1. So at that point, the CDF is x over 1, which is the same as x. And the same is valid for any x between 0 and 1. So the CDF is this line here with slope 1. And finally, if you take any x bigger than 1, you've already gathered all the area under the PDF, so the probability stays as 1. So this is how the CDF looks. A straight line followed by a diagonal and then followed by a straight line. And the one on the left is at 0 and the one on the right is at 1. For the general uniform distribution between A and B, you can see that the CDF is the ratio between the length of the segment AX and the length between the extreme values A and B, for values of x between A and B. For x less than A, you have 0 accumulated probability, and again, for x bigger than B, you've already gathered all the probability, so therefore the CDF is 1 after that point.
So now let me tell you about one of the most popular distributions out there. It's called the normal distribution, also named Gaussian distribution, after famous mathematician Carl Gauss. The normal distribution appears everywhere. In statistics, in science, in real life, and obviously in machine learning it appears all over the place. Let me show you.
So now let me show you one of the most used distributions in ML, the Gaussian or normal distribution. But let me give you a little bit of intuition first. Remember in the previous videos you learned about the binomial distribution, which counted, for example, the number of heads in n coin tosses. And the probability mass function looked like this, for example, for 2 throws. Now, let's see what happens as n, the number of throws, gets larger and larger and larger. Let's plot it for all numbers all the way to n equals 100. And you can notice that it looks like a bell curve. So a continuous bell shape fits pretty well. And that bell curve, that orange curve, is what we called the normal or Gaussian distribution, named after the very famous Carl Friedrich Gauss. So this means that when n is very large, the binomial distribution can be approximated by a Gaussian distribution pretty well. Now let me tell you more about this Gaussian distribution. So let's say that the data looks like this, like a bell curve. We're going to try to fit it with some curve. And the curve e to the negative x squared over 2 seems to work pretty well because it seems to look like this, like a bell curve. However, we need to adjust it a little bit. Let's look at where the blue data is centered. It's centered at 2. We're going to call it mu for the mean. And we're going to learn these mean more in detail in the next week. But for now, let's just think of it as the center of the data. The orange curve has this point 0 as the center because it's symmetric over the x-axis. So we need to move it to the right. And how do we move it to the right? Well, by subtracting 2. So that moves it to the right, and now they're equally centered. However, the orange one is a little too skinny for the blue one. It needs to be widened a bit. There's something called a standard deviation that we're going to learn next week, but that tells us how thick the curve is. And the orange one has a standard deviation of 1, and the blue one of, let's say, 3. So what we need to do is to thicken the orange curve. And the way we thicken this curve is by dividing the exponent by 3. That gives it the right thickness. Now, another problem we have is that the orange curve is different height than the blue one. It's actually too high. And more specifically, the area is not the same. The area under the blue curve is 1 because it's a probability distribution. And the area under the orange curve is much higher. So what is it? Well, for these numbers, it's actually 3 times square root of 2 pi. So we need to divide by this number in order to get the right curve. And notice that now it fits it really, really well. So that's the formula for the Gaussian or normal distribution. So it has some parameters, as you saw. The mean, so that's the center, the average of the data, is mu. The standard deviation, which we're going to learn next week, but as I told you, it's a measure of the wideness of the curve. It's a number called sigma. And if you want the mean to be mu and the standard deviation to be sigma, those are the two parameters, then the equation of the Gaussian or the normal distribution is exactly this one over here. And mu is the place where the data is centered, and sigma is a measure of the wideness, as I said before. Now let me give you a small recap because this is a very important distribution. So mu is the center and sigma is the spread. And the curve is obviously symmetrical and the range is all the real numbers. So it actually is one example of a distribution which its probability density function is always positive, although it's very, very, very small for big and for negative big numbers. And the formula is this one over here. This part over here is simply a scaling constant. And here are some different normal distributions for different means and different sigmas. So if you have a random variable x with this probability density function, you can write it like this. X is distributed as n of mu sigma squared. N stands for normal and mu stands for the mean or the center of the bell. Notice that in this notation, the standard way to describe the distribution is using sigma squared rather than sigma, which is the square of the spread. As you will learn in the next lesson, this is called the variance. Don't worry too much about this change, as both sigma and sigma squared convey exactly the same information. Because sigma has to be positive, then there is a 1-to-1 relation between the two parameters. There's one particular set of parameters of great importance, and they are mu equals 0 and sigma equals 1. When a distribution has these parameters, it's called the standard normal distribution. Notice that the resulting bell-shaped curve is centered at mu equals 0, and it's symmetric with respect to this axis. Now let's take a look at the density function fx. When we plug in the value for mu equals 0 and sigma equals 1, the simplified formula makes calculations much easier. There's a really easy way to convert any normal distribution to the standard one, and it's by doing some small operations. So let's say that x has a normal distribution with parameters mu equals 2 and sigma equals 2.5. So the first thing we do is, instead of x, consider x minus 2, and that moves it all the way to the center. And now let's divide by the standard deviation by sigma. So x minus 2 divided by 2.5 actually puts it off the right height and the right width, and it makes it the standard normal with parameters 0, 1. We're normally going to want parameters 0, 1. 0 is the mean and 1 is the standard deviation. And so we're not going to look at x, we're going to look at set equals x minus mu divided by sigma. Standardization is crucial in statistics because it helps us compare variables of different magnitudes. So if one variable, for example, moves in some range of values and another variable moves in a completely different range of values, then we can compare them by standardizing both of them. Now let's see what the CDF looks like. It looks like this. As usual, it starts at 0 on the very left, which is now the point at infinity, and ends at 1 at the very right, which is the point at plus infinity. But here's a catch. This area is actually really hard to compute. It can be computed analytically. So what do we do to compute these areas? Well, in the old days, there were big tables of data that people used to look at. Now you can use the help of some software to do the approximate area under the curve for you. And what are some things that can be modeled using the normal distribution? Well, that's the great thing about it. So many things in nature are modeled by the normal distribution. Height is modeled by the normal distribution. Weight, IQ, things like noise in a communication channel, and in general, variables can be modeled as a sum of many independent processes always follow normal distribution. So we're going to see that in more detail later. Also, many machine learning models assume variables follow a normal distribution, so beware of that when choosing appropriate models. So imagine that you're transmitting bits between two antennae. You send the message 10010. The message travels through the air, which in this case is the communication channel. The channel has noise, which will affect the message you send. This noise can come from different sources, like interference from our devices. Think of a Wi-Fi router, obstructions like walls, trees, buildings, etc. And conditions like rain or high humidity may also affect your signal. Also, electrical interference, for example, from nearby power lines, and many other factors can influence what actually gets received. So in fact, let's say you receive the message 10010 plus some noise that affected the signal, and let's call the noise Z, which has a random nature. One common assumption in communication is that the noise Z has a Gaussian distribution with mean mu equals 0. One measure that is very useful in communications is the noise power, which is roughly modeled by the square of the noise. This measure is important because it is associated with the variance or dispersion of the noise and will determine how hard it is to correctly interpret the received signal. The big question is now, what is the distribution of W? So for simplicity, we're going to assume that Z follows the standard normal distribution with parameters 0 and 1. So let's try to see it graphically. Each value of W can be achieved with two different values of Z, which are negative square root of W and square root of W. Even more, the probability that capital W is less than W is the area under the PDF curve of the Gaussian between these two numbers. So you can get the CDF for W by finding these areas for each possible value W. Notice that for small values of W, you gain area at a much quicker rate. This is because the Gaussian distribution concentrates probability around 0. This is known as the chi-squared distribution with 1 degree of freedom. Now, since the CDF is the integral of the PDF, then you can easily find the PDF by taking the derivative of the CDF. So this is simply the slope of the CDF at each point. Now, you can easily see that the rate at which the probability is accumulated is big for small values of W and it gets smaller and smaller as w increases. And the reason is that for small values of w, this is a very steep curve that grows really quickly, but for larger and larger values, it grows slower and slower. Now, what if we want the noise power accumulated over two transmissions? That means that the power is now z1 squared plus z2 squared, where both of them are normally distributed. That is the chi-square distribution with 2 degrees of freedom. What about the power accumulated over 5 transmissions? That is going to be z1 squared plus all the way to z5 squared, and that is a chi-square distribution with 5 degrees of freedom. And what about the power over k transmissions? Well, notice that, again, this is the sum of many independent standard normal variables squared, and is said to follow a chi-square distribution with k degrees of freedom. And notice that as k increases, the PDF is more spread and becomes more and more symmetrical.
So imagine that you have a dataset, for example, heights of people, but you need it to be larger, but you can't go and collect more data, it's too expensive. So what can you do? Well, you can create some synthetic data that looks a lot like the original one. And a way to do this is to construct a distribution out of this data and then sample out of it. And by sampling, I mean picking points that have the probabilities given by the original distribution. So this is a very important concept in probability and in machine learning. Sampling from a distribution. Let me show you.
Let's say you have a simple discrete distribution over colors with 3 possible outcomes: green, blue, and orange. And you get green with probability 0.3, blue with probability 0.5, and orange with probability 0.2. And now you want to run an experiment where you want to create a random sample of data that follows this distribution. So how do you sample data from this distribution? Well, as you know, the probabilities of the outcomes add to 1, so you can stack them up together like this to get a continuous strip between 0 and 1. Now, computers can choose a random number from a given interval uniformly. So to simulate this distribution, you need to follow 3 steps. First, generate a random number between 0 and 1. Second, find out which of the 3 intervals the generated number belongs to. And then third, assign the correct color based on the interval. That will help you pick a random color between green, blue, and orange with the probabilities that are given in this graph. Now, let's say that instead of green, blue, and orange, you assign these outcomes some numbers. Let's say 0, 1, and 2. The process will be exactly the same. So let's take a look at another way to solve this problem. Let's create another plot here where we simply rotated the bars, and what we're going to do is we're going to push them to the right and draw that red line, which is actually the cumulative distribution function. And now all you have to do is you sample uniformly from the vertical interval. So these 4 points are sampled uniformly, and then you simply read out what the value is in the horizontal axis of the cumulative distribution function, and then you are picking the numbers according to the distribution on the left. We can also do this for a continuous one, and it's actually very beautiful. Check it out. When you have, let's say, the Gaussian distribution on the left, you want to pick randomly from this distribution. It's not easy because calculating areas is hard. But if you take a look at the CDF on the right, and then you pick uniformly from that gray interval, the interval from 0 to 1, that's vertical, let's say we pick some numbers here uniformly. And now all we do is we take a look at where this hits the distribution and where it hits the horizontal axis. So these points over here are actually distributed based on the normal distribution on the left. As you can see, this is the distribution that these points are taken from, and when you look at them on the left, that's the exact distribution that they're taken from. So the CDF, both for the discrete and the continuous case, is a very useful method when you want to sample from a particular distribution. To give you a solid foundation in applied statistics, this course includes 5 exploratory data analysis labs. You'll get a chance to get hands-on with some data and see how concepts from probability and statistics can help find patterns and make decisions. These labs are ungraded, but there are many suggested activities for you in each of them. This week you'll have 2 labs from that series. The first one is an introduction to pandas, which is a widely used Python library for analyzing data. This lab is focused on introducing you to the tools from pandas you'll use throughout the other 4 labs, but you'll get a first look at a dataset on world happiness you'll see later in the course. If you're already familiar with pandas, feel free to skim this lab. The second lab will get you applying some of the concepts you've learned here in week 1 to analyze and visualize data and describe some of its key features. This lab introduces a dataset on rideshare from the city of Chicago that you'll also see later in the course. I hope you enjoy both labs. Afterwards, you'll have the graded portions from this week. First, you'll find a graded quiz covering all the topics of this week. Finally, you will have a graded programming assignment in which you apply Bayes' theorem in order to predict whether an email is spam. The assignment will help reinforce much of what you've been studying about Bayes' theorem and conditional probability. It's also just a great opportunity to see how powerful some of the concepts you've been studying can be when applied cleverly to a real-world problem. You've got your work cut out for you, but I know you can do it. Good luck finishing out this week.
Welcome to week 2. In the first week, you learn about probability distributions. This week, you're going to learn about some ways for describing the data and these probability distributions. You're going to see how mean, median, and mode describe the center of the distribution, and how variance describes the spread of the distributions. You will also be introduced to the concept of an expected value. You're going to see that expected values can be used to describe some interesting properties of variance, as well as some advanced properties of probability distributions, such as skewness and kurtosis. So far, you've seen probability distributions of one random variable, but in lesson 2 of this week, you're going to learn probability distributions of more than one random variable. Some concepts you'll learn are joint distribution, marginal distribution, conditional distributions, and covariance. These are very useful to describe probability distributions in multiple variables. So let's get started.
In this video, we're going to cover a topic that you may already be familiar with, and it's the mean. This video will be a quick review of the topic, a formalization of how it's thought about in statistics, and then an application to some of the distributions you've studied. Let's look again at the example where you looked at a sample of kids of different ages. You have 3 kids of age 0, 2 kids of age 1, 4 kids of age 2, and 1 kid of age 3. What is the mean of the distribution? Before looking at the mathematical meaning of this concept, let's look at an intuitive meaning, the point where this distribution would balance. To help, I'm going to replace each kid with a ball. Now that I have just a bunch of equally sized balls, you can put them on the scale and find a tipping point. By trial and error, you can find that the scale would balance somewhere here. And this is a value of 1.3. Now let's try to calculate this number. You probably know that the way to calculate the mean is to sum all the kids' ages and divide by the number of kids. This way you get the average of kids, and that's exactly the point where you have to balance your scale. So you have 3 kids of age 0, 2 kids of age 1, 4 kids of age 2, and 1 kid of age 3. And then you divide this by 10, because there are 10 kids in total. This sums up to 13 over 10, which equals 1.3. And that is the average age of a kid in this distribution, and also the mean. Now look at how you can rewrite the equation above. On the top, you have 3 times 0 plus 2 times 1 plus 4 times 2 plus 1 times 3, and all this is divided by 10. Now let's distribute that 10 into the denominator of every term to get something like this. The new equation looks a lot like probabilities, right? You have 3 over 10 probability at the age is 0, 2 over 10 probability at the age is 1, and so on. Of course, the result is still 1.3, since all I did was rewrite the original equation. Written this way, however, it's easier to see that this equation is the weighted average of the values of the variable, where the weights are the probabilities of each possible value. This balancing point is the mean of the dataset. There's another more formal name for it used in probability, and that's expected value. So when you see the word mean or expected value, know you are referring to the same concept. In this context, the expected age of a kid is 1.3 years. If x is the variable representing the age of a child, then the expected value is written like this, and it's read as e of x. Let's look at another example where this concept of expected value can be useful. This time, imagine you play a game with a friend where you flip a coin, and if you get heads, you get $10, otherwise you get nothing. And let's assume that this is a perfectly fair coin, so 50-50 chance. Now your friend wants you to pay $6 every time you play the game. Would you play the game at this price? What about if they want to pay you $4 to play this game? Would you play the game then? So what would be the maximum you would pay to play this game? So how can you figure this out? What is a fair price to pay for the game? You can think of this in terms of probabilities, or you can think what is likely to happen in the long term, and it's actually the same calculation as you just did with the kids. So in the long term, you expect to get half of the times $10 and half of the times $0, which gives you $5. And this is your expected payoff. If you imagine the game is a random variable x, then this is actually e of x, the expected value.
and the calculation you just performed is the same weighted average you calculated when finding the mean age of the kids. Since 5 is the expected payout for the game, this is also the highest amount you would be willing to pay to play the game. At least at that price on average, you would break even. Ideally, you could pay less, and you should not agree to pay more. You can also see the expected value in this plot. The point where you would balance this on a scale is exactly at 5, as you have already calculated. And so visually, you can see the expected value as the point that balances the distribution. Now let's think about another game, where you flip 3 coins and you win $1 for each heads. What is the maximum amount of money you would pay in this case? Now you have seen this one before. You can arrange the possibilities by the number of heads and create a histogram. Now you can put it on a scale and try to find a point where it's balanced, which is at 1.5. So the expected number of heads is 1.5. You can also think of this problem differently. You flip 3 coins and half of them are heads. What is half of 3? It is 1.5, which is the result you already have. Finally, you can use the weighted average definition to find the same value. 1/8 times 0 plus 3/8 times 1 plus 3/8 times 2 plus 1/8 times 3 will again give you an expected value of 1.5. So in general, if you have a discrete random variable x, it will have a probability mass function that provides the probability of each possible x can take. The expected value will be x times the probability of x summed over all possible values of x. This is just more formal notation for the weighted average formula you've seen in the previous examples. Since you're performing a weighted average of the values the variable can take, if every value on your data has the same probability or mass, then the expected value will be right in the middle, which in this example is 3. However, as soon as one of the values has more weight than the others, it will shift the equilibrium point towards it, in this case giving an expected value or mean of 2.3. Notice that to increase the probability of 1, you had to also lower all the other probabilities, because as you might remember, the sum of all the probabilities has to be 1. So you can't just increase one probability without having to adjust the other ones. So far, we've been looking at discrete random variables. Now let's see what the expected value or mean of a continuous random variable looks like. Recall the phone center example from the previous videos. When you have a sample of data, in order to find the mean, you can imagine that each of these bars on the plot has its own weight, and all you need to do is balance them on a scale, just like you balanced the balls in the previous video. For this case, it balances somewhere around here, and this is exactly where the mean of your sample is. Now, we can again go towards continuous distributions, just like we did in the previous week. You can always talk about the distribution in your sample more precisely, and you can break down the intervals into smaller ones. For finding a mean, this makes no difference. You still just have to balance the left and the right side. If you keep going until you reach infinitesimally narrow bars, you get a continuous distribution. Instead of balancing bars, now you have a continuous shape, which you still need to balance. For discrete random variables, you saw the expression for the expected value. You sum over all possible values of the random variable, weighted by the value of the probability mass function, making it a weighted average. What happens with continuous random variables? Well, there's actually a formula that looks a lot like the one on the left, and it involves using integrals. If you're familiar with integrals, I will show you the expression here, but since this specialization didn't teach integral calculus, don't worry. I won't expect you to know it in this course. With that said, the symbolic expression here is very similar to the expression for discrete random variables. The idea behind integrals is that you are summing the area of bars that get thinner and thinner, so that in the limit you are adding an infinite number of very narrow bars. Even still, all you're calculating is a weighted average. In both cases, you are summing up all the possible values of x, but in the discrete case, you weight the sum using the probability mass function, and in the continuous case, you are using the probability density function. Let's see what the expected value for a continuous distribution looks like by considering this example. Let's say you're taking the bus every day, and you look at how much time the bus takes to arrive. Let's say the first time it took 15 minutes, and so I'm going to plot this number here. You continue collecting data points because you take the bus every single day. You take it on the next day, and it took, let's say, 32 minutes. You keep recording every day, and you keep collecting these data points. Now you want to find the average of these numbers, because you want to find the average time that you spend waiting for the bus. The average of these numbers is 27.833, and that's where you balance these points over. Now you can continue collecting data points every single day that you take the bus, and now you get something like this. And you're expecting that if you're not really planning to take the bus at any particular time, and let's say it arrives every hour, then roughly you're going to get a uniform distribution. And the average is going to be somewhere around 30. Why 30? because the distribution for the time that you spend waiting for the bus is uniform, because as you can see, the point can land pretty much anywhere in that interval equally. Where would you balance a uniform distribution between 0 and 1? You would balance it in the very middle at 0.5. For a uniform distribution between a and b, then you're balancing it in the middle, which is the point a plus b divided by 2. Now let's look at the expected value for a less well-behaved continuous distribution. Again, considering the wait times on the phone. Let's say you call, and this is how long you need to wait for the first call. If you make more calls and record how long you wait, you would expect a dataset that looks like this, with relatively more dots where the probability density function is higher and fewer where the curve is lower. Where is the expected value of this distribution? Well, again, it would be the mean point, and it would show up somewhere around here. This is visually the point on which you can balance this distribution without worrying about the calculus needed to calculate it. You can just think of it as the weighted average of the blue probability density function. Now here's a common misconception. It might seem natural to think that the mean is a place where the data is split in half, but that's generally not the case. Notice that 50% of the data is here, and the other 50% is here, and the mean point is not in the middle. This point is actually called the median, and you'll learn more about it in the next video. The mean is actually here, and notice that if you split the distribution of the mean, there is more orange area than there is yellow area. That is okay. The reason is that even though we have more mass here it's more spread out. I like to imagine this with an extreme example. Let's say that I have an elephant really close to the balancing point, and a mouse that is many kilometers away. Well, because the mouse is so far, even though it's much smaller and lighter, it still balances the weight of the elephant, even though the elephant has more mass. The mouse is much farther away. If you like physics, this is the concept of torque, which is force times length. To summarize about expected value, if you have a random variable x, then the expected value is written as e of x. It is the mean of that probability distribution and can be thought of visually as the balancing point of that distribution. Expected value is defined for both discrete and continuous random variables, and you can think of it as the weighted average of either the PMF or the PDF of your random variable, depending on whether the variable is discrete or continuous. In the last video, you learned about the expected value or mean of a random variable. The mean is not the only way to measure the center of a distribution, however, and that is important because there are other ways to measure what are the central or typical values for a probability distribution. In this video, you will learn about 2 more measures of central tendency and why they're important. So you've seen the mean before, but let me show you an example where the mean may not work so well. In the 1980s, the starting salary for a geography graduate at the University of North Carolina was actually $250,000. Sounds like a very big salary, especially considering that for the rest of the United States, the starting salary for a geography graduate was $22,000. So why do you think this happened? Well, it could have been that the program was excellent, although I'm sure there were other excellent programs too, so that may not be it. Could have been that the university had great connections, but I'm sure other universities also had great connections, so maybe that's not it. Or perhaps it was that one student made a lot of money, and that was indeed the case. Michael Jordan graduated from the geography program at the University of North Carolina in the 80s, and he went out and made a lot of money, and he brought the average up for everybody. So it's not really that the average student was making a lot of money, it's that he was making so much money that it looked like they were all making money. But the average here is a little deceiving. And here's a plot that shows us why the average is deceiving. So imagine that this is the histogram of the salaries. So salary is in the horizontal axis and the number of students with that salary in the vertical axis. And if you were to balance it, it goes over here at around $22,000. However, Michael Jordan is all the way here. And then what happens? He tips the scale, and in order to balance it, we have to move it up. So he brings the average up for everybody, and the average is no longer measuring what the average student makes. It got skewed by that one point on the right. So how can we fix that? Well, let's consider a different metric. Let's actually put them all in order by salary. So now it's just the position that matters. And once we do that, we can pick the number in the very middle. So the salary in the very middle is the median. And notice that that is no longer so high because now Michael Jordan doesn't contribute a lot of money
he just contributes 1% to this list. That is the median. Now, if the median were to be in the middle because you have an even number of points, then you simply take the average of the 2 points in the middle. So the moral here is when the average is deceiving, go for the median and you may get a better idea of your data. There's one more way to describe the center of a distribution apart from the mean and the median, and it's called the mode. Remember a call center example where the probability that the operator picks up the phone in a given time looks something like this? Mode is simply the value at which the distribution has the highest probability, which makes it the most frequent one. For example, in this case, it's this number over here. You can see that it's the outcome with the highest probability. And the same thing happens here in the more granular discrete distribution. It's the point where the tower is the highest. And for a continuous distribution, the mode is simply the value that has the highest height. Now, the mode may not be unique. You may be in a distribution like this where the maximum value gets repeated many times, and that's called a multimodal distribution. And in places like the uniform distribution, for example, everything is a mode. So in summary, you have the mean, the median, and the mode, and it's always good to look at the three of them in order to really see where the center of your data is. Now let's look at a real example, the binomial distribution. Here you see an example of 5 trials with the probability of 1/2, like flipping 5 fair coins. What does this mean? Well, remember that we used a scale to balance distribution? In the scale of distribution, it's pretty simple to find the balance and it's perfectly symmetric. It's over here. The mean is at a value of 2.5. Now, what about the median? Well, same thing. It's the average of 2 values in the middle because we have an even number of values. So it's also 2.5. And what about the modes? Well, the highest points in the distribution are 2 and 3, so the modes are 2 and 3. Now let's look at an asymmetric normal distribution. So we'll flip a coin 5 times, and this time the probability of heads is 0.3. So you're going to balance it on a scale and find out that it's here at 1.5, so that is the mean. As the blue line shows, median is where half of the data is to the right and half of the data to the left, so that one is over here. And mode is again the outcome with the highest probability, so it's going to be 1. Now let's look at a continuous example, the normal distribution. What's the mean? Well, the mean is the center because that's where you would balance the distribution as it's perfectly symmetrical. What about the median? Well, the median is also that point in the middle, and the mode is also that point in the middle, which is the highest one. So for a normal distribution, they all match.
You have now learned how to find the expected value of a random variable. But what if you were looking for something different? Perhaps the expected value of the square of this variable, or the cubed, or any other function. Let me show you how.
So imagine you have this probability distribution and you get the outcome x1 with probability px1, then you get the outcome x2 with the probability p of x2, then the outcome x3 with the probability p of x3, and finally the outcome x4 with the probability p of x4. Now, how do you find the expected value of the outcome? To find the expected value, you have to simply take each outcome and multiply by its probability and then sum over all outcomes. So you start with x1 times p of x1, then add x2 times p of x2, and then all the others. Now, what if you're interested in some function of x, for example, the expected value of x squared or x cubed? Well, luckily it turns out the result is very similar. So if you're interested in the expected value of g of x, you need to do a similar summation as before, but now you multiply g of x by the probability of x each time. So you start with gx1 times p of x1, then add g of x2 times p of x2, and all the others. Now this may look like a lot, but it's actually very simple. You just replace the x with g of x, and you kept the probability the same. Now let's look at an example. Imagine a game you play with a friend. You roll a dice and your friend gives you the square of the amount you roll. What is the fair price to pay for this game? To answer this question, you can do the same as you did in the previous videos. You can plot the distribution of your payoffs and try to balance it on a scale. And to calculate where the scale should be balanced, you can simply take the average of these numbers, which is 91 divided by 6. So looking at the squares of numbers is nothing harder. You just need to think a bit about how to transform it into a problem you already know. Now look at what you've actually done.
You have summed the squares of the rolls times the probability of each roll, which is 1/6. So you have actually calculated the expected value of x squared. Imagine now that your friend changes the game and now they will pay you 2 times the number you roll on the dice. In order to get in on the game, you need to pay up $5. So at the end of the game, you will have 2 times the number you rolled minus the $5 you gave to start the game. Which means your wins are -3, -2, -1, 0, 1, and 2. A negative win means that you lost money. How much will you win with this game on average? Once again, to answer this question, you can do the same thing you did in the previous videos. You can plot the distribution of your payoffs and try to balance it on a scale and calculate where the scale should be balanced. Because each of the 6 values happens with probability 1/6, you can simply take the average of these numbers, which is -3/6 or -0.5. Now remember that each value was obtained by doing 2 times the value you rolled minus the $5 you started with. You can see that you have 6 times -5, which you can group together. But 6 times -5 divided by 6 is simply -5. Finally, note that you have a common factor of 2 in all the sums, so that you can rewrite the expression this way. Now 1 plus 2 plus 3 plus 4 plus 5 plus 6 divided by 6 is simply the mean or expected value of a dice roll. Notice anything cool here? It turns out that the expected value of 2 times x plus -5 is 2 times the expected value of x plus -5. In general, no matter the distribution of x, it is true that the expected value of a times x plus b is a times the expected value of x plus b. This means that the expectation is a linear operator. You can have 2 more takeaways from this general result. First, expectation of a times x equals a times the expectation of x. But also, the expected value of a constant is the constant itself. So imagine a game where you can do 2 things. First, you flip a coin, and if it lands on heads, you win $1, and otherwise you win nothing. And then, after you flip the coin, you roll a die, and you win the amount that you rolled. So here's a question. What is the expected amount that you win for this game? Well, for the coin toss, the expected value, we're going to call this variable x sub coin, is 1/2, as you saw before, because with a half probability you win 1, with half probability you win 0. So each time you play, you're winning on average $0.50. And for the second game, it's 3.5 because that's the average of all these numbers. We're going to call x dice the result of the second game. And e of x, which is the result of both games at the same time, is going to be the sum of the expectations of the coin game and the dice game. So it's going to be 50 cents plus $3.50, which is $4. And in general, if you have 2 variables and you add them, the expectation of the sum of the variables is equal to the sum of the expectations. Now, the sum of the expectations may be something that seems very trivial, but actually it can get us to some pretty non-trivial results. Let's look at the following game. You have a bunch of names corresponding to all the people in the world. So since there's 8 billion people, you have 8 billion names in a bag. And imagine that these are unique names. Everybody has name and last name and just enough identifiers that each little piece of paper corresponds to one person and only one person in the world. Now, I'm going to travel around the world and grab out of this bag one little piece of paper and give it to each person in the world. What is the expected number of correct assignments? Now, I want you to take a guess here. What is the expected number of people that are going to get their own name if we play this game with all the people in the world? And believe it or not, the answer is 1. So there's going to be very likely one person, Bob Bleeby Blop, who's going to be given their own name. Now, why is this the case? Let me show you in the next video. So let's play the game, but for only 3 people, Aisha, Beto, and Cameron. So we have the 3 people and the 3 names in a bag, and we're going to start giving them to the 3 of them. So let's say we give this person Beto's name, and we were wrong because that was Cameron. And we give this person Aisha's name, so we were correct because that's Aisha. And then we give this person Cameron's name, and we were wrong. So this time we got 1 right and 2 wrongs. Now let's play this game many times, and 6 possible things can happen, and they're mentioned here. These are
the 6 different ways that I can give these 3 people the 3 names in the bag, and each one has the same probability. So let's count how many times we are correct. So if we do the first assignment, we're correct 3 times. If we do the second assignment, we're correct 1 time. For the third, we're correct 1 time. For the next 2, we're not correct at all. And for the last one, we're correct 1 time. And this is because for the first one, we got the 3 names correct. For the second, we got Aisha. For the third, we got Cameron. For the 6th one, we got Beto correctly. And for the others, we got them all wrong. So we need to find the average of these numbers. That is the expected number of people we're going to get correct at this game. Now the sum, 3 plus 1 plus 1 plus 1 is 6. And 6 divided by 6, which is the total number of times we play the game, is 1. So the average is 1. So for 3 people, the expected number of correct assignments is going to be 1. Now we can do the same thing for 8 billion people. Of course, this is going to be a pretty difficult average to calculate because there's going to be a lot of possibilities for that game. Is there anything simpler that we can do? So it turns out that yes, there is something simpler we can do for this calculation. And let me show you. It's going to be a little counterintuitive, but it works really well, and it's going to be using the sum of expectations. So let's call matches the random variable that counts the number of matches in this game, and we want to find that the expected number of matches is 1. Now let's split it into several things. Let's call A the number of correct assignments that only matter to Aisha. So the number of times that Aisha is given her own name. Now, because she can be given the 3 possible names, then what is E of A, the expectation of A? Well, each name is given to her with probability 1/3. Therefore, each time we play this game, on average, she gets her name correct 1/3 of the time. Therefore, E of A is 1/3. We can do the same thing with Beto, and the expected value of the number of assignments that get his name correct is 1/3. And with Cameron, we do the same thing. The expected number of assignments that get their name correctly is 1/3. And because the number of matches is equal to the number of matches with Aisha plus the number of matches with Beto plus the number of matches with Cameron, then their expected values also add together. So therefore, expected number of matches is 1/3 plus 1/3 plus 1/3, which is 1. And that's another way to see that the expected number of matches is going to be 1. Now, that technique is simpler because now we can use it with every person in the world. We have 8 billion people. We're going to play this game with all of them. And as I told you before, the expected number of matches is going to be 1. But why? Well, let's say that we have all the people called person 1 all the way to person n, where n is 8 billion, or the number of people in the world. And the number of matches is going to be the number of matches for person 1 plus the number of matches for person 2, etc., plus the number of matches for person 8 billion. And now the expected number of matches is equal to be the sum of all those expectations. Now, the expectation for each one of these is 1/n, because, let's say, if you're one person, the probability that you get your correct name is 1/n. So the expected number of times you get your name correctly is 1/n. And when we add these together, we're adding 1/n n times. So 1/8 billion, 8 billion times. And this number is 1. Because in general, you have that the expected value of a sum of n variables is the sum of their expected values. This result is always valid. It doesn't depend on the distribution of your variables, and it doesn't matter if they're independent or not. It is always true. So as you can see, this property that the expected values add is pretty simple, but it can also be pretty powerful.
So it turns out that expected value, although it tells us a lot about the distribution, it doesn't tell us the whole story. For example, 2 distributions may have the same expected value, but one of them can be very narrow and the other one can be very wide. This is captured by something called the variance. Let me show you what the variance is. We're going to use an example of a game.
Let's look at 2 games. In the first one, you flip a coin. If it's heads, you win $1. If it's tails, you have to pay $1. What is the fair price to pay to play this game? The correct answer here is 0. This is the expected value of this game.
And if you played it over and over again, this is what you would expect to win an average. Now look at the second game. If the coin lands heads, you will win $100. And if it's tails, you lose $100. What is the fair price to pay to play this game? Again, if you said 0, you're correct. Both games have an expected value of 0. If you played either game over and over again, on average, you would expect to break even. While these games have the same expected value, there's clearly a big difference between them. The second one has a much larger spread of possible outcomes where you're losing or winning $100 at a time. If you want a way to quantify this difference in the spread of possible outcomes, clearly expected value isn't working, so you'll need to use a new measure. And that measure is called variance. To work up towards the formal definition of variance, I'll first plot both games. The first game looks like this. You can win or lose $1 with a probability of 1/2 each. If you treat this game like a random variable x1, then it's pretty clear that the expected value of this game will be right at 0. Now here's the second game, which I'll call x2. You can win or lose $100 this time, also with probability of 1/2 each. Just like x1, the expected value here is 0. Now you can look at these two games together. Obviously the scaling here is a little off, but look at the high level differences. They have the same expected value or balance at the exact same point. The difference is the spread of the possible outcomes in the first game is relatively small, and the spread of the outcomes in the second game is relatively large. So let's explore some ways to quantify this difference in spread. One way to think of the idea of spread is how far away the points are from the expected outcome. If the spread is small, you would expect most points to be close to the expected value. With a bigger spread, you would expect most of the points to be farther away. Let's look at a few different expressions that try to capture this idea. The first one is deviation, and it's simply the difference between each point and the expected value. If you find the deviations for the points in the first game, you would calculate 1 minus the expected value of 0, giving a deviation of 1, and minus 1 minus 0, which gives a deviation of minus 1. Now, if you want to summarize the typical deviation in this data set, a natural thing to do would be to find the average of the deviation. And in this instance, that is some minus 1 plus 1 divided by 2, which is 0 divided by 2, which is just 0. That's weird. Does that mean there's no variation at all in this data? It turns out that the average deviation is actually always 0, and perhaps you can think why. The expected value will always appear at the point at which the positive and negative deviations cancel each other out. For example, in the second game, you would have deviations of 100 and minus 100, but you can probably already see that this will also give an average deviation of 0. So average deviation isn't a good approach, but perhaps it points us in the right direction. The issue was that some deviations are positive and some are negative. So a very intuitive approach would be to consider this expression, the absolute deviation. Now all the deviations become positive, and it might actually make sense to take an average. Is that a good measure of spread? Without getting too much into the mathematics of why, I'll just say this approach isn't used that often. Even if it's very intuitive, the absolute value function introduces some messy mathematical properties, and for that reason, the approach I'm about to show you is the preferred method of measuring spread. Perhaps you've seen this before, but the most common approach is to actually square the deviations. In other words, all of these deviations, minus 1, 1, minus 100, and positive 100, are squared. All of these values will now be positive, which is what the absolute deviation attempted to do, but without introducing some of the mathematical issues of the absolute value function. Finally, you can find the expected square deviation or mean square deviation using this expression. This will tell you the average size of these square deviations. And this is called the variance, which looks like this. Notice that this is just the average of those square deviations. Simplifying these expressions gives the actual values of variance for these two games. The first game has a variance of 1, and that makes sense since both negative 1 and positive 1 squared are equal to 1. The average square deviation is 1. And using the same approach, you can calculate that the second game has a variance of 10,000. This may seem like a significant increase in variance, but remember, you're no longer measuring the average deviation, but rather the average square deviation. And as you'll learn in the following videos, this measure of the spread of a dataset has many useful properties. One more time, here's the equation of variance. If you're still getting used to the expectation notation, remember it always essentially means that you're finding an average value. So this expression contains 4 steps. First, find the mean of x. Second, find the deviation from that mean for every value of x. Third, squared those deviations. Fourth, average those squared deviations. And once again, that just makes variance the average squared deviation. Notice, just like expected value, that this is a weighted average. In these examples, all the outcomes had equal probability. But if they didn't, you would use the probability of each outcome as weights. It is symbolically written like this, var of x. In the last example, you saw two games that had the same mean but different spread or variance. Now compare these two games. Game 1 is similar to the one before. You flip a coin and if it lands heads, you win $2, and if it's tails, you lose $2. The second game is slightly different. If the coin lands head, then you win $3, but if it lands tails, then you lose $1. Which of these games has a greater variance? To answer this question, you can think of the spread. As it turns out, they both have the same variance because the spread of their outcomes is the same. Let's see how this works. First, let's look at the expected value for each game, or the amount of money you expect to get after many plays. For the first game, e of x1 is 1/2 times minus 2 plus 1/2 times 2, which is 0. However, as you can see, the second game is not centered. So in this case, e of x2 is 1/2 times minus 1 plus 1/2 times 3, which is 1. Now let's find the variance of each game. In each case, I'll just find the average square deviation between each outcome and the expected outcome of that game. For game 1, you have 1/2 times minus 2 minus 0 squared plus 1/2 times 2 minus 0 squared, which gives a variance of 4. For the second game, you have 1/2 times minus 1 squared plus 1/2 times 3 minus 1 squared, which is also 4. So this means that these two games have different expected outcomes, but the same variance in those outcomes. The formula var x equal expected value of x minus e of x squared is a great definition, and it's quite intuitive. However, in many cases, it's easier to do the math using this alternative formulation, e of x squared minus e of x squared. Let's see that both expressions are exactly the same thing. It might look a bit scary, but just remember that at the end of the day, it's simply some algebraic manipulation of the variance formula. Let's start with the definition of variance and expand the square terms inside the square brackets. You get the expectation x squared minus 2 e of x times x plus e of x squared. Expectation is a linear operation, meaning e of x plus y equals e of x plus e of y. So next, I'll write the single expectation as the sum of three different expectations. E of x squared minus e of 2 e of x times x plus e of x squared. Here's the next step. Getting to this point depends on a few additional facts about the expectation, which I'll explain one piece at a time. First, e of a constant times x is just the constant times e of x. This is actually just an extension of the fact that the expectation is linear. What this means is that you can pull the constant outside of the expression. In this case, this 2 was pulled outside of the expectation. Next, e of x is a constant. As you already know, e of x is the expectation or mean of the random variable x. It is just a number. That means that this e of x could also be removed from the expectation. Finally, e of a constant is just that constant. In this case, it allowed the outer e of x on this third term to be removed. Remember, e of x is just a constant, so this is just the expectation of some constant squared, or yet another constant. From here you can simplify, first by rewriting the second term 2e of x times e of x as simply 2e of x squared. And finally combining the last two terms to get minus e of x squared. And there you go. That's the identity you were looking for. Sometimes you'll find it very useful to know this other means of calculating variance. Let's explore an important property of variance by returning to the example of a dice game. You roll a fair dice, so all the 6 sides have a probability of 1/6 of coming up. Then you win double of whatever you rolled. However, the game costs $5 to play, so here is the net amount you take home for each possible outcome of the game. You can win as much as 7 if you roll a 6 and lose as much as 3 if you roll a 1. What is the variance of this game? Let's imagine that your dice roll is a random variable x. You can think of x as a randomly generated number between 1 and 6 with an equal 1/6 probability of each outcome. Your net winnings is a new random variable y. Whatever x outputs, in order to obtain y, you multiply it by 2 and minus 5. The key relationship I'm going to introduce here is this identity. The variance of ax plus b is equal to a squared times the variance of x. In this case, that would indicate that the variance of your new random variable y is 4 times the variance of your original random variable x. Now let's think it's true. In this case, that would indicate that the variance of your new random variable y is 4 times the variance of your original random variable x. Now let's think through why this makes sense based on what you've learned. First, I'll draw the expected value of x, which is 3.5, and the expected value of y, which is 2. Now recall that variance is the average square deviation from the mean, so let's look at what happened to the deviations. For example, this deviation in x started at 0.5, but that same outcome in y now has a deviation of 1. Meanwhile, the largest deviation in x is 2.5, and in y that deviation grows to be 5. In other words, all the deviations double. Since variance is the average square deviation, it makes sense that if all your deviations are twice as big, the variance is now 4 times as big. In general, if you multiply a random variable by a, the variance increases by a factor of a squared. Notice that the negative 5 did not have any impact on the variance. Intuitively, adding a number to a random variable just changes the point the new distribution is centered around, but it doesn't impact the spread. Multiplying x by a value, however, will impact the spread of your data. This is a useful relationship to be aware of, and hopefully this explanation of why it holds reinforces what variance is measuring. So the variance is a pretty useful way to measure the spread of a distribution. However, it has one small drawback: the units. Imagine if your distribution has, for example, the height of people. So these heights are measured in meters or feet, and the expected value is also measured in meters or feet. However, the variance is measured in meters squared or feet squared, and this is not useful. So what do? We take the square root. We call that the standard deviation. So the standard deviation is a pretty useful way to measure the spread of a distribution using the same units of the distribution. So as we saw, the variance is the expected value of x minus the mean squared, which can also be written as the expectation of x squared minus the square of the expectation of x. Now here's a small problem. Say that x is measured in meters, maybe its height or some length, then expected value of x is measured in meters. So it would tell us, for example, the average of the height of the people we're measuring. So it's in the same units as the variable that we're measuring. However, look at the variance. The expectation of x squared is in meters squared, and the expectation of x all squared is also in meters squared. So the variance of x is measured in meters squared. And that's not so useful. Imagine if we're measuring people's heights and the variance tells you something in meters squared, which measures area. So that's not so useful. What can we do? Well, a simple solution is to just take the square root of the variance of x, and that is now measured in meters. So let's call that the standard deviation of x. The standard deviation is the square root of the variance of x. Now, in the normal distribution, the standard deviation is very useful. Let's take a look at this bell-shaped, and remember that when we defined it, it had two parameters: mu, which was the center of the bell, or the mean, or the expected value, and sigma, which was the spread of the bell, or the standard deviation, and the formula was this one over here that we saw in the previous week. Well, a good visual cue to determine the value of sigma is where the bell starts changing concavity. And at that point, you are at mu plus sigma or mu minus sigma, depending on where you're standing. And how much of the area is between mu plus sigma and mu minus sigma? Well, it turns out that 68% of the area is in between those two. And when you look at mu plus 2 sigma or mu minus 2 sigma, so the area between two standard deviations of the mean in both directions, there's actually 95% of the curve here. And if you look at 3 standard deviations, 99.7 of the curve is there. So, to be more exact, 68.2 lies in between one standard deviation. In these little two strips over here between 1 and 2 standard deviations, there's 13.5%. And in the next ones, there's 2.35%. And in the tails, which extend infinitely, but they're still very, very, very tiny, there's a 0.15% of the area. And in statistics, it's very common to talk about being within 1 or 2 or 3 standard deviations of the mean when you're talking about a normal distribution. So in this video, I'm going to show you an interesting application of what you learned so far about mean, expectations, variance, and standard deviations, which is adding two Gaussian distributions. Imagine you're studying the total response time of a computer system, which consists of two components: the processing time, which represents the time taken by the system to process a given task, and the network latency, which is a delay in communication between the computer system and other network devices, like database servers or external APIs. Let's call these variables R, T, and L. So the total response time is the sum of processing time and network latency. In other words, R equals T plus L. Imagine you can model the processing time in milliseconds with a Gaussian distribution with mean 10 and standard deviation 2.
And the total latency, you can also measure it in milliseconds, also a Gaussian with mean 5 and standard deviation 1. And suppose also that these two variables are independent of each other. So here are the corresponding densities for the processing time and for the latency. Now sample each variable 10,000 times and draw the resulting histograms. They both fit the curves pretty well. Now with these samples, you can now generate 10,000 samples of the response time. Let's do it. When you generate them, this is how the histogram looks. The histogram for the sums of each processing time and each latency, and notice that R is still Gaussian. Now the question is, what are the parameters of these Gaussian? Well, let's begin with mu. Mu is easy because it's the expected value of R, and that's the expected value of t plus L, but since expectation is linear, then that's expected value of t plus expected value of L, or mu of t plus mu of L. If you remember correctly, the expected values were 10 and 5, so this one is 15. And now let's look at the sigma for this new variable, which is the square root of the variance of R. Again, this will be the square root of the variance of t plus L. Now, this is not the general result, but since t and L are independent, it turns out that the variance of the sum is the sum of the variances. So this is variance of t plus variance of R. In other words, sigma of R is sigma of t squared plus sigma of L squared. And that's 4 plus 1, which is 2.2361 or 5. So the resulting R is Gaussian, where the mean is 10 plus 5, the sum of the two means, and the standard distribution is 5, the square root of the sum of squares of standard distributions. Now in general, if you have a linear combination of variables where x and y are both Gaussian with parameters mu x, sigma x, and mu y, sigma y, and both of them are independent, then the resulting variable follows a Gaussian distribution with mean a mu of x plus b mu of y, and variance a squared sigma x squared plus b squared sigma y squared. So let's formalize something we saw already. When you have a distribution with mean mu, it's always nicer when the distribution has mean 0. So one thing you can do is subtract mu and get a new distribution with mean 0, and this one is simply x minus mu. It's the variable x minus mu, where mu is simply a fixed number, which is the mean of the distribution. So this is common practice. When you have a variable x, actually it may be better to consider x minus mu. And why is it that the new variable x minus mu has expectation 0? Well, remember that expectation is linear, so you can take the expectation of x plus y as the expectation of x plus the expectation of y. Therefore, the expectation of x minus mu, if we let y equals minus mu, is the expectation of x minus the expectation of mu. But the expectation of mu is simply mu because mu is a constant. And so therefore this is 0 because e of x is precisely mu, so e of x minus mu is 0. Now here's another trick that's very useful. When you have a distribution, and let's say we already have mean equals 0, and if the standard deviation is sigma, that measures the spread. Well, in the same way that we want the mean to be 0, we kind of want the standard deviation to be 1. It's always nice when the standard deviation is 1. So what do? Well, if the original random variable was x and has a standard deviation of sigma, then x divided by sigma has a standard deviation of 1. So we take this x, turn it into x divided by sigma, and that has a standard deviation of 1. And the math is the following. The variance of cx, where c is a constant, is the expected value of cx squared minus the expected value of cx all squared. And because we can take away the constants outside, then the part of the right is c e of x squared, and we can also take the c squared from the first one. So we factor this c squared and we get e of x squared minus e of x squared, and that's c squared variable of x. So I can take a constant out of the variance, but it comes out as a square. Now let's take a look at variance of x divided by sigma on the right. That's 1 over sigma squared variance of x, because precisely 1 over sigma is that constant c in the left. And if we take the square root, we have that the standard deviation of x over sigma is 1 over sigma times the standard deviation of x, because we took the square root of everything on the right side. So the 1 over sigma squared becomes 1 over sigma, and the variance becomes the standard deviation. This is sigma divided by sigma, which is 1. And that's why dividing by the standard deviation means our new variable has a standard deviation of 1. So to summarize, this is how you standardize a distribution. You have the distribution x with mean mu and standard deviation sigma. If you subtract mu, you get a new one, x minus mu, with mean 0 and standard deviation still sigma. This is called centering a distribution. And now, since we want a standard deviation of 1, then we divide x minus mu by sigma, and now we have a mean of 0 and a standard deviation of 1. And this is called scaling. And this whole process is called standardizing. So anytime I say standardize a distribution, you do this. Subtract the mean, divide by the standard deviation, and you get a really nice distribution with mean 0 and standard deviation 1. Next, you'll find an interactive tool that lets you sample from several different distributions and visualize the results. You'll be able to see the mean, median, and standard deviation of the data you collect and compare those results to the theoretical values you'd expect. Try a few different distributions, and once you're ready, move on to the following video.
So as you can see, the expected value and the variance or standard deviation paint a really good picture of the distribution. However, there are a lot of subtleties that are not captured by them. Some of them are called skewness and kurtosis. And let me show you what they are.
So before we get into other ways to measure a distribution, let me tell you about the moments. It's something you've already seen, but we can formalize it here. So let's say you have a random variable that can take the value -2 with probability 1/3, the value 0 with probability 1/6, and the value 1 with probability 1/2. So what is the expectation? It's 1/3 times -2 plus 1/6 times 0 plus 1/2 times 1, whatever that is. What's the expectation of the variable squared? Well, it's the same thing, except you take the value squared times the probability. Now, those are called the first and the second moment. E of x is the first moment, the expectation, and e of x squared is the second moment, which is related to the variance. It's not exactly the variance, because you have to center it, but it's related to the variance. What do you think goes next? Well, we can continue with the third moment, which is e of x cubed, the expectation of the variable cubed, and so on. And the kth moment is the expectation of the variable to the k. And those are going to be pretty useful in a bit. So in general, if the random variable can take the values x1 up to xn with probabilities p1 up to pn, then the first moment is sum of pi xi, the expected value. The second moment is sum of pi xi squared. Third moment is sum of pi xi cubed. The fourth moment is sum of pi xi to the fourth, and so on until the kth moment, which is sum of pi xi to the k. And as I said, we're going to be using those in a bit. Now let's actually change the scenario a little bit. In one scenario, you're going to be playing the lottery. And in the other scenario, you're going to be the owner of a car insurance company. And bear with me for the numbers. So if you're playing the lottery, then you buy a ticket that costs $1, and the jackpot is $100. So you can win $100 and you pay $1. So what can you win? Well, if you win the lottery, means you paid $1 and you won 100. So you won $99 and you win it with 1% probability. The probability that you win this lottery is 1%. And with 99% probability, you don't win it, which means you lose $1 because you paid that dollar in your ticket. Now keep these numbers in mind. Now, let's say that you sell car insurance. You are the car insurance company. And people buy car insurance from you. So let's say you only have one client, and that client buys car insurance and it costs $1. And the client could crash or not crash. And if the client crashes, then the reparation is $100, which means you have to pay $100 to repair the car. And the probabilities are similar as before, because the probability that the client crashes the car is 1%. So with 99% probability, the client will not crash the car and you will win $1 because they paid $1 for the insurance. And with a 1% probability, you will gain the dollar and lose 100 because you had to pay for the crash reparation. So with 1% probability, you lose $99. If you look at these two games, they are the exact opposite, right? In the lottery, you win 99 with a 1% probability and you lose 1 with a 99% probability. And in the car insurance, win 1 with a 99% probability and you lose 99 with a 1% probability. So let's plot them. Over here in the lottery, here is the dollar you lose if you buy the ticket and don't win the lottery. And here's a 99 you win if you buy the ticket and win the lottery. And on the car example, here is the $1 you win when they buy insurance from you and they don't crash. And here's the 99 that you lose if somebody buys insurance and then they crash. So as you can see, this is the same game, but reflected over the horizontal axis. So now let's start calculating things. As you can see, these two games or these two scenarios are tremendously different. And let's see if that difference can be detected by either the expected value or the variance. So let's first calculate the expected value. So when you calculate it, you can see that it's 0 because here it is. Expected value of x1, the first scenario is going to be called x1, the lottery. And the expected value is, well, minus 1 times 0.99 because you lose that dollar with probability 0.99, plus 99 times 0.01 because you win 99 with a probability of 0.01, and that's actually 0. And e of x2, the car insurance variable, is also 0 because you lose 99 with probability 0.01 and you win $1 with probability 0.99. So these two games have the same expected value, which is 0. That means that on average, if we play this lottery many times, you're going to be gaining an average of 0. And if you are the car insurance company and you sell a lot of insurance policies, on average, you're going to be making $0. So we did not succeed at telling these two scenarios apart using the expected value. So what about the variance? Well, what's the spread of this distribution versus the spread of this distribution? They seem to have the exact same spread because they're reflections of the other one. And you can determine this by actually calculating the variance of x1. Now the variance is just e of x squared because it's already centered. So it's minus 1 squared times 0.99 plus 99 squared times 0.01, and that's 99. And the variance of the other one is the exact same calculation, which is 99. So the variance of these two games is the same. The expected value of these two games is the same, but they're vastly different games. So how do we tell them apart? Well, remember that the variance is e of x1 squared minus e of x1 all squared, and the same thing for x2. And e of x1 is 0 and e of x2 is 0, so these ones don't really matter. So in reality, we were looking at the second moment. So these two distributions have the same first moment and the same second moment. So how do we tell them apart if they have the same first moment and the same second moment? Well, what about the third moment? Why don't we calculate the third moment? E of x1 cubed. That's negative 1 cubed times 0.99 plus 99 cubed times 0.01. That's 9,702 for the left scenario, the one of the lottery. And for the one of the car insurance, it's the same calculation but with negatives on the wrong places. So it's negative 9,702. So that's it. We're going to use the third moment, the expected value of the cube of the variable, to tell them apart. And what the cube takes into account is that for the first distribution, there's some values that are really, really far away to the right, because at the end of the day is that 99 cube which is making the difference. The positive 99 cubed is the one that takes most of this calculation with it. And on the other one, there's this negative 99, that's the one that dictates pretty much this number of minus 9,702, because the other number is very small, and that means that some values are very far to the left. So in other words, the cube of the variable detects if you have numbers that are skewed towards the right or skewed towards the left. Let me show this to you in a more continuous example. The distribution on the left is going to have a very high third moment, e of x1 cubed, because it's positively skewed. Positively skewed is the term we used when there's more values towards the right very far than towards the left. So it's skewed towards the right. And the other distribution is negatively skewed, which means it has values very far towards the left. And that one has a large negative value for e of x cubed. So the magic value here that's helping us is the expectation of x cubed. That's almost called the skewness. We still need to standardize. So the skewness is the expected value of the centered and standardized distribution. So expected value of x minus mu divided by sigma cubed. So we have three cases. When the distribution is positively skewed towards the right, then e of x minus mu divided by sigma cubed is bigger than 0. When it's not skewed, it means that it looks more symmetric and the expected value of x minus mu over sigma cubed is going to be 0. And finally, when it's negatively skewed, that it has a lot of values towards the left, then e of x minus mu divided by sigma cubed is less than 0. So the moral of the story is when the first and second moments don't help you, go to the third one. And that tells you the skewness of the distribution. So now that you've learned expected value, variance, and skewness, let me show you two new games. Game 1 is the following. With a probability 1/2 you win $1, and with probability 1/2 you lose $1. That's like tossing a fair coin. So that's the game we've seen already many times. Let's have a second game where with probability almost a half, that's 100 divided by 202, you win 10 cents. With probability 100 over 202, you lose 10 cents. So it's a less risky game, except that there's a tiny probability that you win and lose a lot more. So with probability 1 over 202, you win $10. And with probability 1 over 202, you lose $10. So in the game on the left, you win $1 or you lose $1. In the game on the right, you could win 10 cents or lose 10 cents with much higher probability, but there's also a small chance that you win or lose $10. So here's a tricky question. Which game is riskier? See, the game 2 seems a lot more conservative with the 10 cents, but once you throw in the $10, it becomes a little riskier, but the probability that you win $10 is very small, or that you lose $10. So let's calculate the variance. But before calculating the variance, let's actually calculate the expected value. In other words, let's take a look at the games as distributions. So here's game 1, where you can win $1 or lose $1 with probability 1/2. We've seen that one many times. Game 2, you can win 10 cents and lose 10 cents with probability almost 1/2. And then there's a small chance that you make $10 or that you lose $10. Now, those two distributions are very different. So do you think we'll be able to tell them apart with expected value, or with standard deviation, or with skewness? Well, let's hope that one of them works, because we need to be able to tell them apart with some metric, right? They are different games. First, let's calculate the expected value. And as you can see, the expected value is not much hope, because it's 0 for both. They're both centered, right? So for the left one is 0, and for the right one is 0. And I invite you to actually calculate it, but if it's a symmetric distribution centered around 0, then the expected value has to be 0. Now let's look at the variance. What do you think happens with the variance? This one's going to tell us which one is riskier. Let's look at e of x1 squared. So this number is 1/2 times minus 1 squared plus 1/2 times 1 squared, which, as we've seen many times, is 1. But now let's look at e of x2 squared. x2 is the amount of money you gain on the second game. Well, this one is 100 over 202 times minus 0.1 squared plus 100 over 202 times 0.1 squared plus 1 over 202 times minus 10 squared plus 1 over 202 times 10 squared, because it's the sum of the probabilities times the squares of the values. When we do the math, we get this, and this actually adds up to 202 divided by 202, which is 1. So believe it or not, these two games have the exact same variance. Neither one of them is riskier than the other one. Variance of x1 is 1, and variance of x2 is 1. So when you take the square root, they have the same standard deviation. And that's not so convenient. We couldn't tell them apart using expected value or using variance. Do you think we have a hope with skewness? Well, Remember that distributions that are symmetric around the midpoint have skewness of 0. So both of these have a skewness of 0. They're not skewed towards the right or towards the left. They're both symmetric. So skewness is also not going to help us. So who can help us? The first moment didn't help us. The second moment didn't help us. The third moment didn't help us. I wonder. So to summarize, both have a skewness of 0. Both have a variance of 1. Both have a mean or expectation of 0. However, something interesting is happening here. How would you tell them apart? How would you describe to someone that these two are different? One way to describe it is to say, well, the one on the right has values that are really far away from 0. Maybe we can capture that. So let's go back to moments. The first moment is 0. The second moment is 1. The third moment is 0. And the same thing happens for x2. So what moment should we go for? What about the fourth moment? Maybe the fourth moment can help us. Let's take a look. What is e of x1 to the fourth on the left? Well, it's a half times minus 1 to the fourth plus a half times 1 to the fourth, which is again 1. And what is e of x2 to the fourth? Well, let's take this calculation and see what happens. That is 99.01. That is huge. Why is it huge? Because this minus 10 to the fourth and this 10 to the fourth are 10,000. And that's a big value. So when the distribution has very large numbers very far away from the center, even if the probabilities are tiny, e of x to the 4 captures this. So that is called kurtosis. And kurtosis is the fourth moment. E of x, oh no, actually it's not. It's almost that. We still need to standardize. So the kurtosis is the expected value of x minus mu divided by sigma raised to the fourth power. And what does kurtosis say of a distribution? Well, in a case like this, where the tails are very skinny, the kurtosis is small. But in a case like this, where the tails are thicker, then we have a large kurtosis. So thin tails, small kurtosis, thick tails, large kurtosis. Even if they have the same variance, the variance may still not be able to pick up, because even if you have thick tails, you may have a very skinny distribution in the middle. But kurtosis is a much more sensitive measure for the thickness of the tails of the distribution. So we've learned many ways to tell distributions apart: expected value, variance or standard deviation, skewness, and kurtosis. With these 4 tools, you'll be able to say a lot about your probability distributions.
You've learned several ways to describe your data numerically, but for a data scientist, it's tremendously important to be able to visualize the data correctly. In this video, I'm going to show you several ways for visualizing data.
So let's begin by considering a data set. We're considering an advertising sales data set and the newspaper ad budget. So if you took course 2 from this specialization, you're already familiar with it. This data set showed the newspaper, TV, and radio budgets and the sales revenues generated. For simplicity, let's start considering only 12 samples from the newspaper ad budget. From this small sample, you may want to infer the median. Remember, the median is the point that splits your data in half. So first, you will need to sort the observed values in increasing order, and then, since you have 12 data points, then you can evenly split the data set into these 2 halves with 6 samples each, and the median is simply the average of the 2 values in the middle. That is 27.8. We call that the 50% quantile or the second quartile, and those names will make more sense in a minute. So what about the point that leaves 1/4 of the data to the left and 3/4 to the right? Or in other words, the average of these 2. Well, that's 18.35, and that's the 25% quantile, or the first quartile. We call it Q1. So it's kind of like the median, but it doesn't cut it into half-half, but into 1/4, 3/4. And we can call it little q of 0.25 or big Q of 1 for first quartile. And in general, you can do this for any percentage. The k% quantile is the value that leaves k% of your data to the left and 100 minus k% of the data to the right. And we just denote it as little q of k divided by 100. And some common quantiles are the 25% one, the 50% one, and the 75% one. The 25% one, as you saw, is the first quartile, q1. The 50% quantile is the median, which is q2. And the 75% quantile is the third quartile, which is q3. So let's say your dataset has n points, and n sub k correspond to the first k% of data. So for example, n20 here is the first 20% of data, and n100 minus n20 is the last 80% of the data. Then we have that 20 divided by 100 is n sub 20 over n, and that's the probability that the variable you're measuring, x, is below the k% quantile. In this case, it's q 0.2 because that's 20%. And what we're doing is, suppose that your data follows some distribution and that has a PDF which looks like the blue curve. So then the area under that curve for the k% quantile, in this case the 20% quantile, should be k over 100. And so if you're computing quantiles from distributions, you can say that the k% quantile is simply the value such that the probability of the variable being below q is simply k over 100. Now there's a cool visualization called the box plot or the box and whiskers plot, which is a standardized way of displaying the distribution of your data based on 5 statistics: the minimum, the maximum, the median, the first quartile, and the third quartile. Let's see how it works using our newspaper advertisement example. So to create a box plot, you need to calculate the 3 quartiles. That means the 25% one, the 50% one, and the 75% one. So let's divide the data into 4 blocks of the same size. The first quartile, as you saw, is the midpoint between 18.3 and 18.4. The second one is the midpoint between 25.9 and 29.7. And the third one is the midpoint between 51.2 and 54.7. Those are the 3 quartiles. Now we're going to call the interquartile range as q3 minus q1. That's where 50% of your data lies, and that's 34.6. That's that difference between those two. And we're going to look also at the minimum and maximum values of the dataset. The minimum is 8.7 and the maximum is 75. And we're going to put all of that in one plot. So let's start with the box. It should go from the first to the third quartile. That's from 18.35 all the way to 52.95. Then we draw a line at the value of the median, 27.8. That's Q2. Now it's time to draw the whiskers. For this, you draw 2 lines going from the end of the box until Q1 minus 1.5 times the interquartile range, which is the height of that orange box, and one going from Q3 plus 1.5 times the interquartile range, which is Q3 minus Q1. However, the whiskers should never go beyond the max and the minimum values of the dataset. So if that happens like in this example, simply cut the whisker at those values. Now the box plot is very useful because just by looking at the plot, you can get plenty of insight on your data. In this case, you can easily see that the data is skewed because Q3 minus Q2 is way bigger than Q2 minus Q1. For this small case, we can see that there are no extreme points or outliers, since both whiskers end at the max and min values. If there are any values that are outside of the whiskers, then we say that those are outliers. They're too far from the center. Now the length of the box and the whiskers allow you to analyze the dispersion of the data. Now let's take a look at the box plot obtained using all the datasets. For this, you need all the values of Q1, Q2, Q3, the interquartile range, and the minimum and the max. The minimum is 0.3 and the max is 114. With these values, you get these box plots. So these are the Q1, Q3, and Q2. Notice that the bottom whisker goes from Q1 to the smallest value of the dataset, 0.3, while the upper whisker actually ends in 93.626, which is 1.5 times the IQR. This leaves 2 data points outside of the whisker, which are considered outliers. Now let's go back to the advertisement example. All these samples seem to come from a continuous random variable.
You know by now that you can describe your data distribution for continuous variables with the probability density function, or PDF. The question is, can we gain any idea of what the PDF looks like from the data? Well, I'm sure you're already familiar with histograms. Since doing a histogram with just 12 values doesn't make much sense, let's plot the histogram for the whole dataset. Technically, a histogram satisfies all the conditions of a density function. It's positive and the area under the curve is 1. However, it's not a great approximation. For one, PDFs are usually a smooth function, and also the discontinuities of the bars appear from the technique used to compute histograms and not from the data itself. So in other words, the actual distribution where these come from may have a pretty smooth density function, but since we're taking a histogram, it looks like it has a lot of peaks. So is there any way we can approximate the PDF of our data from this histogram? And it turns out there is, and the method is called kernel density estimation. We start by making our observations in a graph. And then you want each point of your data set to have an effect that spreads around the observation point, because we want high density where there's a lot of points and low density where there's no points. So let's put a little mountain in each of the points. That means a small Gaussian curve on top of each data point. This is called the kernel. You could choose other functions than the Gaussian, but we're not going to get into that. And the value of sigma you choose for the Gaussian density will determine how far the effect of each point spreads. It could be thin or it could be wide. Now let's get back to the original plot. Lastly, all you have to do is multiply everything by 1 over n and sum all the blue curves. Notice that since the area under each curve is 1, the average of the curves must give us an area under the curve of 1. And this is what estimation looks like after cleaning up the plot a bit. Doesn't look so great, but that's because you try to approximate a density from just 12 data points. But if you try from many points, then you're actually going to get a really nice smooth function that actually resembles the PDF well. So this is a way to approximate the PDF based on the data. So finally, I want to show you one last visualization tool. These are called violin plots and are widely used in data science. What's so cool about violin plots? It contains the information of both the kernel density estimation and the box plots. Really all you do is you put the kernel density estimation here at the side of the box plot. Let me be more specific. The violin plot looks like this. Here you have the KDE curve, the kernel density estimation. Here you have the mean. Here you have the quartiles. And here you have the whiskers. So that is the violin plot. And as you can see, it's pretty useful. Now, checking for normality in data is frequently done in data science. Many models such as linear regression, logistic regression, and Gaussian naive Bayes assume that the variables follow a Gaussian distribution. Some other tests used in data science also assume this hypothesis. But how can we tell if the data follows a normal distribution or not? Well, sometimes a quick inspection of something as simple as a histogram can let us know that data is in Gaussian. For example, the left one doesn't look very Gaussian and the right one looks a little Gaussian. But how do we get a more exact answer if the data is Gaussian or not when it looks bell-shaped like the one on the right? Well, for that we use quantile plots, or QQ plots. These are a great tool to visually inspect if your data is Gaussian. These present a graphical comparison between quantiles in your data and quantiles from a normal distribution. In the most classical form, your data is first standardized by subtracting the mean and dividing by the standard deviation. Then you compare the quantiles of your data, and finally it computes the same quantiles for a standard normal distribution. And it creates a scatter plot where the x value are the theoretical quantiles and the y value are the sample quantiles. Note that in each point, the scatter plots correspond to one of the quantiles. If your data was actually normally distributed, then the points should be close to this orange line. This QQ plot corresponds to the newspaper budget data, so it's expected that the data wasn't going to be Gaussian. This is especially obvious if you look at the two marked areas where the scatter plot really splits from the orange line. Also, the fact that there's more concentration of points on the area to the left than the one to the right is a sign that the data is skewed. Now let's see what happens when you look into the sales column on the data set. This histogram was pretty bell-shaped, and the QQ plot with this data confirms it. This time the quantiles are pretty much aligned around the orange line, which suggests a Gaussian distribution for the data. So previously you learned probability distributions for one variable. For example, the height of a population. But what if I want to look at two variables? For example, the height of the population and the age of the population. That's two distributions. And I may want to look at them together and see how these two features combine. For that, we need a joint distribution, and that's what you're going to learn in this video.
So consider a simple data set of 10 children aged 7 to 10, and let's count the children for each age. There's 3 children of age 7, 2 of age 8, 4 of age 9, and 1 of age 10 for a total of 10 children. Let's plot this count data here on a graph, and it gives us this histogram over here where this is the number of children of each age. Now if we divide by 10, we can turn these numbers into probabilities. So the probability, for example, that a child is age 9 in this data set is 0.4. Now, for these same children, let's say we capture their height data as follows. These are their heights in inches, and we're going to generate another table with the number of children of each height rounded to the nearest inch. And we can put these in a histogram as well. Notice that there's no child of height 48, but to complete the axis, let's bring that value back. Again, with a total of 10 children. Now let's divide the counts by 10 to get the probabilities. So for example, the probability that a child is 47 inches is 0.2 in this data set. So we have the data set ordered by these two metrics, age and height. Now here's a question for you. What is the probability that a child is 9 years old and 49 inches tall in this data set? Well, let's see from the probability mass function for age how many children are 9 years old. And we have 4 of them. I'm looking at the graph of the heights. Only 3 of these 4 children are 49 inches tall. So dividing this 3 by the total of 10 kids, we get 3 out of 10, and the probability is 3/10. And we're going to call age H and height Y. Those are 2 variables. And so the probability that a child is 9 years old and 49 inches tall, which is 3/10, can be written as P of xy of 949. X, the age, has to be 9, and y, the height, has to be 49. More generally, the joint probability of two discrete variables is denoted by P of capital X, capital Y, the name of the variables, of little x, little y, which are the values that I want these variables to take, the 9 and the 49, and that's the probability that x, which is the age, is equal to little x, 9 in this case, and that y, the variable for height, is equal to little y, which is 49. But we can calculate these probabilities easier if we organize the data properly. So let's construct the joint counts for 2 variables, and we're going to have something like this. There's one child whose age is 7 and height is 45. We put them here. Then there's 2 children of age 7 and height 46, and they're here. And then we have zeros for the rest of the row because there's no more children of height 7. Then some zeros here, and 2 children of age 8 and height 47, and then no more of age 8. And then there's 3 children of age 9 and height 49, and 1 of age 9 and height 50, and finally 1 of age 10 and height 50. And this is the table of counts, which we can turn into a probability mass function when we divide everything by 10. And now we have the probabilities for each possible combination of data. All possible combinations of x and y are what's called a joint distribution. And in this case, it's a discrete joint distribution because both ages and heights are discrete variables. Now let's solve some more questions with this joint distribution. For example, what is the probability that a child is 8 years old and 48 inches tall? We call the formula for probability discrete joint variables, and this is going to be 0 because there's 0 children of age 8 and height 48. Let's do one more. The probability that the age is 7 and the height is 46, that one's over here, which is 2 divided by 10. And so this is an example of a joint probability distribution function. Now let's throw two fair six-sided dice. Let x be the discrete random variable that indicates the number rolled on the first dice, and y the one that indicates the number rolled on the second dice. So the possible outcomes for x and the possible outcomes for y are all probability 1, 6, and there the numbers 1, 2, 3, 4, 5, 6. Let's put the probability mass function of x and also of y, because they're the same thing, over here. All the probabilities are 1/6. So we have x as the number rolled on the first die and y as the number rolled on the second die. The individual PMFs for each variable are as follows, and notice that x and y are independent variables. So for example, the probability that x is 2 and y is 5 is over here, and it's going to be the product of the two probabilities, 1/6 times 1/6, and so it's 1/36. And that's going to happen for all the pairs because, as we said, they're all independent, and so the probability mass function is simply a table full of 1/36 all over the place. So in the formula we have the following. The probability mass function of xy is p of x equals x and y equals y, which for independent discrete random variables is the product of the two. This obviously is not going to be the case all the time, but when the variables are independent, this is pretty simple because the probability mass function for x and y factors into the probability mass function of x and times the probability mass function of y. Now let's look at a more complicated example. You again throw a fair six-sided dice, and now x is the discrete random variable that indicates the number rolled on the first dice. So for example, here x is equal to 4. And y is going to be another discrete random variable, but this one's going to capture the sum of the two dice. So if the first one is 4 and the second one is 5, then y is going to be 4 plus 5 equals 9. And now let's look at this joint probability function. So the probability mass function of x is, again, the number rolled on the first dice, and that one looks like this because we already saw it. It's 1/6 for the values 1, 2, 3, 4, 5, and 6. What about the sum of both dice? Well, for this one we have the entire table with the values of both die, and we have 2 for 1, 1, then we have 3, 4, 5, 6, 7, 8, 9, 10, 11, and finally 12 for the value 6, 6. We can put these ones in a histogram too. Let's put them over here. The sum of dice is on the horizontal axis and the count is on the vertical axis. So as you can see, the sum that appears more often is 7, and the ones that appear the least often are 2 and 12. And let's actually write the pair of dice here in the histogram. And so that's our histogram for y. Now let's look at the table of counts for both x and y. So on the horizontal axis we have x, which is the value of the first die, and on the vertical we have y, which is the sum of the values of both dice. And we're going to put all these numbers here. So first we start with 1, 1, which is here because the first dice is 1 and the sum is 2. Then we have this one over here, 1, 2, which has the first dice is 1 and the sum is 3. And we can continue putting them here. As you can see, everyone is plotted on the coordinates where the first coordinate is the value of the first dice and the second coordinate is the sum of the two dice. Now, the counts are all 1 because only one combination leads you to each one of these blue boxes. So we have 36 possible outcomes, and when we divide by the sum, then we get that the probabilities are all 1/36, and that is the joint distribution for x and y. Now, using this distribution, what is p of 3, 7? For example, the probability of x equals 3 and y equals 7. Well, if x equals 3, then it has to be on the third column, and if y equals 7, then it has to be in the 7th row. It's really just the numbers 3 and 4. And the probability of this is 1/36 because all of them are 1/36 or 0. What is the probability of 1, 1, for example? That the first die is 1 and the sum is 1. Well, that's impossible because no dice can fall on a 0, and so that's shown over here. It falls on a square that has a 0 on it, so that probability is 0. So this is the joint probability distribution for the variables x and y.
So now you learn what a joint distribution of two discrete variables is. Now what if the variables are continuous? It's very similar. It's called a joint distribution of continuous variables, and that's what you're going to see next.
So far, all the joint distributions we've taken a look at have been discrete variables. For example, the age and height of a child, where the height was rounded to the nearest inch, the number rolled on the first die or on the second dice, or the number rolled on the first die and the sum of both dice. All of them are discrete. However, what happens when x and y are continuous random variables? And this is what I'm going to show you next, jointly continuous distributions. So recalling in a previous lesson, we had the example of a phone call, and we generated the probability distribution of the call waiting similar to this one over here. Now you learned to find the probability between some interval for a continuous variable, and it was the area under the curve as shown. Now let's work with some new data. Let's say we have two variables x and y, and x, as before, is the waiting time before a call is picked up by a customer service agent that we can assume is any number between the range of 0 to 10 minutes. And y is the customer satisfaction rating that also we can assume is a continuous value between 0 and 10. So it's not going to be 1, 2, 3 only. It can be 1.2, 4, anything. And so both variables are continuous. So for example, x can be 2.4 minutes, 1.5 minutes, and y can be a rating of 0.0, 5.7, etc. Now, x is the variable of waiting time between 0 and 10 minutes, and after 10 minutes the call ends. So it really has to be a number between 0 and 10 minutes. And we're going to look at a data set of 1,000 customers, and we get the following histogram. Now, y is the variable of satisfaction rating of a customer, and we have 1,000 customers, and here's the histogram. So a lot of customers gave it a 0, a lot of customers gave it a 10, and there's some values in between. Now, let's look at both of them at the same time. The x variable of waiting time between 0 and 10, and the y variable of satisfaction rating also between 0 and 10 for 1,000 customers. And the graph is the following. Looking at the distribution of the data, we can see that a lot more of the data is in the corners. So here is a heat map. And why is it in the corners? Well, a lot of customers had a very quick call. They got picked up pretty quickly and they're very satisfied. Those are over here. And a lot of customers had a very long call of 10 minutes, or maybe the service agent didn't pick up. And these customers were not very satisfied, so they gave it a low rating. When you actually look at the density, it's this over here. So these two areas are here. They're strong areas, low time and high rating, and high time and low rating. And you can actually see this as a three-dimensional plot. If you imagine this plot in the right as a mountain seen from the top, where the dark areas are high points and the light areas are low points, then this is the actual mountain. So these areas of high density are over here. And those are the areas where we're most likely to find a customer. So going back to the scatter plot, let's actually calculate the mean for both the x and the y variables. So when we calculate the mean of x, of the amount of time that is spent before the call being picked up, that's 4.903 minutes. And the expected value of y, which is the average of the rating of the customers, is 5.280. This point is over here. That's the mean. That's the place where you would balance this data set on your finger if you were to balance all these points. Now let's calculate the variance of each variable. So let's aggregate over every row to obtain the distribution for time, and let's aggregate over every column to obtain the distribution for customer ratings. And now we have to calculate the variance of x and the variance of y. In order to calculate the variance of x, we first calculate the expected value of x, which as we saw before is 4.903 minutes, and the expected value of x squared, which is 32.561. And now the variance is simply e of x squared minus e of x all squared, which is 32.561 minus 4.903 squared, which is 8.526. In a similar way, we're going to calculate variance of y. Recall that e of y is 5.280. E of y squared, we can calculate it as 38.037, and the variance is e of the square of y minus the square of e of y, which is 38.037 minus 5.280 squared, and that's 10.163. So our variances are going to be 10.163 for y and 8.526 for x.
So now that you know joint distributions, let me introduce you to two very important concepts: the concept of the marginal distribution and the conditional distribution. Let's go back to the age and height example. Imagine that I have a full distribution of ages and heights of the populations, but all of a sudden I don't care about age anymore. I just want the distribution of heights. What I have to do is aggregate over all the ages, and now I have what's called a marginal distribution. Another thing I can do is take slices. For example, I have the full distribution of age and height, and let's say I now only care about the height distribution of people of age 30, for example. So what I do is I take a slice, and that is called the conditional distribution. Let me show you more.
So recall this data set of children with ages and height from which we generated a joint distribution as shown here. Now, what if all of a sudden we didn't care about age anymore and we only cared about height? So we wanted to summarize the behavior of the distribution across only the height variable. In order to do this, we need to find what's called the marginal distribution of height. It's really just a distribution of one variable while completely ignoring the other one. These are useful for summarizing the behavior of one variable at a time. So to find the marginal distribution for the heights, we simply add over each height value all the probabilities. So in other words, we are adding each column, and that value corresponds to each of the heights. So for example, for 45 it's 110, for 46 it's 2 tenths, so 47 it's 2 tenths, for 48 is 0 because the column is all 0, for 49 is 3 tenths, and for 50 is 1 tenth plus 1 tenth, which is 2 tenths. And the formula is over here, P of y of yj, where yj is the sum of all pxy of xi yj. That's the same as saying that we're taking the sum over each column. So here's a small quiz. Let's find the formula for p of y of 50. And the formula is the sum over all these columns. So it's basically the sum over I of pxy of xi 50. And it's actually 2 divided by 10 because that's the sum of that column. Now let's say we care about age. So we forget about the height and we want to find the distribution of age. The formula is very similar. We're adding over every row and we obtain 3 tenths, 2 tenths, 4 tenths, which is 3 tenths plus 1 tenth, and 1 tenth. And the formula is P of x of xi equals the summation over all j, that's the elements in the row, of the corresponding probability of xi yj. So for example, what is px of 7? Well, it's going to be 3 tenths because it's the sum of that entire row. Now this probability distribution right here is the marginal distribution for age, and this one is the marginal distribution for height. Now let's expand the data set to 50 children, and this is the corresponding scatter plot. Notice that there is shading in the plots because there may be more than one child here. So more children are 10 and 50 inches tall, hence the darkest spot compared to the one over here with age 11 and 62 inches tall. Overlaying the plot with a heat grid, we can clearly see sections where there are more counts of children for a specific data point. The marginal age will be obtained by summing across the vertical axis, and those for height will be obtained by summing across the horizontal axis. So earlier we saw an example where x was the number rolled on the first eye and y the number rolled on the second one, and we have this joint probability where it's a table full of 1 over 36s like this. When we want to generate the marginal one over x, we simply add over every row and we get 1/6. And the margin over y, same thing, we get a bunch of 1/6. And that's what we started with, right? Because originally we said that the probability of each value is 1/6 for the first and for the second dice. But now let's look at a slightly more complicated one. The one where x was the number rolled on the first dice and y was the sum of the two dice. For this one, we had this distribution over here. Now, let's say that we want to aggregate over the rows, because now we want the distribution for the sum of the two dice. So we add over the rows and we get the values 1/36, 2/36, etc., etc., all the way to 1/36 again. And the histogram is like this because many more pairs add to 7 than they add to, say, 2 or 3. So the formula is this one over here, and let's see, what do you think is py of 10? Well, when we add over the 10th row, we get 3/36. So the probability that the sum of two dice is 10 is 3/36. This is something we saw a while ago, but now we went to two variables and then back to one. And this is the histogram for only the distribution y, which is obtained from that table. Let's go back to the call center example where we had time on the horizontal axis and the customer rating on the vertical axis. And recall that we can find two marginal distributions. The one for waiting time, which is obtained by aggregating over every column, and the one for rating, which is obtained by aggregating over every row. Now recall that with marginal distributions, the goal is to reduce a highly dimensional distribution into one of less dimensions. In other words, here we have a two-dimensional one, which has two variables, and we want to bring it back to one dimension, that's one variable. So how do we reduce this in, for example, the time dimension for waiting time? Well, we sum up all the probabilities along the waiting time axis, and we get a histogram similar to this, which actually gives us this probability distribution. So that's the slice that we take if we cut that graph with a plane parallel to the waiting time axis. Now recall the simple data set of ages and heights of children. We generate our marginal distribution over the x variables age and the y variables of height. And with a marginal distribution, we were summarizing the behavior of the distribution across only one variable, say height, because we just forgot about age and we added all the values of ages for one height. But now, what if we wanted something different? We want to observe one variable given that the value of the other one is known. For example, let's say that we only care about age 9. That's the only one we care about, and we want to find the distribution across the height variable. That's called the conditional distribution. And this one is simpler. All you have to do is take a slice. So if you fix x equals 9, that means I'm fixing age equals 9, then I'm only looking at this row. Of the whole table, I only care about that row, and that is my probability distribution of height for kids of age 9. So if I want to find, for example, p of y given x equals 9 of 49, then that's going to be this value over here. However, there's a small caveat. Notice that in a probability distribution, everything has to add to 1. The numbers in this row do not add to 1 because they add to 4/10. That's 3/10 plus 1/10. So what can I do? Well, I can normalize. I can divide everything by the row sum, and I get 3/4 and 1/4. And so my probability that y equals 49, given that x equals 9, is now 3/4. Now remember that we had this formula, the probability of a and b is p of a times p of b given a. If we look at a and b as x equals 9 and y equals 49, then we have this formula over here. And we can rewrite it like this, where this p of x equals 9 was the row sum. So normalizing and dividing by the row sum is actually applying the conditional probability rule. So in other words, we obtain that p of y equals 49, that's the height, given that x equals 9, given that the age is 9, is 3/10 over 4/10, which is 3/4. That's this 3/4 we obtained over here. The general formula is this one. P of y given that x takes as value small x of y is the joint probability distribution P of xy divided by the marginal distribution Px of x. So remember this formula. This is the formula for a discrete conditional distribution. The top is the joint PDF. This is the conditional PDF that we're going to call, and this is the marginal distribution of x. Let's see another example. On this example over here, very simple example where x is the value of one dice and y is the value of the other one, then if we wanted to say, for example, if the first dice takes the value 4, what is the probability that the second one takes the value 1? Well, it's this formula over here, which really means take this row and forget about the rest of the table, but now normalize by dividing by 1 over 6 to turn the row from 1 over 36s to 1 over 6s, and you get 1 over 6, which is precisely what we expect the probability to be. Let's go back to the example of the phone calls with waiting time and customer rating. If I want to take, for example, the marginal distribution over the customers that gave a particular customer rating of, say, 3.5, all I have to do is take this slice over here. Now remember that the density function was like this. So for example, if I want to find the probability distribution for a rating, given that the waiting time was, say, 4 minutes, what I have to do is take a slice at a waiting time of 4 minutes and look at the plot in there. In other words, you take a slice, and this is the slice over here, and the curve that you obtain on the slice is the conditional distribution. Well, actually it's not, because you have to normalize it, but when you normalize it, you actually get the conditional PDF of y given x equals 4. So recall that for a discrete conditional distribution, this was the formula where this is the joint PDF, this is the conditional PDF, and this is the marginal distribution of x. Well, the same thing happens for continuous conditional distribution, except now we change the probability mass functions to probability density functions. So we change the p's to f's.
Let's go back to the example of two variables, age and height. Each distribution has its own expected value and its own variance, but there's something here that we haven't captured, which is the relation between the two. As you can imagine, age and height are somewhat related because the older someone is, the taller they are, or similar things. How do we capture that? We capture it with a very important concept called covariance. There's also another concept called correlation. This is what you're going to learn in this video.
So sometimes we want to know how two random variables are related to each other. Having a good understanding of these relations helps us build accurate models and make better decisions. So consider the discrete random variable x, which is the age of a child, and let's consider three random discrete variables. y1 is the height of the child in inches, y2 are the grades in some particular test, and y3 is the number of naps per day. And we're given some data as follows. And the question is, how is x compared to any of the three y variables, and how do you compare these relations? So to help us better visualize what's going on in each of these data sets, let's actually generate scatter plots for each, where the horizontal axis is x and the vertical axis is y1, y2, or y3. So the first plot is like this, the second one is like this, and the third one is like this. And I'm sure you can start seeing some kind of pattern. How do you think these relate? Well, first let's look at some metric. For the age versus height one, we can look at both of the means. The mean of the age, which is 10.5, and the mean of the heights, which is 60, and that's this point in the middle. The point 10.5, 60 is the point where you would balance these points. For age versus grades, it's this point in the middle where mean of x is 10.5 again and the mean of y is 5. And for this one over here, age versus naps per day is 10.5 for the age and 3.7 naps per day as an average. Now we can also look at the variances. Let's look at the x variance, which means we forget about the y coordinate and calculate the three variances, which are 9.17 because it's the same data set for ages. And now let's look at the y coordinates only, and calculate the three variances, which are 39.56, 9.78, and 7.57. So we have some information about each of the means and each of the variances. However, I'm sure you see something else going on. The age versus height one is almost a diagonal that goes up to the right. The age versus naps is the opposite, it goes to the bottom, and the age versus grades is kind of all over the place. That can be captured in something called the covariance. The covariance of the first plot is bigger than 0, the covariance of the second plot is almost 0, and the covariance of the third plot is less than 0. And the covariance talks about the relation between the two. As you can imagine, the older the child is, the more height they have, and that explains the first plot. Age and grades seem to not be very related. You can be old or young and have high or low grades, but they're not related. And age and naps per day are the opposite. The older you are as a kid, the less naps you're going to have per day. So that's what covariance really summarizes. Now, how do we calculate covariance? Well, the first step is, as usual, to center the graphs. So let's actually subtract the mean of x from the x coordinates and the mean of y from the y coordinates in order to get this center point to be at the origin. And then let's also divide by the standard deviation of x and of y in order to have these really nice plots where the x variance and the y variance are both 1. Now that we have that, let's try to cook up a formula that captures this trend over here and this trend over here and the lack of trends in the middle. So what would this formula be? Well, let's look at the plot in the left. It seems that when you move to the right, the coordinates move up. On the one in the middle, there seems to be no rule. And on the one on the right, if you move to the right, the coordinates move down. So let's try to capture this as some numbers that could be positive or negative. Let's look at age versus height. When you move to the right by x, you move up by y, and when you move to the left by x, you move down by a quantity y. So the quantities always have the same sign. If I move to the right on some sign, positive or negative, then the points move up or down by the same sign, positive or negative. Let's look at the coordinates in the points in the left. Some of them have a positive x coordinate and also a positive y coordinate, and some of them have a negative x coordinate and also a negative y coordinate. In other words, the coordinates of x and y tend to be the same sign. Maybe not for every point, but for the majority, the coordinate of x and the coordinate of y are the same sign. The opposite things happen on the left graph. When you have a negative x coordinate, you have a positive y coordinate, and when you have a positive x coordinate, then you have a negative y coordinate. So they tend to have a different sign. And for the age versus grade ones, the one in the middle, nothing seems to happen. Sometimes the x coordinate is positive and the y one is positive, but sometimes the x one is negative and the y one is positive. It seems like a land with no rules, so anything can happen here. So now let's look at the product of coordinates, because on the left, the coordinates normally have the same sign. So the product of coordinates is normally a positive number. On the one on the right, the coordinates normally have a different sign, so their product is a negative number, because positive times negative or negative times positive is negative. And for the one in the middle, well, we can have both positive numbers and negative numbers because anything can happen. Now, what if I were to add all these products of coordinates for each number? Well, in the left, I'm going to get something positive. In the right, I'm going to get something negative. And in the middle, I may get something close to 0. Maybe positive or negative, but probably close to 0 because I'm adding things that also cancel with others. And this sum is called the covariance. So we get to the important formula here, which is covariance. It's going to tell us if one variable makes the other one grow or makes it decrease, or if it doesn't do anything to the other variable. But it's not exactly the sum of the products x, y. It's almost that. It's actually this number. First, you have to center the data, and then you take the average of all these products. And covariance is going to be the one to tell us if the first variable makes the other one grow, such as age and height, if the first variable does nothing to the other variable, which is age and grades, or if the first variable makes the second variable decrease, like age and naps per day. Now we're ready to do some calculations. Here is the table of age and height, which recall it had a covariance bigger than 0. This is the mean of ages and the mean of heights. And what we're going to do is first center the data. So let's subtract the mean of age from all the ages and the mean of heights from all the heights, and then multiply these two columns to get this. And when we add it and take the average, we get 170 divided by 10, which is 17. This covariance is 17 because the data is positively correlated in the sense that when age grows, height grows. Now let's do age and naps per day. That's the one that was negatively correlated. It has covariance negative. Here's again the mu of x, the mu of y. Here's age, here's naps, here's the centered age and the centered naps per day. And the product of these two columns is this. As you can see, all the numbers are negative, is a sum of minus 74.5. When we take the average, we divide by 10 because there's 10 kids, and we get a covariance of negative 7.45. That is negative because, as you know, the higher the age, the less naps per day. And finally, we can do the covariance formula for the age versus grades distribution. Here are all the numbers: the age, the grades, the centered age, the centered grades, the product of the two centered coordinates, and that sum is going to be 1. And when we divide by 10, we get that covariance is 1 over 10, or 0.1, which is very close to 0. So one of them doesn't have influence over the other one, or at least very, very little influence, for the fact that the covariance is very small. So a small summary: we have 3 pairs of variables. The ones that grow together have a positive covariance of 17, age versus height. The ones that look independent from each other have a covariance of 0.1, very small. And the ones that seem to be negatively correlated have a covariance of negative 7.45, which is less than 0. Consider the following scenario. Players X and Y are playing 3 games to either win or lose $1. In game 1, there are 2 possible outcomes. Both players win $1 each, or both players lose $1 each. Here are the 2 possibilities. Either they both win $1 or they both lose $1, where the horizontal coordinate is how one player does and the vertical coordinate is how the other player does. And each one happens with probability 1/2. In game 2, 2 things can happen. The first player can win $1 and the second one loses $1, or the first one loses $1 and the second one wins $1. And we're calling these players X and Y, remember. So X is the first player and Y is the second player. The plot for this one is over here, where half of the times it happens that one player wins $1 and the other one loses it, and the other half the time one player loses $1 and the other one wins it. And both with probability 1/2. So recall that the X coordinate tells you what the first player wins or loses, and the Y coordinate what the second one wins or loses. And in game 3, more can happen. So actually, both players can win $1, both players can lose $1, one player can win and the other one loses, or the other player wins and the first one loses. So 4 possibilities, basically, A, B, C, and D, all with probability 1/4. So here is a question for you. How similar are these 3 games for player X and for player Y? Well, let's examine them. And first, we're going to examine them independently. So X is how much money in dollars player X wins, and Y is how much money in dollars player Y wins. So let's first look at how much X makes in the first game. And as you may imagine, it's going to be the expected value. And we're only looking at the horizontal coordinate because we're looking at player 1. So it can be winning $1 with probability 1/2 or losing $1 with probability 1/2, and that's 0. So the expected value for the first player is 0. And the same thing for the second player. They win $1 or lose $1 with probability 1/2. The same thing happens for the second game. For the second game, for the first player, they can win $1 or lose $1. That's 0. And for the second player, they can win $1 or lose $1. So again, it's 0. And so this game has the same expectancy for the first and second player. Now, the third game, let's take a look. 4 things can happen. You can win $1 or win another dollar, or you can lose a dollar or lose another dollar, and that again adds to 0. And the same thing for the second player. They can win a dollar 2 times or lose a dollar 2 times, all with the same probabilities. So these games are basically the same if you only think of one player at a time in terms of expectancy. Every player, at the end of the day, if they play many times, they're gonna end up winning 0. And so these expectancies don't really tell these games apart. Now what happens with the variance? Could it be that the variance can help us? Well, let's calculate the variance of each of the games. For the first game, this is the calculation of the variance. Recall that the expected value is 0. So all we care is the expected value of x1 squared, and that's going to be 1. And I'll spare you of the calculations, but it's actually going to be 1 for all of these ones. So these games are pretty similar in terms of expectancy and in terms of x variance and in terms of y variance. But obviously, they are different games. However, where does the difference lie? The difference lies in that you have to look at both players at the same time. Otherwise, the game is the same for each player. For each player, just win a dollar or lose a dollar. So we need to look at the covariance. The covariance is going to tell these 3 games apart. And recall that this was the formula for the covariance of a data set, and we're going to calculate it for the 3 games. So let's do it for game 1. Here is x and y. Now we center x and y, which nothing changes because the mu of x and the mu of y are 0. And when we multiply them, look at what happens. We have a 1 and a 1 because either they both win a dollar or they both lose a dollar. So the products are 1. And when we add this, we're going to get 2. And the average is going to be 1 because we have to divide this by 2. So the covariance of the first game is 1. And the fact that the covariance is positive shows this correlation here, that the more player 1 wins, the more player 2 wins. So either they both happy or they both sad. Now let's look at game 2, which is the complete opposite. When one is happy, the other one is sad, and when one is sad, the other one is happy. Again, these are the means, they're both 0, and in our table, then either one wins 1 and the other one loses 1, or vice versa. The product of these 2 things is going to always be -1, because 1 times -1 is equal to -1, and -1 times 1 is equal to -1. So when we add them, we get -2, and when we take the average, we get -1. So this one has a covariance of -1, which is reflected in the fact that they kind of form this pattern over this diagonal, and that means that either one is happy and the other one is sad, or one is sad and the other one is happy. And finally, game 3, we're going to do the calculation. In game 3, 4 things can happen. They both win, they both lose, or one wins and the other loses, or vice versa. Again, we saw that the mu's are 0, so we're going to do this table where these are the possible things that happen to x, these are the possible things that can happen to y. Centering makes no difference because the means are 0, and when we multiply them, we get 2 1s and 2 -1s. We get all the possible 4 scenarios. This is going to be 0, and when we divide it, in order to get the average, we get 0 again. So this covariance is 0, and that shows the fact that there's not really a pattern among these. They have all the 4 possibilities, so we can't really infer. If we know that one player is happy, we don't know if the other one is happy or sad, and vice versa, because they are more independent of each other. So in other words, we have these 3 games. Game 1, Game 2, and Game 3. In Game 1, they both win or both lose at the same time. In Game 2 is more of a zero-sum game. One wins and the other one loses. And in Game 3, anything can happen. And in the first game, we had a covariance of 1. In the second one, a covariance of -1. And in the third one, a covariance of 0. Now let's introduce one more game, Game 4. Game 4 has the following 3 outcomes. Either both players win $1 each, or both players lose $1 each, or neither player wins nor loses anything. So these 3 things can happen. Both players win $1, both players lose $1, and nothing happens. But the probabilities are unequal. So the probability of both players win $1 is 1/2. The probability of both players lose $1 is 1/3, and the probability that nothing happens is 1/6. And these are illustrated over here. So now if we look at only one player, the X player, what is the expected value of their gain? Well, it's going to be the weighted average of the values, which is going to be 1/6, and the same thing for the other player. It's going to be 1/6. So each player wins on average 1/6 every time they play this game. Now let's look at the variance. The variance is calculated like this, and we can do this calculation, which is 1/2 times 1 minus a 6 square plus a 6 times 0 minus a 6 square plus a 1/3 times minus 1 minus a 6 square, because we have to subtract mu and then square and then multiply with the probabilities, and we get 0.806. So the X variance is 0.806, as you can imagine, is the same as the Y variance. And what's the covariance? Well, let's calculate it. Now, we used to say that the covariance was the average of the product of coordinates, but that's when we had equal probabilities. That was way back in the day. Now we don't have equal probabilities. We have that 1/2, a 1/6, and a 1/3. So what we have to do is multiply by the probabilities. So this is what happens in general. You simply multiply by the probability the product of the X coordinate and the Y coordinate. Covariance of xy can also be expressed like this, which is actually very similar to the variance formula, except you have a different x and a y. If you were to say covariance of xx, you get e of x squared minus e of x all squared, and that's the same as the variance. So if we're going to calculate this, we just do the probabilities times the x coordinate times the y coordinate after centering them, and recall that these are the means and the variances. So we get this calculation over here. This over here is for the first point, and the covariance xy is 0.806. So as you can see, it's a positive covariance because they win and lose together. So there's that sort of diagonal that shows that the result of player A can help us infer the result of player B. Now let's go back to the example of the phone calls with waiting time and customer rating. Recall that we had two marginal distributions x and y, and now we want to find the covariance. So I want you to try to guess. Do you think this covariance is going to be positive or negative? And my guess is that it's going to be negative, because as you can see, we have sort of a diagonal that goes down and to the right, and that means negative covariance, because you can imagine that the more you wait, the less rating you would put, and the less you wait, the more rating you would put. So these are inversely correlated, and therefore the covariance is probably going to be negative. But let's actually calculate it. When we find the expectation of xy, we find it to be 18.014 minus the product of expectations of x and y, and that's going to be negative 7.878. So indeed, it is negative. Let me repeat this calculation for clarity. Here is the formula for covariance, and here is what we've calculated to be the two expectations of x and y and the expectation of xy. So the covariance is simply e of xy minus ex ey. That is minus 7.878. So far we looked at several examples where we've calculated the variance of the covariance of joint distributions. We looked at the discrete joint distributions with age of children and height, grades, and naps. And we got the following variances and covariances. We also saw three different games with the same variances, the same expectations, and covariance of 1, minus 1, and 0. And finally, we looked at the data set of waiting time and customer ratings, and we noticed that it has a negative covariance because the higher the waiting time, the lower the ratings. So now what we want to do is we want to put all these things together. And imagine that we have a very large data set with, say, 5 variables. How would the covariances work here? Well, we have the variance of each one of them separately and the covariances of each of the pairs. So we would have 10 pairs over here. And that's going to be the covariance matrix. So the covariance matrix simply has the variances in the diagonal. That's the variance of x here, the variance of y, and the covariances on the anti-diagonal. Capturing this in matrix form will look as follows. So for example, the covariance matrix of this data set is this matrix over here. The covariance matrix is very, very useful in statistics and also in machine learning. So let's look at the covariance matrix for the age versus height one. It's gonna be this matrix over here. Now let's look at the one for the game examples. They are these two for games 1 and 2. And finally, let's say we had 3 variables. So for a data set with 3 variables, we're going to have a 3 by 3 covariance matrix, where in the main diagonal, we're going to have the variances, and in the other coordinates, we're going to have the corresponding covariances. So for example, in the coordinate xy, we're going to have the covariance of xy. In the coordinates xz, we have the covariance of xz, etc., etc. And again, if we have 5 variables, then we're going to have a 5 by 5 covariance matrix, where in the main diagonal we have all the variances, and in the other places we have the corresponding covariance of the row variable and the column variable. This matrix is going to be called sigma, the covariance matrix. Now consider these two data sets shown here that you've already seen before, with their variances and their covariances. We know that the covariance tells us how the variations of the two variables are related. When this is a positive value, it tells us that both variables tend to increase together, and when it's negative, it tells us that when one increases, the other one decreases. But notice that one is a bigger number than the other one. Forget about the signs. One is 17 and the other one is 7.45. Does that mean that the correlation is stronger for the one that is 17? Well, we cannot really tell because the covariance can assume any value with no limited range. So consider these two data sets shown here that you've already seen before, age versus naps and age versus height. Age versus naps has a negative covariance and age versus height has a positive covariance. And the reason is because the more you age, the less naps you take, and in here, the more you age, the more you grow. However, because of 17 is bigger than 7.45, forgetting about the sign, does that mean that the correlation here is stronger? And we can't really tell that, because it could be that the numbers on the right are just much bigger numbers. So the question is, how could we tell the actual correlation between the two? So what I'm going to show you is something called the correlation coefficient. The correlation coefficient is a number that lies between -1 and 1. -1 is when you have two variables that are completely negatively correlated. +1 is when you have two variables that are completely positively correlated, and 0 is when they're completely independent. And it's always a number between 1 and -1. So these two numbers don't really fit in here, but after standardizing, they will. So let me show you the formula for the correlation coefficient. And the correlation coefficient is simply the covariance except divided by sigma x, sigma y. So it's a standardized covariance. We can also write this as covariance of xy divided by square root of variance of x, square root of variance of y. Now let's calculate it for this data set over here. When we take the covariance and divide it by the square root of the two variances, we get -0.894, which is close to -1, which means that these are pretty close to being completely negatively correlated. And for age versus height, then we have that the correlation is 17 divided by square root of 9.17, square root of 39.56, and that's 0.893, which means they're pretty closely correlated. And so we have correlation coefficients of -0.894 for the one on the left and 0.893 for the one in the right. Notice that despite the big difference in magnitude of the covariances of these data sets, the magnitude of the correlation coefficient is always small. It's always between -1 and 1. And we can see from the graph that it's pretty close to a straight line from the data points. So the only difference here is the direction of the diagonal, which shows the sign of the correlation coefficient. When we calculate the correlation coefficient for the other example, the one of age and grades, we actually get a very small number. We get 0.1 divided by the two variances, which is 0.01, showing that these two are definitely uncorrelated. Finally, let's calculate the correlation coefficient for the data and waiting times and customer rating. That is covariance divided by the product of the square roots of variances, which is negative 0.845, which shows that it is indeed pretty negatively correlated. To summarize, the correlation coefficient is the ratio between the covariance of the two variables and the product of the standard deviations. That is, the product of the square roots of the variances. It's always between -1 and 1. It's -1 when we pretty much have the diagonal y equals minus x. It's 0 when we have something completely uncorrelated. And it's 1 where we pretty much have the diagonal y equals x. Correlation coefficient is very, very useful in statistics when you're comparing pairs of variables. Next, you'll find a short lab based on a couple of famous datasets. These examples will show you some instances where statistical measures like mean, variance, and correlation don't tell the whole story. Enjoy exploring this short lab, and I'll see you once you're done.
Hello and welcome back to course 3 of the Math for Machine Learning and Data Science specialization. So this is the first lesson in the third week of the Probability and Statistics course, and we're going to be focusing on statistics for the second half of the course. To get us started, we're going to talk about two key concepts that are essential to understand in statistics: the concept of a population and the concept of a sample. A population is the entire group or individuals or items that we want to study. And a sample is a smaller subset that we actually observe or measure. So for example, if I'm trying to measure the height of all the humans, well, all the humans are the population, but obviously I'm not going to measure everybody. I'm going to take a sample of 100 of them, for example. That's our sample. In machine learning and data science, we often use samples to train models and make predictions because we can't look at the entire universe of data. So it's important to understand the difference between the two and how they're relevant to the work we do. So let's dive in and explore these together.
So welcome to the beautiful island of Statistopia, where you've been hired as a data scientist to help them with all their statistics problem. The first task is to find the average height of the people living in Statistopia. So you think to yourself, easy peasy lemon squeezy, I know how to calculate averages. I'm going to ask everyone on the island for their height and then divide by the total number of people. So you check how many people live in the island and you're told that it's 10,000 people. That's a lot of people, so not so easy peasy lemon squeezy anymore. How do you calculate the average of the heights if there's so many people? So you have to change strategies and only ask a few people living on the island in order to estimate the average. So all the subjects of interest in the study, the people living in Statistopia, are your population. And if you randomly select a subset of the population, say if size 100, then that subset is the sample. In this example, the population size is 10,000 denoted by n, and the sample size could be anything smaller from 1 to 9,999. That's denoted by small n, and we're going to try to pick a number that is small enough to be manageable but also large enough to be significant. For simplicity and illustration's sake, let's assume that there's only 10 people on Statistopia, meaning the population size is 10. Now you want to take 4 for your study. Let me show you two ways to do it. The first one is to pick 4 random people, and the second one is to put them on a line from shorter to taller and pick the first 4 people. So which one do you think is good and which one do you think is bad? So if you thought that the first one was better, that is correct, because you always want to take random samples. The second way to do it would probably get you a smaller average because you're taking the shorter people in the line. Now let me show you another example. Let's say you pick 4 random people. And let's say you want to run the experiment again. So you take another 4 people. Well, that's not good. Why not? Because you took the first sample set at random, but the second one depends on the first one because you couldn't repeat the people. And that's not good. You can't do that. So why is the sample set 2 not a good sample? Because it is dependent on the first one. You have to start all over every time. So people are allowed to be repeated. And that is very important. Otherwise, the second sample set depends on the first one, and that ruins your experiment. Another thing that you need to make sure is that the samples are identically distributed. So whatever rule you use to pick the first one needs to be the same rule you use to pick the second one. If you were to go to a particular part of town where people are taller or shorter, then you're not going to get a good sample. So you have to make sure your samples are all independent and identically distributed. Let's test your knowledge of populations and samples with this example. The example is the avocado toast trend, a popular trend that involves spreading mashed or sliced avocados on top of your toast. Trends can have a significant impact on the economic value of goods. So after the avocado toast trend, you decide to study the price of avocados in the US. You simply can't check every single purchase of avocados in the US, so you randomly pick 4 stores and record the prices for each avocado sale. What do you think is the population in this example? So the population of the study is all the avocados sold in the US. Now what is the sample? And the sample is the avocados sold by the 4 stores you selected. Alright, so let's check some implications of populations and samples in machine learning. In machine learning, every data set you work with is actually a sample and not the population, no matter how big the data set is. For example, when working with classification of cat images from all the infinite possible images of cats and not cats, your data set is simply a sample. It is important to have a representative data set though, as you also saw in the height example of the population of Statistopia. Having a representative dataset means that distribution of your dataset is the same as the one for the population. For example, if you're working on a classification model for cats and all your cat photos are cats in grass, then when you show a cow standing in the grass, it might learn to say it's a cat because it learns to associate it with grass. Or if you see a cat on a couch, it won't recognize it because it doesn't see grass. So it's essential to have a variety of cat images and a variety of non-cat images. Now let's end the session with a recap of the formal definitions of the terms you have learned. Population is the entire set of individuals or elements that you want to study that share a common behavior. A sample is a subset of the population that you use to draw conclusions about the population as a whole. Uppercase N is used to denote population size, and lowercase n is used to denote the sample size.
So let's say you have the entire world population and you're looking at everyone's height. So if you want to find the average height of the population, or at least estimate it, you can take a small sample of the population, calculate the average of the heights here, and that's an estimate for the average of the height of the total population. You can do this with other things, such as proportions. However, when you try to do it with the variance, something fails. If I take a small sample of the data set, calculate the variance here, I don't get the variance of the original data set, but I do get something very close. Let me show you.
So let's revisit the island of Statistopia again, and for simplicity assume that the population size is 10 as shown here, and the heights are shown over here. Now what is the average height in Statistopia? Well, we can calculate it like this very easily and get 160 centimeters. That is the population mean, and we're gonna call it mu. And that mu lies over here. Now, what if for some reason you can't record all the 10 people's heights? So as a result, you're only able to get 6 people, and you did so randomly. So let's say that your sample size was 6. Now, what is the estimate for the average height in Statistopia? Well, if you pick these 6 people, then it's going to be 160.97. That is a sample mean, which you're going to call X bar. And because it is the first sample we're taking, let's label this X bar, but actually underscore it with a 1. X1 bar is our first estimate. Now let's take another sample of 6 people and let's calculate their heights. So this one's going to be 156 centimeters. So we're going to call that X2 bar, and that's going to go here. And now let's compare X1 bar and X2 bar. Both of these have a sample size of 6, but which one's the better estimate for the population mean? Well, X bar 1 is better, and this can be attributed to the fact that we did more random sampling. As you can see, the second set is formed by the 6 shortest people, so it's not a good sample. But what if instead of n equals 6, we picked n equals 2? What is the estimated average height in Statistopia using n equals 2? Well, let's pick two random people and we get 158 centimeters. That's going to be called x3 bar. As you can imagine, x1 bar is a better estimate than x3 bar because x1 bar used 6 people and x3 bar only used 2. So we're going to explore this phenomenon in more detail in the later lessons. But for now, it's good to know that the bigger the sample size, the better the estimate you're going to get from your sample of the population mean. So once again, for illustration's sake, imagine that there's only 10 people living in Statistopia. That means you have a population size of 10. Now everybody has some form of transportation as shown, either a car or a bicycle. Now, what proportion of the people own a bicycle? Well, to answer this question, we first need to identify everyone with a bicycle. Those are highlighted here. And we'll divide by the total number of people. So that's 4 divided by 10 or 40%. 40% is the proportion of the population that own a bicycle. And of course, this is assuming that everybody owns exactly one type of vehicle. This metric right here is called the population proportion, denoted by P. And the population proportion is the number of items with a given characteristic, X, divided by the population N. Now, what if you don't have access to the population size of 10 and you have to do it with randomly sampled data? So we're going to take a random sample of 6 people and let's calculate the proportion here. What proportion of people own a bike? Well, here it's going to be 2 divided by 6, so 33.3%. This metric is the sample proportion denoted by p hat, and notice that the sample proportion is some estimate of the population proportion p.
As you learned in week 2, variance is a measure of how spread out your data is, and it is related to how far points are from their mean. For example, consider this dataset of the heights of 5 people in centimeters. Each one is represented by one of these 5 dots. The dataset has a mean of 160 and the dots are relatively far away from that mean. This dataset, meanwhile, also has a mean of 160, but the dots are closer to that mean. Let's look at those two datasets side by side. The top dataset has a relatively smaller variance since all the samples are close to each other. And the bottom dataset has a relatively larger variance since the data points are more spread out. Now let's look at the actual formula for variance you learned in week 2. Variance is written as var x, or sigma squared, and it is the average over the population of size n of x minus mu, the quantity squared, where mu is your population mean. This is also just called the average square deviation from the mean. In statistics, however, you usually won't have access to the entire population. You'll only have a sample. In other words, you won't have mu, the population mean, and you won't have capital N, the population size. So the question is, how can you estimate the population variance when all you have is a sample? Let's see if we can come up with some estimation for the variance using only the stuff you've learned so far. Remember that variance is still an expectation, so it makes sense that we can use at least some of the techniques you've learned from the sample mean. Create a new variable y, which will be equal to x minus mu squared. I know this looks a little arbitrary, but consider this as just another random variable written as a function of the original variable x. Now you can make a copy of the expression for the variance of x and rewrite it like this: 1 over n multiplied by the sum of all the values of y. Now notice that this is simply the expected value or mean of the new variable y, and that means that this is the population mean of y. Now that you have rewritten this expression as a population mean, you can use the approach you learned before to get the expression for the sample mean. Specifically, if you have little n samples, just average those n values to create the sample mean. Note that I'm using both uppercase y and lowercase y. Remember that uppercase y refers to the random variable or population, and lowercase y represents observations or individual elements of the population. Now you can substitute x minus mu squared back to get an expression for the sample variance written only in terms of x. I'll add a hat on top of Rx to indicate that this is an estimate. This expression basically just took the population variance and replaced the big N, or total population, with little n, the size of the sample. That said, there is still the problem of the population mean mu appearing in this expression. It might make sense
that if you don't know the population variance, then you most likely don't know the population mean either. So for now, I'm going to cheat. I will simply replace it with the sample mean. This expression only uses values you'd have access to with a sample, and it seems to make intuitive sense that it would work. Do you think that I'll get away with cheating? Well, let's try it out on the examples you just saw. If you recall, the sample mean for both datasets was 160. Let's begin getting the sample variance of the top dataset. First, you'll divide by 5 because you have 5 points. And then you need to add all the square differences between each point and the sample mean, or 160 squared, which gives an estimated variance of 1.7. Now let's move on to the next dataset. Before we calculate, think to yourself, if the previous dataset has a sample variance of 1.7, what will the sample variance be in this dataset? If you guessed about 50, then you are correct. You could calculate it directly using the same formula. You could also guess by noticing the points are about 7 away from the sample mean on average, so the average square distance from the sample mean will be about 49, pretty close to the true value of 50.8. You usually don't need to calculate variances like this by hand, but doing them for small data sets can help reinforce the operations that some of these terms stand for. Now remember when I said earlier that you could just use the sample mean in your equation? Well, actually it turns out that introduced some errors that make this equation a little bit biased. That is a term in statistics that just means that the formula here will either over or underestimate the value it's targeting. In this case, this equation would slightly underestimate the true value of the population variance. This doesn't mean that our first estimation is wrong, but maybe we can improve this undershooting of variance. I want to show you an example to motivate a little change you can introduce to this formula to correct the error. Consider a game where you have 3 sheets of paper with the numbers 1, 2, and 3 written on them. You put them in a hat, and then randomly pull one out. You score as many points as are written on the sheet of paper. If you treat the outcome of this game like a random variable, then the population mean here is mu equals 1 plus 2 plus 3 divided by 3, which gives you 6 over 3, which is simply 2. Using the formula of the population variance, let's see what the population variance of this game would be. First, I'll list out 3 values of x. Next, I'll calculate x minus mu for all 3 values, which is just x minus 2, since that is the population mean. This gives values minus 1, 0, and 1. Finally, square each of these values to calculate x minus mu squared. This gives 1, 0, and 1. Summing all of these, you get 2. Divide by n, and you get 2 over 3. And that is the value you'll calculate for the population variance. Now let's say you decide to play the game twice, placing the sheet of paper you drew back after each game. The outcomes are samples with little n equals to 2. You'll use these samples to estimate the variance. Here's a list of every possible outcome of playing the game twice. And here's the equation for variance, which you could use to calculate the sample variance for each one of these samples. You can then average those variances to see if it's a good estimate for the population variance, which you just saw it's 2/3. First, calculate the mean of each sample, giving you the following values. Now, I'll add a column where I'll use the proposed estimation to calculate variances. Note, I'll use a little n or sample size of 2 in each of these calculations. Finally, I'll average all of these sample variances to see what the average estimated variance would be. It turns out to be 0.333 or 1/3. But you know that the population variance is supposed to be 2/3, so clearly there was an error here. Let's take several steps back to the point where I calculated the variance for each of the samples. Now, instead of using this variance formula, I will adjust the divisor by subtracting 1 to see the effect. So now, in the variance calculation, we're not dividing by n, we're dividing by n minus 1 instead. Let's call this new way to estimate variance s squared, since that is the most common way you'll see it in other sources. And why s? Well, because it's similar to sigma. Here are the new sample variances you would calculate using this formula. Now, taking the average of each of these sample variances, you now get 0.667 or 2/3. And of course, you know that that's the population variance value you were aiming for. So here is the sample variance expression you'll see most often, and the biggest challenge is that n-1 in the denominator. I'm not going to rigorously prove why using n-1 fixes the bias in the sample variance equation I showed you before, but just know this approach works in general. If you want your sample variance to be unbiased, you'll divide by n-1. That said, as n gets bigger, the difference matters less. If your sample size is 3, it's the difference between dividing by 3 or 2, which is a large difference. If your sample size is 1,000, then it's the difference between dividing by 1,000 and 999, which is not a very big difference. In fact, from a practitioner's point of view, if using n or n-1 makes a significant impact on your estimate of variance, then be careful. You might have bigger problems than deciding whether to divide by n or n-1, because it probably means you have a small sample size and should be wary of making strong conclusions. Finally, I want to clarify that some accepted statistical techniques use n in the denominator to estimate variance. For example, maximum likelihood estimation, which you will see in a coming lesson, technically divides by n. However, the S-square estimate where you divide by n-1 is the most common estimate of variance, and the one you'll see most frequently through the rest of the course. With that context and this new unbiased equation, let's go back to the earlier examples and see how much things change. Now let's replace 1 over n by 1 over n-1 to get the S-square estimation. Look into the first data set. In this case, now you go from a 1.7 estimation to an estimation of 2.125. And for the second data set, you go from a sample variance estimate of 50.8 up to 63.5. In both cases, the estimate increased slightly because you're now dividing by n-1 instead of n. To sum up, if you have access to the whole population, then the variance can be found by computing the average of the square difference between each value and the population mean. However, if you only have access to some data points or a sample, then you will most often use the S-squared estimate of variance. In this estimate, you find the average square difference between each value in the sample and the sample mean, but instead of dividing by n, the size of your sample, you divide by n-1. Dividing by n-1 corrects for the bias introduced by using the sample mean instead of the population mean. In a few contexts, you may see the estimation where n is used in the denominator. I'll call this estimator var hat or sigma squared hat. While this estimator has a small bias, which means its expected value is a little difference from the true population variance, it is still a pretty good estimation of variance and appears as part of using some common statistical techniques. That said, the S-square estimator will be the most common estimation of variance you'll see in this course and in practice when you need to estimate the variance of a population from a sample.
So let's stay with the example of height in the human population. Let's say that you want to find a good estimate of the average of the height of all humans. What's a cheap way to do this? We get one person, we measure them, and that's an estimate. It's a bit of a noisy estimate, so we can just take like maybe 2 or 3 people, take the average of their heights, and that's a slightly better estimate. I can do it with 10 people and get a better estimate, or 100 or 1,000. The more people I get, the better the estimate is. And that happens with other metrics, not just expected value. This is the law of large numbers. Let me tell you more about it.
So consider again this fair-sided dice whose possible outcomes are 1, 2, 3, and 4, and where the mean is 2.5. Now let's run an experiment again where we throw the dice twice and record the average. We get the following 16 outcomes of all the possible pairs of values we can obtain. And the average of each possible pair is going to be in this table over here. The mean of all these outcomes is the general population mean, which is 2.5. Now, let's draw samples from this population mean of all possible outcomes one at a time. So we start with 4, 3, and that gives us an average of 3.5. And we're going to point out that this is the population average of 2.5. So the mean of the first sample was x1 bar, which is over here. Now let's take 2 trials, 3, 4, and 1, 3. And let's take the mean of those. And now let's take 3 trials and the mean of those, and we plot it over here. And we can continue 4 trials, we put the mean, and etc, etc. And notice that the more samples that we take, the closer and closer that we get to the population mean. For example, if we draw 9 samples, we get 2.56 as an average, etc, etc. And notice that over here, we're already pretty close to the population mean of 2.5. This is an illustration of the law of large numbers, which says that as the sample size increases, the average of the sample will tend to get closer to the average of the entire population. So if n is the number of samples, and each x sub I is a random variable, and it represents a sample from the population, all x sub I must be independent and identically distributed, or IID for short, and they all have the same distribution as x. Then as n goes to infinity, then this average of the samples actually gets closer and closer and closer to the expected value of x, which is mu of x, the population mean. In other words, as n goes to infinity, this mean gets closer and closer to the population mean, and this happens under certain conditions. So the conditions are the following. First is that the samples must be drawn randomly from the population. Second, that the sample size must be sufficiently large. The larger the sample size, the more accurate the sample mean is likely to be. And third, that the individual observations in the sample must be independent of each other. And this is the law of large numbers.
So remember I told you before that the normal distribution appears in a lot of places? Here's one that perhaps you didn't expect. Take a distribution, any distribution. It can be as skewed as you want. Now, take a few samples, always the same number, and look at the average. And do this many times. And plot all these averages. Guess what you get? Yes, you get the normal distribution, no matter what distribution you started with in the first place. This is a fascinating result, and is one of the pinnacles of statistics. It's called the central limit theorem.
So let's start with an example of a discrete random variable that you've seen a lot of time in this course. The probability of heads and tails is the same, and the random variable x is the number of heads when a coin is flipped n times. So for one coin flip, it's x equals 1 for the case of heads and x equals 0 for the case of tails. And that's a discrete random variable with this probability distribution over here. A half for x equals 1 and a half for x equals 0, where the number of heads is in the horizontal axis and the probability is in the vertical axis. Now, what can we say about the probability distribution when the number of coin flips increases? Well, here's what happens with 2 coins. Here's what happens with 3 coins, with 4, and this is with 10. And as you can see, this looks a lot like a Gaussian or a normal distribution. Notice that counting the number of heads in n coin flips is the same as adding n Bernoulli variables, where each variable takes the value 1 if you see heads and 0 if you see tails. This is an example of the central limit theorem that says that as you increase the number of variables, you are adding the distribution of this sum. Your distribution looks more and more like the Gaussian distribution. Now, recall that in here, when we're tossing n coins with a probability of p, then the mean mu is np, which is n times the probability of heads, and the variance is np times 1 minus p, which is n times probability of heads times probability of tails. So, for the case n equals 1, we have that the mean is n times p, which is 1 times 0.5, and that's 0.5. That's the case when we have a fair coin. And the variance is n times p times 1 minus p, which is 0.25. So let's calculate the mean and variance for all these examples. For the first one, we have 0.5 and 0.25. For the second one, it's 1 and 0.5. For the third one, it's 1.5 and 0.75. Then 2 and 1. And for the 10th one, it's 5 and 2.5. Now, what are these numbers? Well, as n becomes sufficiently large, we get a normal distribution where the mean is np and the variance is np times 1 minus p, just as expected.
So let's see the central limit theorem in the context of another experiment. This time you'll consider a continuous random variable. Let's go back to the tech support line example you saw in week 1, lesson 2. Once you call the line, the operators can answer any time between 0 and 15 minutes, after which the call gets disconnected. You can define a random variable x that represents the wait time for a call to be answered. And in the example you saw on week 1, the variable follows a uniform distribution with parameters 0 and 15. Remember that a uniform distribution models situations where every interval of the same length has the same chance of occurring, which leads to a constant probability density function. Now you're interested in the mean wait time. To try to approximate it, you will average the waiting time of a different number of calls. This means that if you use just one sample, then that sample is the one used to approximate the mean. If you use 2 samples, you will average the waiting times for the 2 calls. For 3 samples, you will average the lengths of 3 calls, and so on. In general, if you record the waiting time on n calls, you can define the variable yn as the average of the wait time for all the n calls. Can you say anything about the distribution of yn? Well, let's start with n equals 1, where you're just averaging one wait time. Let's repeat this experiment of averaging one wait time many times to get a nice histogram and see the distribution. So, the histogram looks like this. It kind of looks like a uniform density from far away because each sample of y1 comes from a uniform 0 to 15 distribution. Of course, there are ups and downs. Now what happens for n equals 2? Well, now again you're averaging the wait time for 2 calls. Again, repeat this experiment of averaging 2 wait times many times and you get a nice histogram to see the distribution. Now the density looks like a triangle. Note that it's almost symmetric around 7.5, which is the population mean of the wait times. Now let's move on to n equals 3. In this case, you're averaging the wait time for 3 calls and repeat this experiment many times until you get a nice histogram to see the distribution. Notice that it's starting to look more and more bell-shaped and is still symmetric around 7.5. Here it is for n equals 4, the population mean of 4 calls. And for 5, it's more bell-shaped and it also has lower dispersion. You can even draw the curves fitting this histogram. The green lines correspond to the kernel density estimation that you learned at the end of the previous lesson. As you can see, as n increases, these curves look more and more like the Gaussian probability density function. You could also ask yourself, what are the mean and variance of these variables yn? Well, let's start with the mean. The mean of yn is by definition the expectation of the average of n variables xi. By linearity of the expectation, this is the same as 1 over n times the sum of the expectations of each of the n variables. But since all variables are identically distributed, this is 1 over n times the mean of x, which is simply the mean of x. For the uniform distribution with parameters 0 and 15, this is 7.5. Now let's do the variance. For the variance, note that the constant 1 over n comes out of the variance, but it comes out squared. Also, because the variables are independent and the variance of the sum becomes the sum of the variances. This is not the general case and it's only valid due to independence here. And again, since all the xi are identically distributed, this is 1 over n squared times n times the variance of x, which is simply the variance of x divided by n. For the uniform distribution with parameters 0 and 15, you can look up the variance, which is 18.75. It is super interesting to know that as n grows, so does the variance of the average. This is exactly what you were seeing in the histograms. Now let's plot the probability density function for a Gaussian with the same mean and variance yn. The plots over here confirm our suspicion. These are the orange plots. Look how the green and orange lines fit together more closely as n increases. They're not so close for n equals 1 or 2, but by the time we get to 4 and 5, they're almost indistinguishable. It is pretty cool to see that we started with a uniform distribution for n equals 1 where the density of each point is the same and ended up with an almost Gaussian distribution with center at 7.5 after n is larger. If we were to increase n, then the distribution would get narrower and narrower around 7.5. When you average a large enough number of variables, the distribution will approximately follow a normal distribution.
It is worth mentioning at this point that while in this example it seems that even averaging 3 or 4 samples is enough to start seeing the normal distribution, this is not usually the case. In general, a safe rule is that you usually need about 30 variables before the bell-shaped distribution comes in. It all depends on the original distribution of the data. If the original population is very skewed, then you usually need more samples than if you were working with a symmetric distribution. In the case of the uniform distribution, the Gaussian PDF curve appears very quickly, as you saw in this example. Now, one of the most common ways to visualize this is by standardizing. This is because, as you can see, the mean is always the same as the population mean, but the variance depends on n. So it's easier to compare the distribution of yn for different values of n when you standardize this average. So by standardizing, you see that as n increases, the distribution of the average is close to a standard normal distribution. There's also one benefit in standardizing that will become very useful in the next week of content. If you don't actually know the value of the population mean and variance, then you know that as n increases, the average will approximately have a Gaussian distribution. But you don't really know of which parameters. Now, to wrap up, whenever you consider the average of n independent, identically distributed random variables, the mean of yn is the same as the population mean. And the variance of yn is the population variance divided by the number of variables you are averaging. So this is interesting. The mean stays the same, but the variance gets smaller and smaller. And this makes sense because the more variables you take, the more likely you're going to be closer to the population mean. So there is less spread and less variance. This result holds true no matter what the distribution of the original population is. Now let me give you the formal definition. Formally, the central limit theorem states that as n goes to infinity, the standardized average will follow a standard normal distribution. In practice, this is usually true for n around 30 or higher, sometimes even with smaller samples as the example you just saw. Another way you will sometimes see the CLT is in terms of sums rather than averages. You can easily arrive to this equation by taking the common factor 1 over n and rearranging terms properly. So you can also say that as n approaches infinity, the sum of n identically independent random variables minus n times the population mean and all that divided by the square root of n times the population standard deviation also distributes as a standard normal distribution. And this is the central limit theorem. Next, you'll find an ungraded lab in which you can see some of these ideas in practice. You'll use Python to take samples from many different distributions and see the central limit theorem in action. For most well-behaved distributions, even a sample of size 30 should lead to a pretty normally distributed sample mean. If your data is less well-behaved, however, you may need much larger samples to get an approximately normal distribution of sample means. The central limit theorem still applies, but it does take longer to kick in. Have fun getting hands-on with these concepts, and I'll see you afterwards for lesson 2 of this week.
Welcome to the second lesson of week 3. In this lesson, we will begin the journey to grasp the concept of estimation. Estimation is fundamental to statistics, and it comes in different flavors. So I will start with point estimation and introduce you to the most common point estimation method that's called maximum likelihood estimation, or MLE. This one is very popular in machine learning. I will also show you how MLE can be generalized using Bayes' theorem to a Bayesian version of a point estimator called the maximum a posteriori estimation. You will find in this lesson a very elegant result according to which MAP, or maximum a posteriori estimation, can be thought of a maximum likelihood estimate with regularization. Regularization being a commonly used method in machine learning to prevent overfitting. Let me show you in more detail. In this video, you're going to learn maximum likelihood estimation, or MLE. MLE is widely used in machine learning to train models. But the concept behind MLE is very simple. Imagine that you have some evidence of something and you want to find the scenario that may have led to that evidence. So you pick out of all the possible scenarios the one that created the evidence with the highest probability. Let me show you this with an example.
So imagine that you walk into a living room and you see a bunch of popcorn lying on the floor next to the couch. So here's a question for you. Which one of these events is more likely to have happened? People watching a movie, people playing board games, or somebody taking a nap. Which one do you think was more likely to have happened? Well, let's try to look at what led to popcorn with the highest probability. The probability that popcorn was on the floor after watching movies is high. For board games, it's medium, and for taking a nap, it's low, because taking a nap does not produce popcorn in the floor. So we're going to go for whatever created the popcorn with a higher probability, and that's movies. So we're going to infer that the most likely thing that happened is that people were watching movies. What we did was we maximized the conditional probability, because there's a probability of popcorn given movies, and that's high. There's a probability of popcorn given board games, which is medium, and the probability of popcorn given nap, which is low. So we found the highest conditional probability, and what we did, in other words, is to find the scenario that most likely leads to popcorn in the floor. This is called maximum likelihood. We picked the scenario that made the evidence more likely. This is actually what's done in machine learning many times. You have a bunch of data and several models that could have generated that data. And what you do is you estimate the probability that we see this data given model 1, the probability that we see this data given model 2, and given model 3, and whichever gives the highest probability is the model that we pick, the model that most likely produced the data. So in other words, we're maximizing probability of data given model. Now, why does linear regression fit in here? We're going to get into more details later, but to give you a vague idea, imagine that you have these as your data points and 3 possible models. And imagine that we had a way to generate points based on a line, and the points would be generated close to the line. So there's a probability that the points appear based on model 1, based on model 2, and based on model 3. And the model that gives these points the highest probability is the model that we're going to pick. But again, we're going to see this in more detail later. Let's go back to the coin example. Suppose that you toss a coin 10 times and it lands in heads 8 times and in tails twice. Now you have 3 possible coins that you could have flipped to get these results. Coin 1 has a probability of heads of 0.7. Coin 2 is a fair coin, has a probability of heads and tails of 0.5. And coin 3 has a probability of heads of 0.3. Now, which one do you think was the coin used for these 10 tosses? Or at least, which one would you use if you were aiming to generate those 10 tosses again? Well, let's take a look at the probability that the coin landed in 8 heads and 2 tails for each one of the coins. For coin 1 is the product of 0.7 to the 8 times 0.3 squared, which is 0.0051. It's quite small, but let's look at coin 2. Coin 2 is 0.5 to the 10, which is 0.0010, much smaller. And coin 3 is 0.3 to the 7 for all the heads and 0.7 squared for the tails, which is 0.00003. That's very, very small. Actually, the largest one is this one over here. So we conclude that if we had to pick one of the 3 coins, we should probably go with coin 1 as the most likely one to have generated this. What we did here was maximum likelihood. We want to generate 8 heads, 2 tails, and there's 3 possible coins that generated it. Coin 1 with 0.7 probability of heads, coin 2 with 0.5 probability of heads, and coin 3 with 0.3 probability of heads, and each one generated the data with some probability. Now, what's the coin that most likely produced 8 heads and 2 tails? Well, it's the one that maximizes probability of 8 heads, 2 tails given coin, and that is the first one because this conditional probability is highest for coin 1. So therefore, that's the one we pick. But could we do better? Is there a better coin that may work? Let's say that we pick some coin with probability P for heads and 1 minus P for tails. What's the probability then that this coin generates 8 heads and 2 tails? Well, it's P to the 8 times 1 minus P squared, which is that product. Now we want the P that maximizes the chances of seeing 8 heads and 2 tails. That's the likelihood. The likelihood is the probability of seeing this data based on the model, which is a coin with probability p. Notice that this is a function of p, so we have to actually maximize it. This is an example that we saw in the calculus class. And it turns out that we don't want to deal with products of many things, especially when we're talking about small numbers. Let's take the logarithm, which is a pretty standard trick we use to turn products into sums. And that turns the product p to the 8 times 1 minus p squared into 8 log p plus 2 log 1 minus p. And that's the log likelihood. So very often we're not going to try to maximize the likelihood, we're going to maximize the log likelihood, and maximizing one is the same as maximizing the other one, but log likelihood normally is a nicer function. So when we take the derivative with respect to p of the log likelihood, we get this over here. Remember that the derivative of logarithm of p is 1 over p, and for the second term we have a chain rule, and that minus 1 comes from that chain rule. If we want to make this equal to 0, then the optimal value is p hat equals 8 over 10. So actually, the best possible coin that would have generated these flips is a coin where the probability of heads is 8 over 10 or 80%. And that makes sense, right? Because the data has 8 heads and 2 tails. For the general case, let's do some math. Let's say you have 8 coins and k heads, and each coin is a Bernoulli variable with parameter p. That means that it has a probability of p of landing in heads. And the likelihood is given by this formula, which is the product of p to the xi 1 minus p to the 1 minus xi. And that's if xi equals 1, we have p, and if xi is equals 0, then we have 1 minus p. Now this is the number of heads, and this is the number of tails, and therefore we can factor this expression like this. Now the log likelihood is going to be the logarithm of this, and the exponents come down and we get this expression. And we want to maximize this expression. All we have to do is take the derivative and set it equals to 0. And that gives us an optimal value of p hat, which is precisely the mean of the population. So in other words, if we had, for example, k heads among this population of coins, then the optimal probability to obtain those k heads would be precisely k over n. Now let's look at a similar problem. Let's say that you have some observations, and they are the numbers 1 and minus 1. These observations were sampled from some distribution. And the question is, what distribution could they have been sampled from? Well, let's say we have 2 candidates, a normal distribution with mean 10 and standard deviation 1, and a normal distribution with mean 2 and standard deviation 1. So the question is, which one of these two do you think is more likely to have generated the observations? Well, let's take a look. Here we have the 2 observations, 1 and minus 1, and let's put them over here in the graph. Now let's look at the heights at those points of the curve. And the heights on top are very low, and the ones at the bottom are a little higher. Now it turns out that these heights are probabilities. Well, not exactly, they're likelihoods. And so you can see that the bottom curve, the one with mean 2, produces both points with a higher likelihood. Therefore, this one is the winner. So we're going to pick this one among the 2 candidates. The top one generates data with very low likelihood, whereas the bottom one generates it with much higher likelihood. So we conclude that among these 2, it's the bottom Gaussian, the one with mean 2 and standard deviation 1, the one that probably generated them. I'm going to look at 3 Gaussians, the one with mean minus 1 and standard deviation 1, the one with mean 0 standard deviation 1, and the one with mean 1 and standard deviation 1. So here are the 3 plots. Now let's test your intuition. Which one of these 3 do you think generated those 2 points? Well, let's take a look at the likelihoods. Well, first let's take a look at the Gaussians. The first one has a mu of minus 1, the second one a mu of 0, and the third one a mu of 1. And now let's see which one was more likely to have generated these 3 points. So let's actually plot the likelihoods. The likelihoods are these vertical bars that go from the point to the curve. And on the top one, the heights are 0.399 and 0.054. For the middle one, they're both 0.242, and for the bottom one, they're 0.054 and 0.399. Now the question is, which one of these 3 do we pick? Well, if there were probabilities, we would multiply them because these 2 points are independently generated. So because they're likelihoods, let's also multiply them. Let's take the product of these 2 numbers, 0.022, then the product of these 2 numbers, and the product of these 2 numbers. And which one is higher? The higher one is the one in the middle, which is 0.059. So we conclude that among these 3, the Gaussian distribution with mean 0 and standard deviation 1 is more likely. This one generated the data with a higher likelihood than the other 2, so that's the one that wins. Notice one more thing. The mean for the first one is -1. The mean for the second one is 0. And the mean for the third one is 1. Now, what is the mean for the original dataset, the dataset that was generated? It's 0. It's the same one as the one of the winning curve. And the reason is that the best distribution is the one where the mean of the distribution is the mean of the sample. Now let's go back to our 2 observations, and now that we've established that the best distribution has to have mean 0, then let's look at several distributions with mean 0. The first one has a standard deviation of 0.5, the second one a standard deviation of 1, and the third one a standard deviation of 2. And this is how they look. So these are their means and their standard deviations. And recall that all of them have a mean of 0 and standard deviations of 0.5, 1, and 2. Now here's a question to test your intuition. Which one of those 3 do you think was more likely to have generated the points 1 and -1? Well, let's do the same thing again. Let's plot the points over here and draw all these heights, which are likelihoods, and we're going to look at the product of the likelihoods and see which one wins. This one over here on top has heights of 0.044, the second one has heights of 0.242, and the third one has heights of 0.176. So when we multiply them, the highest product is the one in the middle, which is 0.059, and that's the best one. So the Gaussian distribution with mean 0 and standard deviation 1 is the most likely one to have generated that data. Among the 3 is the one that gives the data the highest likelihood. Now notice something else that's interesting. What is the variance of the observations? So the variance of the observations is calculated as the average of the squares of the distances from the mean, and that is going to be 1. Now, what is the variance of each one of the distributions? Well, the top one has variance 0.5 squared, the second one 1, and the third one 2 squared.
After this, you'll find a reading that goes deeper into how MLE is mathematically derived. Next, there's an interactive tool that shows you how maximum likelihood estimation works. You'll be able to simulate samples from both a binomial and a normal distribution and see how maximum likelihood estimation would be used to estimate the population parameters. Enjoy exploring this tool, and I'll see you afterwards to talk more about how these ideas get applied. So recall that a way that maximum likelihood is used in machine learning is the following. You have a bunch of data and some possible models that could have generated that data. And for each one of the models, you calculate the probability that the data appears based on model 1, model 2, and model 3. And the one that gives the highest probability is the winner. That means you find the model that most likely produced that data. The one with the highest probability is the winner. That's the one that maximizes P of data given model. And here's a small example with linear regression.
Let's say that these are your points and you're trying to fit a line to them, but let's not try to fit a line to them. Let's try to do it with probability. The candidates are model 1, that's this line, model 2, which is this line, and model 3, which is this line. So first of all, let's think, which one looks like the best fit? And the best fit is going to be the one that's going to give the highest probability. So the first one generates the data with some probability, the second one with some higher probability, and the third one with some medium probability. And the one that wins is this one. However, I haven't yet told you how a line can generate points. So let me tell you that next. The idea is that these lines generate points close to the line. Imagine it as a road. If you have that road being the yellow line and you start building houses, the houses are likely to be built close to the road and not far from it. So if the road is model 2, then the houses are likely to be in these points. And if the road is model 3, then the houses are likely to be around here. But let me put some numbers here. Let's say that this is your model and this is a point X and the point of the line is over here. So you're going to generate a point close to the line using a Gaussian. So we put a Gaussian and we center it at the point where the line meets the horizontal line. And we're going to sample out of that Gaussian. So we sample this one over here. So that's the same as saying we're going to build a house that is likely to be close to the road, and it's going to be sampled from that vertical Gaussian over there. Now, if we have a bunch of points, x1 up to x5, then we have 5 Gaussians all centered at the point on the blue line, and from each one of these, we're going to sample some point, and those are the 5 points that we're sampling based on this blue line. And now all we have to do is find the line that best produced the points, the one that most likely produced these points. And coincidentally, that's going to be the same best fit of a line from linear regression. Why is this the case? Well, let's do some math. Let's say that the line has equation y equals mx plus b, and these are the points of intersection with the line. And these are the generated points. Now, these distances are going to be called d1, d2, d3, d4, and d5. And first, let's calculate the likelihood of generating this point. Since we have a Gaussian, then what really happens is that the Gaussian is centered at the point where x1 intersects that blue line. And we're generating this other point over here. Now, if we assume that it's a Gaussian with standard deviation 1 and mean equals 0, then the likelihood of generating this point is given by the formula of the Gaussian, which is 1 over square root of 2 pi e to the minus 1/2 d1 squared. That is the likelihood of generating the first point. And we're looking at all of them. So that's the product of the 5 likelihoods. That's what we have to maximize. We have to maximize the likelihood of the line generating all those points. And since they're independent, then we have to look at the product. Now, a bunch of these things are constants, this 1 over square root of 2 pi. So let's forget about them and let's maximize this over here. Now we can factor this as e to the minus 1/2 times the sum of the squares of the di's. And notice that if we maximize something, that's the same as maximizing the logarithm. So we can get rid of this e and also to the 1/2 because that would just be multiplying by 2. But let's remember that we have a negative number here. So that means we have to minimize the sum of squares. And minimizing the sum of squares is precisely the least square error. This is exactly what linear regression is. In linear regression, you want to find the blue line that minimizes the sum of square distances from the point. So this shows that finding the line that most likely produces a point using maximum likelihood is exactly the same as minimizing the least square error using linear regression. Here are 3 examples of lines and the Gaussians that they generate at each point. And as you can see, when we calculate the likelihoods for the actual data set of blue points, the winning one is the one in the middle, which we can see is the best line fit for the data set. So first, let me tell you about regularization. Imagine that this is our data set and we have 3 models that could have generated that data set, or that could fit that data set, however you want to think about it. One is linear, the other one is a quadratic polynomial, and the other one is a polynomial of degree 10. And in order to find out which one was more likely to generate it, or which one is the best fit, we look at the loss, which could be the squared error. Now let's imagine that the losses here are 10, 2, and 0.1. Because as you can see, the first model didn't fit the data really well, the second model fitted a little better, and the third one fitted really well. So the third one is the one that wins. However, something tells us that it's not the third one that wins, it's more the second one. And what we're going to do is we're going to apply regularization to help us not pick that model 3, which is a little chaotic, even though it fits the data pretty well. So let's look at the equation, and I'm going to throw in some numbers. Let's say that the first one is the line y equals 4x plus 3, the second one is the quadratic 2x squared minus 4x plus 5, and the third one is this polynomial of degree 10. So what we're going to do is we're going to apply a penalty to each one of these models, and the more complicated the model, the higher the penalty. And in that way, we're trying to penalize model 3 a lot in order to not use it, because as you can see, model 3 is so chaotic that it fits the data really well, but it doesn't really generalize well. It doesn't really get the point of the data, which is kind of a quadratic that points upwards. So what's the penalty? Well, we're going to call it the L2 penalty. L2 regularization is what we're using here. And it's going to be the sum of the squares of all the coefficients of the polynomial except for the constant one. So this one is 4 squared, that's 16. This one over here is 2 squared plus minus 4 squared, which is 20. And this one over here is the sum of all these squares, which is going to be 266. And now the new loss is going to be the sum of the old loss and the penalty. So here's 26. Here it's 22, and here it's 262.1. So now the winner is model 2. So what we did here is we modified the loss and we penalized the models that are too complex. And in that way, we're sort of trying to find the simplest model that fits the data well. In general, if the model has this equation of a polynomial, and the log loss is, for example, LL, then the L2 regularization error is the sum of the squares of the coefficients that are not the last one, that are not the constant one. And we're going to have something called a regularization parameter, because sometimes we don't want to apply the full penalty. We want to multiply it by a small number in order to not be too drastic here. And the regularized error is simply the log loss plus the regularization parameter times the L2 regularization error. So that is, in a nutshell, what regularization is. But what does this have to do with probability and maximum likelihood? Let me show you soon. So let's go back to our example where we had some evidence, which was popcorn in the floor, and 3 possible scenarios, and we're trying to investigate which scenario happened. The first one is movies, which creates the popcorn with a high probability. The second one is board games, which creates popcorn with a medium probability. And the third one is a nap that creates popcorn with a very low probability. So we went for movies, which is the one that generated the evidence with the highest probability. But however, that's not the whole story. Imagine that now we have 2 different candidates. One is that we were watching movies, and the other one that there was a popcorn throwing contest. So movies create popcorn on the floor with high probability. But a popcorn throwing contest would create popcorn on the floor with a very high probability. It's almost for sure that if you have a popcorn throwing contest that you ended up with popcorn in the floor. So that's the winner. However, something tells us that movies should be the winner and not popcorn. Why? Well, one reason is that it's likely that you could have been watching movies. A popcorn throwing contest is not very likely. It's a very unlikely event.
So even though it's more likely to have generated the evidence, it's less likely to have happened on its own, and that should matter. And that should mean that we want to pick movies. But let's put some math here. Before, what we did is maximize the probability P of popcorn given scenario. So we figure out that P of popcorn given movies was higher than P of popcorn given contest. However, the probability that you're watching a movie by itself is actually higher than the probability that there was a popcorn contest. It's actually much higher. And so we should factor this into the equation. So we should actually multiply them. And when we have the product, then the inequality goes in the other direction. And it turns out that it's more likely to have watched a movie. Now notice that this looks familiar. P of popcorn given movies times P of movies resembles P of A given B times P of B, which, as we know, is the probability of A intersection B, the probability of A and B happening at the same time. So therefore, we're trying to maximize the probability that there's popcorn and a movie and the probability that there's popcorn and a contest. That's really what we care about. And that makes more sense because that's actually what we want to maximize, not just a conditional probability, but we want to maximize the probability that those two things happen.
Frequentist versus Bayesian is an age-old debate in statistics between two different broad philosophies. The root difference between the approach taken by Bayesians and the approach taken by frequentists lies in the way they interpret probabilities. I find it best to think about this with a little story. A frequentist and a Bayesian walk into a bar. They found a coin in the street, and they want to know its probability of landing heads. To do that, they toss the coin 10 times, getting 8 heads and 2 tails. The frequentist then says, easy, the probability of heads is 0.8. However, the Bayesian reflects a little more. From experience, they know that coins are almost always fair. So they have a pretty strong belief that the probability of heads should be around 0.5. Seeing the evidence, they are willing to adjust their belief, but not by much, so they may say something like 0.52. They still think the coin should be fair, but now they have a bit of evidence that suggests that maybe this is not entirely the case. The big difference between a frequentist and a Bayesian is that Bayesians introduced the idea of previous belief, also known as prior. That prior represents the statistician's belief before gathering samples. However, after getting some samples, they are willing to adjust their belief to account for whatever they just saw, if that aligns with their original beliefs or not. Let's see some of the conceptual differences between the frequentist and the Bayesian approach. They have different approaches when it comes to interpreting data and probabilities. For frequentists, probabilities represent the long-term frequency of events, meaning the frequency of times an event happens if you repeat the experiment infinitely many times. On the other hand, Bayesians think of probabilities as the degree of belief or certainty of an event. If something has a high probability of occurring, you can be pretty sure that it will happen. There's another thing that splits apart Bayesians and frequentists, and is the concept of prior. As you just saw, the prior is the initial belief that you have about the model. For example, do you initially think that your coin is fair? Frequentists have no concept of priors, so they only go by the evidence presented to them. As you've seen, this means they evaluate the likelihood that a model produced a given dataset. Bayesians, meanwhile, make use of prior beliefs to evaluate the data they collect. The goal of a frequentist is therefore to find the model with the greatest likelihood of generating the observed data, while the goal of Bayesians is to update their prior beliefs about your model based on the observations you have. This means that if you originally had a coin you thought was balanced, but tossing it 10 times you see 8 heads, you will probably want to reconsider your previous assumption. So far, all the point estimations you've seen, including MLE, follow a frequentist approach. So let's dig a little deeper into the Bayesian approach, and in particular, see the effect that using priors has on predictions. Imagine now that 3 Bayesians play the same game where they just found a coin on the street and want to figure out the probability of the coin landing heads. The first one is absolutely convinced that the coin should be fair and thus choose a prior that is very narrow, centered around 0.5. The narrow curve represents a strong belief that the coin is heads 50% of the time, with very quick drop-offs to 0 in either direction. The second Bayesian still thinks the coin should be fair, but they're willing to believe the coin might have a bias one way or the other.
Thus, they choose a prior that is also greatest at 0.5 but more spread out than the first one. Lastly, the final Bayesian doesn't want to assume anything, so they assign the same weight to each possible value. This is called a non-informative prior since it doesn't add any information. What happens to each of the statisticians' beliefs if after one coin toss they see heads? The conservative one almost doesn't shift their beliefs. In fact, to the naked eye, you would probably say that nothing has changed. The one in the middle updates their belief, but also varies slightly. After all, there is only one observation which happens to be heads. The last one, however, changes their beliefs drastically, going from something that weighted all possible values the same to one that assigns small probability to small values of p and increases linearly as p increases. Imagine that they keep tossing the coin so that in total they got 8 heads and 2 tails. Let's see what happens for each of our statisticians. The first one is still super tied to their beliefs. The curve hasn't moved one bit. The second one, who had a milder stance, has now started shifting their belief. Notice that the curve looks narrower and it no longer peaks at 0.5, but rather around 0.65. Finally, the third statistician is the one who changed its belief the most. They went from not having any information to being pretty sure the probability of heads should be around 0.8. Don't worry about how these updates were made for now. You'll learn all about it in the next video. I just wanted you to get a sense of the effect your prior has on updating your beliefs down the road. Even though all 3 Bayesians observed the same data, because they started with different prior beliefs, their final beliefs are different. These curves representing beliefs can be very informative to look at. They show not just one likely outcome, but how strongly a Bayesian believes every possible outcome is to be the true underlying value. However, many times you still want to have one representative value for the parameter. How can you do that from your updated beliefs? There are actually many criteria to choose this value, but one of the most used ones is to choose the value with the highest probability. This means taking the value of the parameter that maximizes your belief. In other words, just take the mode of your updated beliefs. The updated belief is also called your posterior beliefs. Just as your original belief is called your priors because they're your beliefs prior to observing the data, the updated belief is called a posterior because it represents your belief after seeing the data. Because the updated belief is called a posterior, this estimation of the parameter is called maximum a posteriori, or MAP for short. If you want to know about other estimations you can get from the posterior, there is a reading piece at the end of this section. Now let's go back to our coin example and see what the MAP estimation looks for each case. For the very conservative Bayesian, the MAP estimation for the probability of heads is 0.501. As you can see, it almost didn't budge from the original assumption that the coin is fair. The second statistician would say that the probability of seeing heads is 0.607. As you can see, it has significantly changed, but it's still not too extreme, even though they were presented with 8 heads and 2 tails, which from a frequentist approach could suggest an even more biased coin. Finally, the third statistician would say that the probability of heads is 0.8. This result sounds familiar, right? It should, because it's the same conclusion a frequentist would come to. In fact, anytime you use MAP estimation with an uninformative prior that weights all possible values equally, the result is identical to what you would get from a frequentist approach. This reinforces how important and unique the inclusion of priors is within Bayesian statistics. If you don't show up with any meaningful beliefs, MAP will end up being a cumbersome way to essentially do frequentist statistics. Alright, that's enough introduction to the concepts underlying Bayesian statistics. So join me in the next video where I'll explain how it's actually done mathematically. Now that you have a pretty good intuition of how things work in Bayesian statistics, let's learn how to actually perform the belief updates. You will see that you already studied the math involved. It starts with Bayes' theorem. Recall that given 2 events A and B, Bayes' theorem states that the probability of A given B equals the probability of B given A times the probability of A divided by the probability of B. This equation might be a little hard to understand without some examples, so let's define A and B here in the way they're typically used in Bayesian statistics. A is typically some event that you're trying to predict. Ideally, you would know its probability with perfect certainty. For example, whether you'll be offered a job that you applied for. B is another event or some evidence you can observe that helps refine your ability to predict A. For example, whether you were asked to attend a follow-up phone call.
The left side of this equation, the probability of A given B, is what you're solving for. It's called the posterior. And it represents the updated or refined probability of A once you account for the information provided by event B. In this case, what is your likelihood of getting the job now that you know you were asked to a follow-up phone call? The right side of this equation has three terms. The first is the prior, the probability of A. You can think of it as the probability of event A prior to event B happening. In this example, your priors would be your belief of the likelihood you're offered the job prior to receiving the request for the follow-up phone call. The other two terms are what update your prior and create the posterior. The top term is the likelihood of evidence B appearing, given A happen or will happen. In this case, it is the likelihood of getting asked for a follow-up phone call, given that you will be offered the job. The last term is the probability of evidence B appearing at all. In this case, it is the likelihood that you would be asked to a follow-up phone call, whether you will or won't be offered the job. Usually, you need to calculate the probability of B using this expression. You usually calculate the probability of B and B and not A using the general product rule and add them together. So stepping back to look at how all four parts of this equation work together, all you're doing is taking your prior beliefs on the probability of an event and updating them to create new beliefs or posterior beliefs based on new evidence. Now let's go back to the example of determining whether you have a fair or biased coin, and let's see how this expression is actually used. In this example, you know there are two possible types of coins. The first one is fair, which means the probability of flipping a heads is 0.5. And the other type is biased. This type of coin lands on heads with a probability of 0.8. You have a mystery coin. It can be either fair or biased, but you don't know which one it is. The only way to figure this out is to flip it. I'll set this experiment up in the way a Bayesian would, and one of the first steps will be to replace A and B in our generalized expression of Bayes' theorem with outcomes of some new random variables x and y. First, A, which is the event you want to predict, will be replaced with the event that a new random variable y takes some value. Y will be the odds of heads for the kind of coin you have. Y can output two possible values, 0.5 if your coin is fair and 0.8 if your coin is biased. The probabilities of these two outcomes are unknown, so you start with some priors. In this case, let's say you believe that most coins are fair, so you assign a 0.75 probability that the coin is indeed fair. That means that y will be 0.5, and a 0.25 probability that the coin is biased. That means that y will be equal to 0.8. Now you need some evidence to help update your priors. In this case, you will replace event B with the outcome of a new random variable x. X will be the result of flipping your mystery coin, so it will give a 0 if the flip is tails and a 1 if the flip is heads. Now you're ready to update your priors based on the outcome of flipping your coin. So let's flip it. The outcome of this flip is a heads, so I'll write down that little x is equal to 1. Now let's use Bayes' theorem to update those prior beliefs. To start, I'll show you how to calculate your posterior belief that the coin is fair. First, write your posterior. This is the probability that y is equal to 0.5 given that x is equal to 1. Or in other words, the probability that you have a fair coin given that you flipped heads. Next, you need the probability of getting a heads given that you have a fair coin. Now you need P of A. That's the probability that y equals 0.5 or that your coin is fair. Finally, divide by P of B. This is the probability of your evidence or the probability of flipping a heads. To do so, you will need the expanded expression to calculate the overall odds of flipping a heads, whether your coin is fair or biased. Now replace each of these probabilities with the actual values. The probability that x equals 1, given y is 0.5, is just 0.5. A fair coin will land on heads half the time. The probability of y equals 0.5 comes from your priors. You believe coins are fair 75% of the time, so replace this value with 0.75. Finally, this expression says that there's a 50% chance of heads with a fair coin and an 80% chance of heads with a biased coin. Using your prior to weight these two outcomes, you can calculate the overall chance of flipping a heads, which is 0.575. Complete this calculation and you get a probability of 0.652, and you're done. This is your new posterior. Compare this value to your earlier belief and you can see what happened. You used to think there was a 75% chance your coin was fair, but after flipping a heads, you changed your belief slightly. Now you believe that there's only a 65% probability that your coin is fair. While I won't walk you through the math here, a very similar approach would lead to a new posterior belief that the probability the coin is biased increases to 0.348. Notice that the sum of these two beliefs is still 1, which makes sense. You know that the coin is either fair or biased, so the sum of your belief in these two outcomes should still be 1. The example is very discrete, with only 2 possible values of y and 2 possible values of x, but let me start writing it in a more generalized way that uses probability mass functions. The first term in orange is actually the conditional probability mass function, or PMF, of y, given that x equals 1, evaluated in 0.5. Next, you have the probability that x equals 1, given that y is 0.5. This is the conditional PMF of x, given that y equals 0.5. The prior is simply the PMF of y evaluated at 0.5. And finally, this last expanded term can also be rewritten in terms of probability mass functions. Though remember, it also is just the probability that x is 1, which is the PMF of x evaluated at 1. Now that I've rewritten this equation in terms of the PMFs of x and y, I can take one more step to make it more general. Instead of the specific values of x and y I've shown here, I'll rewrite it so you could update your priors for any possible prior outcome little y and any possible event little x. What you're left with is the general expression for Bayes' theorem when you have two discrete random variables. For a given event little y and a given evidence little x, this expression will allow you to update your priors. This is a useful generalized formula, but notice that it is designed for instances where both the event and the evidence are discrete. What happens if either variable is continuous? That's what I'll show you next. There are 4 combinations you need to consider depending on whether x and y are discrete or continuous. The example you saw is for when x and y are both discrete. The next obvious instance is when both x and y are continuous random variables. In this case, the formula looks pretty much the same. Just replace the probability mass function by the probability density function for both variables. In the remaining 2 cases, you again just use the probability mass function if a variable is discrete, and the probability density function if it is continuous. Even though the expressions are different, these terms are all the posterior since they represent the updated probability after accounting for the data that was observed. And these are all priors, or the beliefs about y before knowing anything about x. In many machine learning contexts, you are solving for the probability that a parameter in a model takes a certain value. In these instances, it can be more common to replace the y's in these expressions with capital or lowercase theta. That looks like this. Again, all that has changed here is the notation with the letter y being replaced by theta, but the underlying concepts are identical. Depending on the combination of discrete and continuous variables you have in your context, you will use one of these 4 equations to update your priors. In the next video, you'll get to see one more example of this in action. In this final video on Bayesian statistics, I'll show you a more complete worked example where you collect more data and iteratively update your priors. Suppose this time you toss your coin 10 times to collect more data. You see 8 heads followed by 2 tails. How can you use this data to update your beliefs about your coin? Well, you'll need to start framing the situation using Bayes' theorem. First, you know how your coin has some probability of coming up heads, but for now it's a mystery. You can therefore think of your coin's probability of coming up heads as a random variable, which you'll call theta. Your goal will be to collect data to learn more about the probability density function of theta. In other words, learn more about how likely your coin is to come up heads. Now create a random variable x for the data you've collected. In this case, you can view x as actually containing 10 separate coin flips. To help distinguish the differences here, I will write x in bold and use subscripts 1 to 10 to denote each individual flip. You can actually say a lot about each of these flips xi. Each one outputs a 1 if the flip is heads or a 0 if the flip is tails. In other words, if you knew exactly how likely your coin is to come up heads, you could model each of these flips as a Bernoulli distribution. To capture this data, you can say that if your random variable big theta took a particular variable little theta, then each xi is a Bernoulli distribution for that value, little theta. X is a joint distribution of discrete random variables, which means it is itself also discrete. As a result, this is the version of Bayes' theorem you'll use, with the probability density function for theta and the probability mass function for x. Now your first step will be to calculate the likelihood of seeing these flips given a particular value of theta, so I'll write that down here. Now I'll expand that expression because this is really the likelihood of seeing those 10 Bernoulli random variables end up with 8 heads or 1s in a row followed by 2 tails or zeros. What's the likelihood of each of these outcomes? Well, for the heads, it's theta, and for the tails, it's 1 minus theta, which I'll write below each coin. And finally, we need the joint probability of this outcome. Since each flip is independent from every other, you can just multiply the probabilities across, given the final probability of theta to the 8th power times 1 minus theta squared. Now you can move on to filling in the other terms of Bayes' theorem. I'll collect all the important information you've calculated so far. You know each xi is a Bernoulli distribution, and you've calculated the odds of the data you observed given a particular value of theta. Next up, you need to choose your priors, which you will express as a PDF for the variable big theta. Let's suppose you truly don't have any prior beliefs about the probability the coin comes up heads. Any value between 0 and 1 seems equally likely. In that case, you would choose the uniform distribution, which is written like this. Now you have all the ingredients to solve the problem. First, write your posterior, which is the distribution you're solving for. Next, add in the conditional probability of observing the data, which you just calculated was theta to the 8th power times 1 minus theta squared. Next, multiply by your priors, which in this case is just a number 1. I've cheated a little bit here because I've dropped the 0 less than theta less than 1. This is still part of the prior and so also the posterior, but since theta has always been a probability between 0 and 1, I'll drop it here to make the notation simpler. Finally, divide by the probability of observing the data you saw. This last value can be tricky to solve for, but recall it is going to be some constant value that ensures the total area under the PDF is equal to 1. As I'll show you in a moment, you can typically ignore this constant. In this instance, I actually know that the distribution you have here is one called the beta distribution. You haven't studied the distribution, but technically you could find that the constant in this instance is 8 factorial times 2 factorial divided by 11 factorial. Feel free to read more on the beta distribution in the references at the end of this video or even on Wikipedia. Going back to this problem, however, I'll just ignore the precise value of this constant. Putting all these pieces together, you're able to solve for the final PDF for theta, which is the expression here. And these are your posterior beliefs. This is the conditional PDF of theta given the data you observed. Now let's look at how your beliefs changed after considering the data. You went from a uniform prior belief, which visually is just a flat line, to this posterior, which is definitely a lot more informative. It's telling you that values of the probability of heads under 0.5 are very unlikely, while leaning towards bigger values, having a peak somewhere around 0.8. Now let's look a little more closely at this result. I'm going to completely remove the constant term, so this new expression just says the posterior PDF on the left is proportional to the product on the right. Here's why I can do that. First, remember that if you choose some value little theta, you could call that a model of your coin where it comes up heads with a probability little theta. Then you can think of this first expression as the probability of the data given that model of the coin little theta. The second expression, meanwhile, measures how likely that model is. In this case, you assign the same likelihood to each value of theta with a density of 1. The result was itself a PDF, a new set of beliefs about every possible value of theta between 0 and 1. And that's what's shown on this chart. But what if you want to summarize this set of beliefs with a single number? Well, that's going to be the map estimate you learned about before, the maximum a posteriori value of theta. Remember that the map estimate is simply the mode of the posterior distribution, or in other words, the value of theta that made the posterior maximum. And this is why you can ignore the constant. All that constant in the denominator did was scale the curve of your new PDF. Including this constant won't change the shape of your curve, and most importantly, it won't change which value of theta gives the maximum. Now let me show you another interesting fact about the map estimate. In mathematics, you refer to the input to a function that maximizes the output as its argmax. In this case, it's the value of theta, theta hat, that maximizes your posterior PDF. Doing so typically requires calculus, and you may even recall some techniques if you completed that course in this specialization. In this example, the maximum value occurs when theta is equal to 0.8 or 8 over 10. Sound familiar? Well, it might, because this would be the exact answer of a frequentist. As I mentioned earlier, if you have a non-informative prior, like in this case, then the map is the same MLE estimation. When you think about it, it makes sense why. Uninformative priors are just constants, And just like the constant in the denominator, they don't affect the shape of the curve or the location of the maximum, so you can ignore them. The only term you're left with is the probability of the data given the model, and maximizing that probability is all MLE does. Now, what happens if your prior is informative? Well, an easy way to see would be to just keep going with this example. Let's flip your coin 10 more times. This time you get a sequence with 6 heads and 4 tails. Remember that after the first 10 coin flips, you went from a uniform prior to this new distribution. Well, if you want to keep updating your beliefs, then you can consider this probability density function as your new prior. After all, it is your most recent belief. This is the standard way of updating models in Bayesian statistics. When you want to incorporate new data, you just make your posteriors your new priors and repeat the process from before. Next, you need the probability of getting this sequence of coin flips given a particular value of theta. For each head, you have probability theta, and for each tail, you have probability 1 minus theta, which you multiply, because all variables are independent, to get theta to the 6th power times 1 minus theta to the 4th power. Now repeat the process from last time to update your beliefs. You first have the probability of observing your coin flips multiplied by the new prior, and again, everything is divided by a constant. Just like the last time, this is another beta distribution, but just like the last time, I'm going to ignore solving for the constant since it won't change our results. So you have that the posterior, after the second set of 10 coin flips, is theta to the 14 times 1 minus theta to the 6 divided by a constant. Let's see what the curves look like this time. You started from this prior on the left, which you developed after seeing 10 flips, 8 of which were heads. Then you flipped your coin 10 more times, this time getting 6 heads and 4 tails. I've written the equation for each curve below each of them. What is the map estimate of theta for your new curve? It is still the highest point in the posterior distribution, which is now 0.7. Now, this is a really interesting result for 2 reasons, and it highlights 2 important elements of Bayesian statistics. First, this time your priors were informative, and they clearly mattered. If a frequentist only saw that second set of 10 flips, they would conclude that theta is 0.6, because 6 out of 10 flips were heads. Your priors influenced your results though, and you concluded that the most likely value of theta is 0.7. A second interesting fact is that out of 20 total flips, 14 were heads, so after seeing all 20 flips, a frequentist would have also concluded that theta is 0.7. In fact, a Bayesian starting from an informative priors would also conclude the same. What this shows is that it didn't matter that you incorporate your data in 2 chunks, 10 flips at a time. This property actually holds in general for Bayesian statistics. Whether you incorporate all the data at once or in chunks, your final posterior beliefs will be the same. This concludes the investigation of Bayesian statistics, so let me summarize some key points. The main idea behind Bayesian statistics is to update your prior beliefs using data. As you collect more data, your old posterior beliefs become your new priors and you update them using the new data. If your priors are uninformative, MAP is actually just a complicated way to do the same thing as MLE. If there's no useful information in your priors, it's all coming from the data. Next, assuming you don't have wildly poorly behaved priors, MLE and MAP estimates will converge as you collect more data. You can think of this as the new data slowly watering down the influence of your initial priors. This brings up to why statisticians tend to choose Bayesian approaches. They are best for instances where you either have limited access to data or strong prior beliefs. If you're going to collect a lot of data anyway, frequentist approaches are probably fine. A potential downside of Bayesian statistics is that if your priors are wrong, you can make wrong conclusions. Especially with limited data, your priors will have a strong influence on the conclusions you draw. So now that you understand the difference in philosophies, what do you think? Are you a Bayesian or a frequentist? I suppose if you're having trouble deciding, you could always flip a coin.
So in this lesson, you've learned several different things. You learned maximum likelihood estimation and maximum a posteriori estimation, and you also learned regularization in machine learning. Now in this video, I'm going to show you how they combine.
So in this video, I'm going to show you how regularization and maximum likelihood actually match. So let's say you have the data and you have 3 models that could have fit that data. And Each one of them generates the data with some probability. And remember that a model can generate the data, as we saw before, by simply creating a Gaussian at every point on the line and generating points close to the line or to the curve. So the first one generates the data with some probability, P of data given model 1. The second one generates the data with higher probability, and the third one, since it's the best fit, generates the data with the highest probability. So we're going to pick this one. But just like before with the popcorn throwing contest and the movie, we also have to take into account the probability that the model has been picked. Now, the simpler the model, the more likely to have been selected. And I'm going to show you that in a minute. But the idea is that a simple model like model 1 is very likely to occur. A slightly more complex model like model 2 is not that likely to occur. And a model that's really complex like model 3 is very unlikely to occur. So what we're going to do is we're going to multiply these probabilities. And now the winner is not the third one. Now perhaps the winner is the second one. And so this is the winning model. Now let me show you how maximum likelihood and regression with regularization actually cooperate. Now in regression, you're going to have some loss that could be the square loss, for example. And in maximum likelihood, you're going to maximize the probability that the data was created with the model. Now if we add base here, then we have to multiply here by the probability of the model. Now if we do regularization and regression, then to this we add the regularization term. Now how do we turn the left into the right? Well, what's a good way to turn products into sums? We take logarithms, right? And that is how we turn the argument in the left with probabilities into the argument in the right with a loss and a regularization term. However, there's an elephant in the room here. I haven't yet told you what I mean by probability of a model. So that's what I'm going to tell you next. So what do I mean by the probability, or more exactly, the likelihood of a model? Let's say we have model 1, model 2, and model 3, and there's a high probability for model 1, a smaller one for model 2, and a really small one for model 3. Well, let's say that these are the equations for the models. And what we're going to do is we're going to pick these coefficients out of a standard normal distribution. So A1, A2, and all those up to A10 are going to be selected from a standard normal distribution. What is the likelihood of, for example, AI? Well, it's going to be 1 over square root of 2 pi times e to the minus 1/2 AI squared. Therefore, the likelihood of this model is exactly that number. Now, what is the likelihood of the second model? Well, we need to pick these two coefficients, so it's this product. And the likelihood of the 10th model is going to be the product of all these numbers, the product of all the likelihoods. So now, let's go back to trying to fit the best model. If these are our points, then let's say that this is a model that fits. We want to maximize P of data given model times P of model. And what are they? Well, we established previously that if these distances are d1 up to d5, then P of data given model is going to be this product over here. And what's P of model? Well, if the equation of the model is this, then P of model is 1 over square root 2 pi e to the minus 1/2 a1 squared times the same thing with a2 squared. Now, we want to maximize the product of these two. And there's a lot of constants, so we don't really need those. We can divide by the constants and maximize the rest. And let's take a logarithm like we did before. We take the logarithm here, we get minus 1/2 times the sum of di squared. And we take a logarithm here, we get minus 1/2 times a1 squared plus a2 squared. And the product becomes a sum under the logarithm. And now we have to maximize this. We can multiply by minus 1/2, and now that means we have to minimize the sum of squares of the distances, which is the square loss, plus the regularization term. So that's where the regularization term comes in. Therefore, when we try to pick the model out of model 1, model 2, and model 3, then maximizing the probability of the model is the same as minimizing the sum of squares of the coefficients. And
Maximizing the conditional probability of the data given the model is the same as minimizing the square loss. So the new loss is going to be the sum of the two. And that is how you train a model using regularization based on a Bayesian approach.
That brings us to the end of lectures for this week. After this, you've got 2 more activities to complete on your own. First, there is this week's Exploratory Data Analysis Lab. This week, you will dive deeper into the world happiness dataset you saw in week 1. You'll use linear regression to try to find which features of a country best predict that country's reported happiness level. I especially like some of the interactive portions of this lab, where you can choose which features to include in the model and see which features are actually most important. Afterwards, you will have this week's graded quiz. Good luck, and I'll see you when you're done to close out this week. So the people of Statistopia have some population average height mu, and you've seen how to take samples from this population to estimate it. There are some things you can do to make sure you get good samples, like random sampling, taking larger sample sizes, and making sure that the samples are independent and identically distributed. But even with these practices, you know you can't expect any particular sample to be perfectly accurate. After all, you get a different sample mean every time. Since you'll never be able to measure the height of everyone in Statistopia and calculate the true population mean, all you have is a sample mean, and you'll always have some degree of uncertainty about how accurate it actually is. A natural question then is whether you can use a sample mean with at least some degree of certainty. Statisticians do this using something called a confidence interval. In short, a confidence interval is an interval of values, that is, a lower and upper limit which contain the population parameter, for example mu, with some degree of certainty. Before showing you confidence intervals with a probability distribution, let's build some intuition about how they work. Imagine you're walking along a road to visit your friend. When you get to your friend's house, you realize you've dropped your keys somewhere along the road. That's okay, your friend says. I'll help you look for it. You get in your friend's car and then drive back out to the road where you dropped your key. While you're driving over, you and your friend talk about how you'll look for your key. First, you'll park the car at your best guess of where you dropped it. Then you'll both walk the same search distance in either direction along the road to look for the key. You need to decide this distance before your search so that you know you'll meet back at the car at the same time. You could always choose a different place to park the car, and that will shift the entire range of the road you'll search. But where you park is always going to be a guess. The thing that will have the biggest impact on whether you find the key will be your search distance. So the big question is, how large should your search distance be? To decide your search distance, you think about how confident you need to be that you will actually find the key, which you'll express as a percentage. Let's say you think with this search distance, you're 80% confidence you'll find the key. What if you left your oven on? Then you really need to find that key. Well, then you'd need to agree to a bigger search distance. With a search distance this big, you're 95% confident you'll find the key. Of course, you'll also have to search a much larger portion of the road. Let's say you only have a little bit of time to look. Well, you could always shrink your search distance. But your confidence level is also going to drop. There's a trade-off here. If you want a higher level of confidence, you're going to need a larger search distance. You can think of a section of the road you and your friend will search as a single interval with a lower and upper limit. That said, I think it's really important to remember the way the interval was constructed. At the middle is your best guess of the true location of the key, and then you add a buffer on each side to account for the fact that you know your guess is probably wrong. That said, this orange line is the overall confidence interval. I use this example from the physical world because it helps reinforce an idea that can be tricky to remember when you're looking at probability distributions. The key never moves. Its location is unknown, but fixed. The interval, meanwhile, is randomly generated with a desired certainty, or if you prefer, uncertainty that it contains the key. I say randomly generated because one of the ingredients of the interval is that best guess you made of where to start looking. Yes, you can always add a bigger search distance to either side of it, but at the heart of your interval is just a guess. Many people look at confidence intervals and say something like 50% of keys fall inside this interval, but hopefully you can see why this is wrong. After all, there is only one key, and it's always been in the same location. Talking about a lot of keys randomly appearing in one place or another makes no sense. Instead, you should say 50% of the guesses are within a search distance of the key. This makes it clear that the best guess of where to park the car is the source of the randomness and the uncertainty. So this is an introduction to the ideas. Now let's see what they actually look like when you've got a probability distribution. Okay, so let's go back to Statistopia and let's apply those ideas about confidence intervals to the question you were facing before. What is the mean height across the population? Let's assume that heights in Statistopia follow a normal distribution with a mean mu, which is unknown, and a population variance sigma squared, which for now we'll assume is known. It might seem a little weird that you would know the variance, but would not know the mean of your distribution, and you are right. Usually you're a little uncertain about both of them. For now though, I'll set up a problem in the simplest possible way, where only the mean is unknown, and later in the course I'll show you how to handle the situation where you don't know the variance either. Thinking back to the example of the lost key you just saw, the true value of mu is the key. Mu has a fixed but unknown value. You will randomly generate a confidence interval to estimate where it is located. To do that, you will take a random sample from your population. To make things simple, let's start with a sample of size 1. That is, one person. You're going to measure the height of one random person and use that to estimate the population mean. Since your sample has only one person in it, their height will also be the sample mean, which I will call little x bar. Let's create a random variable, big X bar, to describe the probability of selecting different sample means. It's actually going to be identical to x, a normal distribution centered on mu with a variance sigma squared. This doesn't mean you suddenly know the true value of mu, but you do know x and x bar have the same mean. Now you're wondering about your sample little x bar. Is your person a little taller than average or a lot shorter? While you can't know for sure, you do know something about the probability distribution of x bar, so let's think about this in a different way. How far are most sample means from the true population mean mu? After all, if your sample is typical, it will also be within that range. To do this, you need two related concepts. You will need a margin of error, which is a distance on either side of mu, and a confidence level, which is the probability that your sample mean is within that margin of error. To set these two values, you actually normally start with a third one called the significance level, which is denoted with the Greek letter alpha. That is the probability that your sample mean falls outside your margin of error. Here, let's set alpha to 0.5, which is a very common choice. From alpha, you'll calculate your confidence level, which is 1 minus alpha. This is the probability that a randomly generated sample mean is within the margin of error. Since alpha is usually a small number, 1 minus alpha is usually close to 1. And in this case, it will be 0.95, leading to a confidence level of 95%. Now you can increase the size of your margins of error until 95% of all randomly generated sample means will fall within the shaded portion of the distribution curve. Notice that since the normal distribution is symmetric around its mean, you can say that 2.5% of the time your sample mean will lie outside the margin of error because it's too big, and 2.5% of the time because it's too small. That is just alpha divided by 2. Okay, you're finally ready to see the formula for your confidence interval. It's just your sample mean plus or minus the margin of error. What this is saying is that if your sample mean is one of the 95% of all sample means that is relatively close to mu, then mu is also relatively close to the sample mean. In other words, confidence intervals are a bet. They are saying, unless I got really unlucky and my sample mean is uncommonly large or uncommonly small, then mu should be pretty close to my sample mean. This is still a tricky idea to get your head wrapped around, so let me show you some more examples. Let's build a few confidence intervals. Assume you want a confidence level of 95% and have already calculated how big your margins of error need to be. I'll draw the true value of mu, but remember, you won't actually know it. Now you'll take your first sample at x1 bar, which is the height of one randomly chosen person. Draw the margins of error on either side of x bar to create your first confidence interval. Does this interval contain the population mean? No, this person is much shorter than average. Now take another sample x2 bar and generate the interval around it. This time the interval does contain mu. And here's a third example with a confidence interval around it that also contains mu. Now let's refine the illustration and make the intervals that contain mu green and those that do not contain mu red. You can repeat this process many times, each time checking to see if the interval you generated contains the population mean. You will find that when your confidence level is 95%, 95% of your confidence intervals will contain the population mean, and 5% of the time they will not. This is what's meant by a 95% confidence interval. It means that the recipe you're using to cook up your interval will result in one that contains the population mean 95% of the time. Remember, however, you're not going to generate hundreds of confidence intervals, and you're not going to actually know mu. Instead, you will generate a single confidence interval. Does it contain mu? Well, you can never be perfectly sure, but 95% of confidence intervals generated like this do contain mu. You just saw how to develop a 95% confidence interval when your sample size was 1. Let's look more closely at X-bar to think about ways you can improve this result. You saw that X-bar, the sampling distribution of the sample means, was normally distributed with mean mu and standard deviation sigma. In fact, it had the exact same distribution as the overall population. Before moving on, it is useful to remember why you know this. First, you know mu of X-bar, or the expected value of the sample mean, always equals mu, the population mean. This is true no matter how many observations are in your sample. Now consider the standard deviation of the sample mean, sigma of X-bar. You learn that it will be equal to the population standard deviation divided by the square root of the number of samples n. In this case, it does vary with sample size. However, since for now n is 1, the two standard deviations are the same. Now, what if you increase your sample size so n is now 2? As mentioned before, the mean of the sample means doesn't depend on sample size. It will still be the population mean. The standard deviation, however, does depend on the sample size. For a sample size of 2, this will be sigma divided by the square root of 2. The distribution of the sample means is now a normal distribution with the same mean, but a smaller standard deviation. It will look more like this. The curve didn't move left or right, but it got taller and skinnier. Now let's see how this change in sample size affects your margins of error. At first, you had a sample size of 1 and were aiming for a confidence level of 95%. When your sample size is 2, your distribution is narrower with outcomes more closely concentrated around the mean. As a result, you don't need as large a margin of error to either side of mu to account for 95% of the distribution. Your margins of error shrink. And this pattern continues if you keep increasing n. For example, what do you think happens if you increase n to 10? Once again, the margin of error and thus the confidence interval become even smaller. Let's generate some more confidence intervals for these larger sample sizes. Start with n equals 2 and a 95% confidence interval. It'll generate some samples and draw the confidence intervals around them. Here's the first one, x1 bar. And here is the confidence interval around it. For this first sample, the confidence interval does not contain the population mean mu. The same confidence interval around x2 bar, however, does include mu, and so does the one for x3 bar. Now we'll generate some samples when n is equal to 10. Here's the first sample, x1 bar, and here are the margins of error around its sample mean. Notice how the margins of error are smaller, giving a shorter overall confidence interval. While the margin of error is smaller, you also expect the sample means here to be closer on average to the true population mean. The reason for this is that with larger samples, you get greater accuracy. So even with smaller margins of error, the confidence interval around x1 bar does contain mu. The same is true for the second sample, x2 bar. But the confidence interval around this third sample does not contain mu. Now I'm going to simplify these illustrations and again color them green if they do contain the population mean and red if they do not. And just like before, let's generate many confidence intervals of both types. Here are many intervals when the sample size is 2. And here are a bunch when the sample size is 10. Since in both cases the confidence level is 95%, roughly 95% of the confidence intervals of the left and 95% of the confidence intervals on the right should contain the population mean. And in both cases, about 5% of the confidence intervals do not contain the population mean. While all the confidence intervals have the same 95% chance of containing the population mean, The ones in the right are definitely more desirable, and that's because they're smaller. In other words, you have a more precise estimate for the true value of mu while maintaining the same level of confidence that you're correct. Let's examine the effects of the sample size more closely with this mock simulator. Using the mock simulator, I'll quickly construct a sampling distribution for sample means of size 1 that follows a distribution as shown. And I'll make these limits indicate the margin of error to be used to construct the confidence interval. Keeping the confidence level constant at 95%, I'll change the sample size and see the effects on the margin of error. If I increase it to 10, as expected, the distribution became taller and narrower. To capture 95% of the sample means, you don't need to go as far to the left and right of the mean, and so the overall interval shrinks. More generally, as n, the sample size increases, the confidence interval shrinks. In other words, as you collect more data, you can make more precise estimates of mu without dropping your confidence level. You've seen the effect of the sample size on the confidence interval. Now let's see what happens if you're willing to aim for a different confidence level. I will keep the sample size constant at 1 and keep the same sample distribution that you've seen throughout this video. When your confidence level is 95%, here's what the margins of error will look like. Suppose you're willing to settle for a lower confidence level of 70%. If you place a 70% confidence interval around a randomly generated sample, mu will be captured 70% of the time. This distribution will still be the same normal curve as before, but you will be able to use smaller margins of error since now your sample mean only needs to fall within them with 70% probability. Now let's see what happens if you generate many confidence intervals of both types. Here are many samples of size 1 with a 95% confidence interval drawn around them. And here's another set of samples of size 1 with a 70% confidence interval drawn around them. If you did this many times, the confidence intervals on the left would contain the population mean 95% of the time, and 5% of the time they won't. The intervals on the right, meanwhile, only contain the population mean 70% of the time, and 30% of the time they don't. The difference here isn't that the sample means on the right tend to be farther away from the population mean, but simply that you've chosen to use small margins of error, and so there are more instances where the overall confidence interval does not contain mu. Now let's return to that same simulator. This time I will keep the sample size constant and only adjust the confidence level. Notice that as I change the confidence level, the margins of error change. The actual distribution of the sample means generated stays the same. This is the same trade-off you saw way back when you were thinking about searching for that lost key. If you want a higher probability that your interval contains the population mean, or in that instance, your lost key, you'll need to use larger margins of error. Let's summarize the key points you've seen. Confidence intervals have two ingredients, a randomly generated sample mean and a margin of error added to each side. Since the mean of the sample you collect will, to some degree, be up to random chance, the confidence interval is also random. The confidence level is the probability that a confidence interval generated this way contains mu, a typical value of 0.95 or 95%. You'll never actually be able to confirm whether your confidence interval contains mu, since the whole point is that mu is fixed but unknown. Ideally, your confidence level would be high and your confidence interval would be narrow. You'd love to say with 99% confidence that the value you're looking for is within a tiny range. Unfortunately, you can't just get small margins of error and a high confidence level for free. As you saw, the most straightforward way to shrink a confidence interval is to collect more data. Having a larger sample will lead to a sampling distribution with a smaller variance, and you'll therefore be able to use smaller margins of error to capture the same amount of that sampling distribution. Choosing a lower confidence level also leads to a narrower interval. That said, you rarely see confidence intervals below 90% used, and 95% is the most common. At some point, if you want more accurate estimates, you'll just need more data. So far, you've learned about all these concepts at a high level. In the next video, you'll learn how margins of error, and therefore confidence intervals, are actually calculated. Now you're going to learn how to construct a confidence interval. To help, let's go back to this illustration. Each of these is a different sample of size 1. Since there's only one observation in each sample, the sample mean is just the height of the person in that sample. The orange bars around each sample are the confidence intervals. In order to generate them, you first need to calculate the margin of error. As you saw in the last video, the margin of error is determined by the size of the sample you collected and the confidence level you're aiming for. Once you have your margin of error, you add and subtract it to your sample mean in order to get the lower and upper limit of your confidence interval. So the two main ingredients of a confidence interval are the sample mean and the margin of error. Since you already know how to calculate the sample mean, let's look more closely at how to calculate the margin of error. To start, I'll show you a very general case. Suppose you're studying a population of people whose heights follow a normal distribution with a known mean mu and known variance sigma squared. As before, this random variable will be called x. Your goal is to figure out mu, the average height of the population. To do that, you take a sample of size n and calculate the sample mean x bar. You would measure the heights of n people and calculate their average height. You know that sample mean probably isn't exactly the average height of the overall population, but it's also probably close. Your goal is to quantify how close. If you randomly happen to choose many short people, x bar will be lower than mu. If you randomly happen to choose many tall people, x bar will be higher than mu. X bar is itself a random variable. As you saw in the last video, it will be normally distributed with a mean of mu and a variance of sigma squared divided by n. The distribution is centered around mu, and as you take larger samples, the spread of your distribution shrinks, increasing the probability your sample mean is closer to mu. The main thing to remember here is that you still don't know mu, and you're only taking one sample. All you have is x bar and the value of sigma, which we've assumed for now you magically have access to. Since x bar is normally distributed and centered around mu, you know your sample mean is probably close to mu, but there's always a chance it's an outlier sample. So if all you have is your sample mean and sigma, let's see how you can make your confidence interval. To do that, recall some useful facts you learned about the shape of the normal distribution back in week 2. You learned that for any normal distribution, roughly 68% of the curve lies within one standard deviation of the mean, and roughly 95% lies within 2 standard deviations of the mean. If you know the standard deviation of a normal distribution, you can establish the range around mu in which any percentage of the distribution lies. These points that are a specified number of standard deviation away from the mean have a special name, z-scores or z-statistics. The point 2 standard deviations greater than the mean has a z-score of 2, and the point 1 standard deviation below the mean has a z-score of -1. The name z-score is taken from the standard normal distribution, which is often called the z-distribution. You can easily convert normal distributions to the standard normal by subtracting the mean and dividing by the standard deviation. The z-distribution has a mean of 0 and a variance of 1. Notice that when using the z-distribution, the z-scores are simply the value of the point. For example, at the number 2, you are 2 standard deviations above the mean of 0. When working with the standard normal, you also know roughly 95% of the distribution lies between the values of -2 and 2. Since it makes the math simpler, you'll often see this concept talked about from the perspective of this standard normal distribution. If you want exactly 95% of the distribution, then the z-scores to 2 decimal places are -1.96 and +1.96. If you randomly sample from the standard normal distribution, 95% of the time, the result will be inside of that range. 5% of the time, your sample will fall outside of this range. -1.96 and +1.96 are called critical values. They are cutoff points inside of which an exact percentage of a probability distribution is contained. To find these values, you'd either look them up in a pre-computed lookup table or use a software library. This isn't something you would calculate by hand. The first critical value is z.025. This notation means find me the z-score of the point which has 2.5% of the distribution curve to its left. This shaded region has a probability of 0.025. From your lookup table or software library, you would get the result of -1.96. The second critical value is z.975. Once again, it is shorthand for the z-score, which has 97.5% of the distribution curve to its left. These two values were chosen because you know the normal curve is symmetric and you want the region around the mean that contains 95% of the distribution. In other words, you want your critical values to exclude 5% of the distribution. This is just the significance level alpha, which you learned about in the last video, and in this case, it's equal to 0.05. That means this left critical value is z of alpha divided by 2, and the right critical value is z of 1 minus alpha divided by 2. The same holds if alpha is 0.1. Your critical values are now at z.05 and z.95, which in this case would be the z-scores negative 1.65 and positive 1.65. Between these two values lies 90% of the distribution. Returning to a non-standardized normal distribution, you can still use these critical values, but since the distribution isn't normalized, you need to multiply them by the standard deviation. In this case, 95% of the distribution lies within 1.96 standard deviations of the mean. So you just multiply that critical value by sigma. You're finally ready to calculate your margins of error. You know that x bar has a normal distribution centered around mu and with variance sigma squared divided by n, the number of observations in your sample. This means the standard deviation is just sigma, the population standard deviation divided by the square root of n. This is also referred to as the standard error. So let's update the range of values accordingly to use this standard deviation. You now know the range of values that will contain 95% of all sample means. And from there, you can get your margins of error, which will just be 1.96 times your standard error, which is sigma divided by the square root of n. If you had chosen a different value of alpha, you'll have a different margin of error. You'll look up z of 1 minus alpha divided by 2 and multiply that by your standard error. You've now established margins of error, so let's complete a few more steps to generate a confidence interval. Remember, your entire goal in this process was to find a lower and upper limit that bound mu, the population mean. What you just found is that with probability 0.95, your sample mean will fall within the range shown here. Notice you actually haven't found a bound for mu. You found a bound for x bar. So let's change this inequality to get the result you actually want. Start by subtracting mu from all the terms. Now let's subtract x bar. You're almost done. You just need to multiply everything by -1 to clean up that negative mu in the middle. Just remember that if you multiply an inequality by a negative number, the inequalities switch the directions. As a result, you get this, and now you flip the inequality to face the other direction. And that's it. You managed to get an interval that bounds mu. And so your confidence interval ends up being the interval obtained by adding and subtracting the margin of error to the sample mean. Let me address one more point about how you built this confidence interval. So far, you've assumed that you were working with a population that followed a normal distribution. In this case, if you had a sample size n, then the sample mean will also have a normal distribution with the same mean as the population mean, but variance n times smaller. However, data isn't always normally distributed. Maybe you don't even know how the population behaves. Does anything you just learned still work? Well, remember, you didn't actually care about the population distribution here. All you needed was the distribution of the sample mean. And this is where the central limit theorem swoops in to save the day. If n is large enough, then by the central limit theorem, your sample mean will still have an approximately normal distribution, and it even has the same parameters mu and sigma squared over n. So nothing actually changes. The process you just learned to develop your margins of error will still hold, so long as you pick a large enough sample. After this, you'll find an interactive tool in which you can generate your own confidence intervals for both Bernoulli and normal distributions. You'll be able to set the confidence level you're aiming for and see the impact on both the size of the confidence interval as well as the share of the confidence intervals that contain the population mean. This is a great chance to get hands-on with the concepts I've been talking about. Enjoy, and I'll see you once you're done. So here are the calculation steps for finding the confidence interval. First, you find the sample mean. Then you define a desired confidence level. You next find the critical value for this desired confidence level, 1 minus alpha, which is 95%. Then you find the standard error. This is the standard deviation of the distribution of sample means. You multiply the critical value and this standard error to get the margin of error. Finally, you add and subtract the margin of error to the sample mean to obtain the desired confidence interval. And there you have it. That's how you calculate the confidence interval. There are some assumptions under which computing this confidence interval works. The first is that the sample used is random. The second one is that the sample size is bigger than 30, or the population is approximately normal. So even though in our illustrations we use sample size is less than 30, when applying the confidence interval in your work, be sure to follow these assumptions.
So let's go back to our running example. I'm trying to estimate the average height of the world's population. So I take a small sample of the population and I take the average of their heights. So let's say that value is here. And let's say that the actual average of the human height is here. So a 95% confidence interval is going to tell me an interval where the actual average is very likely to be. Let me elaborate.
Now let me show you an example of a confidence interval calculation. Let's say we go back to the island of Statistopia and that there are 6,000 adults there. And we want to find the average height of the people of Statistopia, or at least have some interval where it's very likely that this mean lies. So since we can't measure all the 6,000 adults, you pick 49 of them at random and you found that the mean height of the sample is 1 meter 70 centimeters. And the population standard deviation is 25 centimeters. So let's find a 95% confidence interval for the average height of adults on Statistopia. We know that it's probably close to 170, but let's find an interval for which we're 95% sure that the average of the heights of the people in Statistopia lies within. Recall that the critical value for a 95% confidence level is 1.96 as we saw before. So let's start with the margin of error. We know that the formula for the margin of error is 1 minus z of alpha over 2 times the standard deviation sigma divided by square root of n. So that's 1.96 times 25, the standard deviation, divided by the root of 49, which is very conveniently 7. So this number is going to be 7. Therefore, the confidence interval is going to be 1 meter 70 or 170 centimeters plus or minus the margin of error, which we know is 7. Therefore, the confidence interval is between 163 centimeters and 177 centimeters. That is the interval where we're 95% sure that the average height of the people in Statistopia lives. In the last example, we had a population of 6,000 adults. I wanted to calculate a 95% confidence interval for a sample of 49 adults with a mean height of 170 centimeters and a standard deviation of 25. We got a margin of error telling us that 95% of the time the population mean was between x bar plus or minus 7 centimeters. That gave us a confidence interval of 163 centimeters on one end and 177 centimeters on the other end. But let's say that we're not happy with that. 7 centimeters is too much. We want to have a margin of error that is much smaller. We want, for example, 3 centimeters because we want to have a more exact estimate of the population mean. So all of a sudden 49 is too small. So we need a bigger number of people. We need a bigger sample in order to give us more confidence. And the question is, what is the smallest sample size that will help us obtain the desired margin of error? So we're going to do similar math as in the previous example, except backwards. So recall that the formula for the margin of error is this one over here. Now, we know the value for everything here except for n. So let's go ahead and substitute the margin of error into the equation. So now we have that 3 is equal to 1 minus z alpha divided by 2 times the sigma divided by root n. But since we want a margin of error of 3, that means that getting anything less than 3 is even better. If you have a margin of error of 2 or 1, then that's much better. So we can substitute the equal by a greater than or equal and keep the right hand the same. So now we get 3 bigger than or equal than 1 minus z of alpha over 2 times sigma divided by n. 3 is the maximum margin of error that we're allowed to have. Now replacing all the values we know into our inequality, we get that 3 is bigger than 1.96 times 25 divided by root n, from which we can solve for n and get that n is bigger than or equal to 1.96 times 25 divided by 3 squared. And that's going to be the value that we want. What is that value? That value is 266.78, and since we're talking about people, then we can round it to 267. That means that we need a sample of at least 267 adults from the population in order to get a margin of error of 3 centimeters. Now let's generalize the formula we just used to calculate the sample size. For a particular margin of error here called MOE, we want the sample to be at least 1 minus z of alpha over 2, where alpha is the confidence interval, times the standard deviation sigma divided by the margin of error squared. So you can plug in any margin of error into this equation and get the desired n. So say you compute a sample estimate x bar and you calculate a confidence interval of 95%. And in your interpretation, you say this: the confidence interval contains the true population parameter 95% of the time. You could be correct. Now, what if you said there is a 95% probability that the population parameter falls within the confidence interval? You would be wrong. There's a subtle difference between these two, and we're going to see what it is. So consider the population parameter mu, which is the population mean. A defining characteristic of mu is that it's fixed, but it's unknown, is the one we're trying to estimate. And note that mu does not have a probability distribution because it is not random. It's just unknown, so it's always the same value for a given population. And because mu is fixed for a given interval, it is in the interval or it is not in the interval. It does not change, so it's not going to fall within a specified interval 95% of the time or not. The sample mean, on the other hand, has a probability distribution, the sampling distribution of the sample means. This value changes given the sample taken, so the concept of the confidence interval is tied to the sample mean, and it changes depending on the value of the sample mean. Saying that you're 95% confident has to do with repeating the sampling experiment many times and calculating the intervals for each sample estimate. 95% of the time, those confidence intervals will contain the mean. This confidence level has to do with the success rate of contracting the confidence interval. It is not the probability that a specific interval contains the population mean, because as we've seen, the population mean is either on the interval or not. So this is something that is very subtle, but it needs to be clarified.
So in this course, we've done a lot of point estimates. However, for all of them, we've assumed that we know the standard deviation of the total population. This is not always the case. Many times we don't know it. But that's no problem. When we don't know it, all we have to do is make a small change in our calculations by introducing something called the student t-distribution. Let me show you how.
So recall that the formula to find the confidence interval given some point estimate x bar is this one over here. And as you know, this only works because we actually know this sigma. We know the population standard deviation, which gives the sampling distribution quantity that generates a normal distribution around the population mean as shown. And this is because of this normal property that we're able to use the critical value 1 minus z of alpha over 2. However, more often than not, we do not know this standard deviation of the population. And that's a problem because we can't use that sigma in the formula. So what do we do in this case if we want to have a confidence interval? So you may have guessed it, we have to use the actual sample standard deviation S. So we can't use the population standard deviation, but we took a sample and we can use the sample standard deviation S. This gives us this sampling distribution where we simply change the sigma into an S. However, this quantity is no longer a normal distribution. Now it's a different distribution. It's called the student's t-distribution. And using the normal distribution as a reference, the student t-distribution looks like this. It's very similar to the normal distribution, but it has much fatter tails, meaning that more of the points can be found on these sides compared to the normal distribution. If you were to sample a point out of the student t-distribution, it's more likely to be far from the center than if you pick it from the normal distribution. So how do we then adjust for this variability in the distribution to still give us some more accurate confidence intervals? Well, let's do a quick recap. With a known sigma, we have a sampling distribution quantity with a normal distribution, and that's why it's okay to use the z-score in scaling to find the confidence interval. Now, what happens with an unknown sigma? Well, we can replace sigma with s, the sample standard deviation, and then this quantity becomes this quantity with s instead of sigma, and that's a student t-distribution. And if we just replace the sigma in the margin of error with s without adjusting the z-score used for scaling to match the distribution, we would be wrong, because this z-score actually depends on the normal distribution. 1 minus z of alpha over 2 is defined over the normal distribution. So what do we do then? Well, since we're not using the normal distribution, but we're using the student t-distribution, then this z changes to a t, that is the t-score. So we don't use a z-score, we use a t-score to calculate the margin of error to fix this scaling issue. So to recap, here are the two formulas for the confidence interval compared side by side. The main difference is that if we happen to know sigma, then we put it here on the calculation for the margin of error. But if we don't know sigma, which is most of the time, then we put an S, the sample standard deviation, the one that comes from our samples. On the case where we know sigma, we use the z-score that comes from the normal distribution. And in the case that we don't know sigma, then we use the t-score that comes from the student t-distribution. Now you already know the formula to find the margin of error and confidence interval when sigma is unknown. We introduced the t-statistic and mentioned how it's related to the t-distribution. Now it turns out that there are several t-distributions defined by something we call the degree of freedom. The degree of freedom of a t-distribution is given by the number of samples that we used minus 1. Now, what is the effect of the degree of freedom in the t-distribution? Well, let's use the normal distribution as a comparison. The degree of freedom defines how high and tight the t-distribution is. So, for a t with degree of freedom 1, you have larger tails. And when you compare this to one of 5 degrees of freedom, then you have smaller tails and it's closer to the normal distribution. And here's one of 10 degrees of freedom. Note that now it has smaller tails and it's even closer to the normal distribution. The larger the number of degrees of freedom, the closer and closer you get to a normal distribution. And this makes sense, right? Because the more samples you use, the bigger n is, the closer and closer that your sample standard deviation s is to the population standard deviation sigma. And if you know sigma, you use a normal distribution. So the closer you get to sigma, the closer you get to using a normal distribution. So in the last lesson, we looked at how to compute confidence intervals given a sample mean. We knew we were working with sample means because we were calculating the confidence interval for the average height of the population. And recall that when calculating the confidence interval for sample means, then this is equal to the sample mean plus or minus the margin of error, where the margin of error is given by this formula over here. The z-value times the standard deviation divided by the square root of the sample size. But now, how do we work with confidence intervals for proportions? So for example, consider this problem. You want to find out the proportion of adults who would own a car in Statistopia. You sample, let's say 30 people, so n is equal to 30. And out of the 30 people, you find that 24 of them own a car. Therefore, x is equal to 24. You calculate the proportion of the people who own a car, and that's given by p hat, and that's 24 divided by 30, which is 80%. This is the sample proportion. Now, of course, that may not be the population proportion, but it's likely to be close to it. And the question is, how do we calculate a 95% confidence interval for this sample proportion? Well, similar to the confidence interval for the mean, the confidence interval for the proportions is given by the formula p hat, which is your sample proportion, plus or minus some margin of error. Now the question is how to calculate this margin of error. This is where the difference lies. The margin of error when calculating the confidence interval for proportions is given by the formula margin of error equals the critical value times the square root of p hat times 1 minus p hat divided by n. Obviously, the critical value will depend on the confidence interval you use. So the major difference is in the standard error and how it's calculated. So just as a sample distribution of means, the standard deviation is given by sigma divided by square root of n. The standard deviation of a sampling distribution of proportions is given by p hat times 1 minus p hat divided by the sample size n. So quick recap, the confidence interval for proportions is given by p hat plus or minus the margin of error, where the margin of error is given by the critical value times the square root of p hat times 1 minus p hat divided by n. So we had an example where we wanted to calculate the proportion of adults that own a car in Statistopia from the sample size of 30. We found p hat, the sample proportion, to be 80%. Now I want to calculate a 95% confidence interval for the sampler proportion. For a 95% confidence level, the critical value is 1.96. Thus, the margin of error is 1.96 times the square root of 0.8 times 1 minus 0.8, which is 0.2, divided by the sample size 30. And that gives us a margin of error of 0.14. And therefore, the 95% confidence interval is p hat, which is 0.8, plus or minus the margin of error, which is 0.14. That means that the confidence interval is between 0.66 and 0.94. Thus, we're 95% confident that the population proportion of how many people own a car in Statistopia is within 66% and 94%.
All right, welcome to lesson 2. In this lesson, you're going to learn about hypothesis testing. Hypothesis testing is a way to tell if some belief you have on the population is likely to be true or false. And then we're going to learn a very important application of hypothesis testing called A/B testing. So first, let's start with a simple example.
So to understand hypothesis testing, I like to look at this example. Let's say you have an email spam detector, and what it does is it determines if a given email is ham or spam. And remember that ham is when an email is not spam, and by default we're going to assume that all the emails are ham. And the reason for this is that it's much worse to delete a good email than to accidentally put a spam email on our inbox. So our base assumption is going to be that an email is ham. That's going to be called the null hypothesis. It's the base assumption when we assume safely that nothing is happening. This null hypothesis is called H0. And then we have an alternative hypothesis called H1. And that's the special one. That's the one we are trying to identify. One important characteristic of the null and alternative hypothesis is that they are mutually exclusive, because the email can't be ham and spam at the same time. Also, these questions have to have a true-false answer, and the key is to designing a good set of hypotheses. And notice something really important. If there's a lot of evidence that shows that the email is spam, then the null hypothesis is rejected, and the alternative hypothesis that the email is spam is accepted as true. But this doesn't work the other way around. If the evidence gathered is not enough to show that the email is spam, then you can reject the null hypothesis. However, that does not mean that the email is ham, only that we don't have enough evidence to show that the email is spam. So in general, you will need to propose your hypothesis. The null hypothesis is the baseline, and the alternative hypothesis represents the competing statement. And given the asymmetry in the conclusions, this is usually the one you're interested in proving. And the goal of hypothesis testing is deciding between two hypotheses based on data and evidence. In the case of the spam example, then this evidence comes in the form of the sender, the attachments, the size of the email, certain keywords, etc. Anything you can use to show that the email is spam. Intuitively, when performing hypothesis testing, if your sample gives plenty of evidence against H0, then you will reject the null hypothesis and consequently accept the alternative hypothesis. In this case, your evidence based on data will be different words or phrases in the email. And so suppose that you get an email that has phrases like earn extra cash, risk-free, dear friend, act immediately, apply now, and winner. These are all trigger phrases for detecting spam. In fact, these phrases are very likely to happen if the email is not spam, which is the null hypothesis, under the hypothesis that this is a regular email. In this case, you would reject H0 and send the email to spam. So ideally, you would like to always make the perfect decisions. Unfortunately, this is impossible to guarantee due to the randomness of the world and the fact that we only have partial information from the population under study. So what could go wrong? Well, there are two possible outcomes to the test. Either you send the email to the spam box or you send it to the regular inbox. Each of these outcomes could be wrong. In the first case, you send a regular email, a ham email, to the spam box. This is called a type 1 error or a false positive, and it happens when you reject H0 when it was actually true. The other error appears when you incorrectly determine a spam email to be ham, to be a regular email. This is called a type 2 error or a false negative and occurs when you don't reject H0 and the hypothesis was actually false. It is important to understand that you can never know if you are right or wrong about your decision because you don't know the ground truth. However, you will try your best to determine a test where you keep these errors below an accepted threshold. This table sums up the possible outcomes of your decision. If the ground truth is that H0 is true, that means if the email was actually not spam and you reject H0, you will be committing a type 1 error. That means you send a perfectly good email to the spam box. However, if you decide not to reject H0, then you would have made the right call. That means you send a good email to the inbox like you should. If in reality H1 was true, that means the email was spam, then rejecting H0 will be the right decision. That means if you get a spam email, you send it correctly to the spam box. And finally, not rejecting H0 will make a type 2 error. That means you took a spam email and sent it to the inbox. Notice that type 1 and type 2 errors don't have the same impact on the problem. In the case of the email, assuming that the email is ham implies that sending a spam email to the inbox is more positive than sending a ham email to the spam box, which is true. You would much rather have an accidental spam email in your inbox than lose a perfectly good email and never be able to read it because the classifier thought it was going to be spam. This means that type 1 errors are more severe than type 2 errors. The question is then, how much are you willing to negotiate here? What is the greatest probability of type 1 error you're willing to tolerate? Or in other words, on average, how many times are you willing to incorrectly send a ham email to the spam box in order to have a good spam detector that still sends most of the emails to the correct place? Well, the maximum probability of type 1 error is called the significance level and is usually denoted by the Greek letter alpha. Of course, since it's a probability, it can only take values between 0 and 1. If alpha is 0, it means that whatever evidence you get, the email is always considered to be ham. In that case, you never get a type 1 error. On the other end, if the significance level is 1, that means every email is considered spam. And in this case, every time you get a ham email, you will be making a type 1 error. Of course, both extremes are terrible decision makers. What you want is something that is able to define if an email is spam or not and has as few type 1 errors as possible. However, as you saw, this error can never be made 0. So a typical value to consider is 0.05 for your significance level. This means that on average, you will decide that a ham email is spam 5% of the time. Another value usually encountered is alpha equals 0.01. As we said, you want alpha to be as small as possible, but however, there's a small catch. If you reduce the probability of a type 1 error too much for a fixed number of examples, then you're increasing the type 2 error. This is what happens when we thought of the alpha equals 0 scenario. To give the proper definition of significance level, it is the maximum probability of committing a type 1 error, which is the same as the maximum probability of rejecting H0 when H0 was actually true. The value of alpha is your design criterion for this test. This means that alpha will determine a threshold to decide if you should reject H0 or not based on your sample.
So now that you know about hypothesis testing, let me show you how to do it for a population mean. We're going to do both cases again, when you know the standard deviation of the population and when you don't. When you don't, a familiar term will come up again, which is the student t-distribution. Furthermore, we're also going to learn a very important concept, which is the concept of the p-value.
In order to get a clear view of hypothesis testing and how the significance plays its role, let's analyze another example. Imagine you are interested in the average height of 18-year-olds in the US, and consider a sample of the height of 10 people measured in inches. If you recall, this is the same data set from week 2 that we used to perform the maximum likelihood estimation for the mean height. For these observed values, the average height is 68.442 inches. Before diving into the hypothesis testing, there's one more thing you should consider, and that is data quality. Since your goal is to make a decision based on data, then the data needs to be reliable. Otherwise, you'll be arriving to false conclusions. But what does reliable mean? Each sample has to be representative of the population. The data needs to be completely randomized. This is to avoid introducing bias into the decision making. For example, if you're interested in the height of 18-year-olds in the US and you take all your samples from the basketball teams of each school, you would be introducing bias in the sample because in general, basketball players are taller. Also, you should consider the amount of data you have available. Is the sample size enough to make a good decision? A good rule of thumb is considering 30 samples or more. In the examples that follow, we'll be assuming that the samples we have are good enough for the testing. So historical data says that the mean height of 18-year-olds in the US in the 70s was 66.7 inches. Based on the observed data, can you confirm that the mean height of 18-year-olds in the US has increased? So the sample mean you have is 68.442, which is greater than 66.7. But is this enough to confirm the hypothesis? Let's try to formulate the null and alternative hypothesis. Your baseline here is that nothing has changed, and thus that the population mean for 18-year-olds is still 66.7 inches. And the competing hypothesis is that the population mean is greater than 66.7 inches. Note that the hypotheses are always formulated in terms of the population, in this case, the population mean, and must not involve samples at all. Now, the hypotheses are based on the population parameters, but the decision will be based on the observations that you have. In this example, you will base your decisions on the sample mean, which is the average of the random samples xi. If your decision is made on the sample mean, then the sample mean will be your test statistic. Note that this is a random variable and doesn't yet depend on the particular observations you have. On the other hand, the value 68.442 is called the observed statistic, and it is based on your measurements. In general, a test statistic will be a function of the random samples. That gives information about the population parameter you want to study. For example, if you are testing the mean of the population, a good statistic is the sample mean. Same thing goes for testing probabilities or occurrence rates. If you wanted to test the variance of the population, then a good candidate is the S-squared statistic. It is important to mention that the test statistics are not unique. For example, the sum of square difference between the xi and the sample mean could also be used as a test statistic for variance. You will see an example about this in the following videos. In general, there are 3 types of hypotheses. Let's go back to our example where we want to compare the current population mean with the population mean from the 1970s. There are 3 sets of questions that arise under this scenario, each of which can be identified with a set of hypotheses. The first one was, has the population height increased in the last 50 years? The baseline here is that the mean height remained the same, and what you want to prove is that the population mean actually increases. This means your H0 is that mu is 66.7, and H1 is that mu is bigger than 66.7. This one is called a right-tailed test, because the alternative hypothesis extends to the right of the null hypothesis. Namely, because a number bigger than 66.7 is to the right than 66.7. The second question is whether the population mean decreased during the last 50 years. This leads to the null hypothesis that mu is 66.7 and the alternate hypothesis that mu has to be less than 66.7. This kind of hypothesis is called a left-tailed test, because the alternative hypothesis is to the left of the null hypothesis, namely a number less than 66.7 is to the left than 66.7. And the final question is whether the mean height has changed at all, either became bigger or became smaller. In this case, the h0 is again that mu equals 66.7, and h1 is simply that mu is different than 66.7. And the null hypothesis is the same. And this is a two-tailed test because it says that the mu has changed and has either gone to the right of 66.7 or to the left of 66.7. So notice that for these cases, the null hypothesis or the baseline is always the same, but the alternative hypothesis changing depending on what you want to prove. Now let's consider the first set of hypotheses. This is called a right-tailed hypothesis because the alternative hypothesis to the right of the null one. Here is h0, the null hypothesis, and here is the alternative hypothesis. Now, since you're trying to make a conclusion about the mean of the population, it's natural to consider your sample mean as a way to get close to the population mean. There is another way you might see right-tailed tests where h0 states that mu is less than or equal to 66.7. Both tests are equivalent, so for simplicity, let's keep the original formulation. If your sample mean is much greater than 66.7, which is h0, then reject h0 and accept h1. What are the two errors we can have here? Well, type 1 error will be determining that mu is greater than 66.7 when the true value was actually 66.7. A type 2 error will happen when you determine that the population mean stayed the same, but the true value was bigger. Now let's look at the second set of hypotheses. Here h0 is still that the population mean is 66.7, and your alternative hypothesis is that the value actually decreased over the years. This is a left-tail hypothesis because the alternate hypothesis lies to the left of the null hypothesis. And again, you might see this test written as follows. h0 says that mu is greater than or equal to 66.7, and in this case, if your sample mean is much less than 66.7, then you would reject h0. In this case, a type 1 error happens when there was no change in the population mean, but you accepted the hypothesis that mu is less than 66.7. While a type 2 error happens when you don't reject h0 while there was actually a decrease in the population mean height. Finally, consider the third set of hypotheses. This is called a two-tailed test because the null hypothesis spreads to both sides of the hypothesis. Mu equals 66.7 is that hypothesis. In this case, you will reject h0 when the sample deviates a lot from 66.7. Since the difference can be in any direction, a simple way to represent this is simply taking the absolute value of the difference between the sample mean and the value in h0, 66.7. In this case, a type 1 error happens when there is no change in the population mean, but you accepted the hypothesis that mu was different from 66.7. While a type 2 error happens when you don't reject h0, while there was actually a variation in the population mean height. So far, the intuition is that if your sample mean falls too far away from the null hypothesis, then you reject h0. But what does too far mean? Remember that h0 is that the population mean is 66.7 inches. So suppose now that the standard deviation for the height is 3, and that there was no change throughout the years. Remember also that you had a sample size of 10. In that case, if h0 is true, then the sample mean has a Gaussian distribution with parameters mu equals 66.7 and variance for 3 squared divided by 10. This is because we have a sample size of 10. Right now, we're assuming that the value of standard deviation sigma is known, and I know that it is not usually the case, but don't worry. Later on, you will learn how to deal with an unknown standard deviation. Now that you have a distribution for the statistic, now you can answer the question, how likely was your sample if h0, the null hypothesis, is true? If your answer is very unlikely, then this is grounds to reject h0. Consider now the right-tailed tests for the mean of a population with the Gaussian distribution. Remember also that the sample mean was of 68.442, which is bigger than 67. But is this difference big enough to be statistically significant? Remember that your goal is to make a decision
with a type 1 error probability of no more than the significance level alpha, which in this case, we're going to pick 0.05. Now, in this case, a type 1 error happens when you determine that the population mean has increased when the true value of mu is still 66.7. It makes sense that if you consider that an observed sample mean of 68.442 is enough to reject H0, then of course you would also reject H0 if you saw a sample mean greater than 68.442. So what does this mean in terms of the type 1 error probability? Well, if you reject H0 every time you observe a sample mean greater than 68.442, then the probability of a type 1 error is simply the probability that the sample mean is greater than 68.442 given that mu is 66.7. The probability you're looking for is the shaded area, which has a value of 0.332. Notice that this value is less than 0.05. So with this proposed rejection criteria, the maximum probability of incurring a type 1 error is below the 0.05 threshold you are willing to tolerate. It then makes sense to reject the null hypothesis. By the way, the probability you just calculated is called the p-value. So what's a p-value? Formally, the p-value is the probability, assuming H0 is true, that the test statistic takes on a value as extreme as or more extreme than the value observed. This means that from the observed value, you move into the direction of H1. In this example, since it was a right-tail test, a value as extreme or more extreme than the observed sample mean meant that you had to consider all the values greater than 68.442. The p-value measures how well your sample is modeled under the null hypothesis. A small p-value says that your sample landed on the tail of the distribution under H0, so they're pretty unlikely to happen if H0 was true. So the p-value is a good metric to create a decision rule for the test. This decision will ultimately depend on the significance value you choose. If the p-value is less than alpha, you will reject H0 and accept H1 as true. If the p-value is bigger than alpha, then you decide the evidence is not strong enough and you don't reject H0. So what do p-values look for each type of test? For a more general case called T, the test statistic, you define T observed as the observed value of the statistics and mu equals mu0, the null hypothesis, where mu is the parameter you're looking to test. For right-tail test, you just saw the p-value is the probability of the test statistic being greater than your sample under the assumption that H0 is true. For two-tailed tests, you want the probability of all points that are a distance from mu0 greater than the observed value in both directions. Finally, for a left-tailed test, the p-value is the probability that the test statistic is smaller than the observed value, always assuming that H0 is true. Now let's see what the p-value is for the two-tailed test. Remember that the observed sample had a 68.442 mean. In this case, the type 1 error occurs when you accept that mu is different from the baseline 66.7 inches. So in this case, the p-value is the probability that the difference in absolute value between the sample mean and 66.7 is greater than 1.742, given that H0 is true. For this case, we have to consider both tails since you're considering the absolute value. This gives a probability of 0.0663, which is twice as much as what you had for the right tail test. In this case, the p-value is greater than 0.05, so you conclude to not reject H0. Finally, consider the left tail test. The original sample with sample mean 68.442 won't do because it is larger than the baseline value. So let's imagine instead that the average mean in your sample was 64.252. In the case of the left tail test, the type 1 error happens when you reject that mu equals 66.7 when it was actually true. So the p-value is the probability that the sample mean is less than the observed value, 64.252. which is the shaded area over here, and it gives a probability of 0.0049. This is clearly smaller than alpha equals 0.05, so you conclude to reject H0 and accept the hypothesis that the population mean has decreased over the last 50 years. Notice that this p-value is not only smaller than 0.05, but it is also smaller than 0.01, which is another commonly used significance level. It tells us that even with the more conservative alpha of 0.01, you would have rejected the hypothesis. So far, all the tests we perform using the statistic h bar, which if H0 is true, has a Gaussian distribution with mean mu0 and sigma 3 squared divided by 10. However, there's an alternative way
to design the test using the z-statistic, which is simply the standardized version of x bar. In this case, if h0 is true, then the z-statistic follows a standard normal distribution. Let's see how this looks using the right tail test. Remember the example from before? You're looking at the right tail test for the population mean. Let's try to see how we can formulate the same problem in terms of the z-statistic. Remember that you had a population standard deviation of 3, a sample size of 10, and an observed sample mean of 68.442, and the p-value was the probability of the sample mean being greater than your observed sample mean under the assumption that mu equals 66.7, which had a value of 0.332. Notice that the hypothesis and the type 1 error interpretation need to remain the same. Also, your sample data doesn't change. Let's see what the z-statistic looks in this case. The observed statistic is then 68.442 minus 66.7 divided by 3 square root of 10, which is 1.837. How do you transform the event x bar bigger than 68.442 so that the probability of type 1 errors is stated in terms of the z-statistic and its observed value? First, subtract the population mean under h0 from both sides, and they scale everything by 3 divided by square root 10. The right hand side is the observed statistic 1.837. Also, since you are now working with the z-statistic, then you need to adjust the PDF so that it's the PDF of the standard normal distribution. Therefore, the 66.7 turns into a 0, and the observed sample mean of 68.442 turns into the observed z-statistic value 1.837. Of course, the result of the p-value has to be the same because you're performing the same test over the same data and you're just standardizing the statistic. So far, you learned to make decisions based on the p-value of the observed statistic. If the p-value is smaller than the significant level alpha, then you reject the null hypothesis and accept the alternative hypothesis as true. One thing you could ask yourself is, what is the least extreme sample you could get so that you would still reject h0? This is the sample that has the p-value of exactly alpha. Anything less extreme than that sample wouldn't satisfy the condition of the p-value less than alpha. This is called a critical value. Notice that it depends on the value that you choose for alpha. Different alphas determine different critical values. The critical value is usually referred to as k alpha to emphasize this dependency. One cool thing about critical values is that any observed statistic which is more extreme than your critical value will always achieve a p-value of alpha or less. So you can create a decision rule based on the critical value. Let's go back once again to the right tail test example about the mean height of 18-year-olds. The hypothesis being h0, that the population mean is 66.7, and h1 is that the population mean is greater than 66.7. For this example, you were working with a sample size of n equals 10 and a population standard deviation of sigma equals 3. Consider that you're interested in an alpha of 0.05. You need to find the value k 0.05, which has a p-value of exactly alpha equals 0.05. But this is nothing more than the value that leaves an area of 0.05 to the right, which means that the critical value is nothing more than the quantile 1 minus 0.05. Now, when the population mean has a value of 66.7, which corresponds to the null hypothesis, the sample mean follows a Gaussian distribution of mean 66.7 and a standard deviation of 3 divided by root 10. For this distribution, the critical value is 68.26. Now that you have the critical value, you can make a decision rule. You can reject h0 if the observed sample mean is greater than 68.26. One cool thing about critical values is that you can define your decision rule before having to collect any data. Once you do have your data, you can calculate the observed statistic and make a decision from that. In our example, the observed sample mean is 68.442, which is greater than the critical value 68.26. In this example, you will reject the null hypothesis when a significance level of 0.05. This is exactly the same conclusion you reach when using the p-value method. Now, what would happen if you change your alpha for 0.01? Well, since 0.01 is smaller than 0.05, then k 0.01 will definitely move you to the right. That means you need more evidence against h0 to reject it, and the critical value would be 68.91. The decision rule will now be to reject the null hypothesis if the observed sample mean is greater than 68.91. With your data, this means that you cannot reject the null hypothesis with a significance level of 0.01. Now let's see what critical values look like for each type of test. For right-tail tests, K alpha is the value that under the null hypothesis lives an area of alpha to its right. That means that the critical value is the quantile 1 minus alpha of the statistic distribution when H0 is true. A decision rule becomes reject H0 if the observed statistic t is greater than the critical value. For left-tail tests, the critical value will be the one that leaves an area of alpha to the left, so that it corresponds to the quantile alpha. In this case, the decision rule is to reject the null hypothesis if the observed statistic is smaller than the critical value. And finally, we get the two-tailed test. In this case, the probability of error needs to be divided between the two tails of the distribution, which means you will need to find two critical values, K alpha 1, which leaves an area alpha 2 to its right, and K alpha 2, which leaves an area of alpha 2 to its left. They correspond to the 1 minus alpha over 2 and the alpha over 2 quantiles respectively. You will now reject H0 if the observed statistic is greater than K alpha 1 or smaller than K alpha 2. So to sum up critical values, you can define the critical value in advance since you don't need the sample to get it. You only need to know the design conditions, like the sample size and any information you might need about the distribution of the population you're studying. It is very important that the p-value method and the critical value method must always lead you to the same conclusion. As we mentioned, with critical values, you can define the decision criteria beforehand and then make the decision once you have your data. This makes it possible to determine the type 2 error probabilities. Since you have a clear decision rule that does not depend on the observations, you can find the probability of making a type 2 error very easily. You will learn more about it in the following video. So remember at the beginning of the lesson, we defined type 1 and type 2 errors. So far, we've been focusing on type 1 errors through the significance level. Consider again that you want to test where the population mean for the height of 18-year-olds in the US has increased since the 70s when it was 66.7 inches. A type 1 error happened when we rejected the null hypothesis that the population mean was still 66.7 when it was actually true. Now you're concerned about the other type of error, which happens when you fail to reject the null hypothesis when it wasn't true. Note that type 1 errors can only happen for one value of the population mean, in this case 66.7. However, type 2 errors can happen for any population mean value which is bigger than 66.7. For this example, remember you were working with a sample size of 10 and a standard deviation of 3. In the previous video, you found that for a significance level of 0.05, the critical value was 68.26, so that the decision rule was to reject the null hypothesis if the observed sample mean is greater than 68.26. You can ask yourself, what is the probability of incurring in an error if the true value of the population mean was 70? That's the probability of a type 2 error. What you're looking for is the probability of not rejecting H0 given that the true population mean is 70. With the proposed decision rule, this is the probability that the sample mean is smaller than 68.26 when the population mean is 70. So remember that if H0 is true, then the sample mean had a Gaussian distribution with mean 66.7 and standard deviation of 3 divided by square root 10. However, if the true value of the sample mean is 70, then that is no longer true. In this case, the sample mean will follow a Gaussian distribution, but this time with mean 70 and the same standard deviation, and the probability of not rejecting H0 is this blue area over here, for values smaller than the critical value of 68.26, which has a value of 0.333. This probability of type 2 errors is usually called beta. A very interesting thing is that the probability does not depend on the observed sample, only on the significance level that you chose for the test. Note here that you considered mu equals 70, but you can get the type 2 error probability for any value on mu in the alternative hypothesis, so you can define beta for as many values as you want. Now, you should have a better understanding about type 1 and type 2 errors, but many times you want to characterize the chances of actually making a good decision. In particular, It is important to focus on this quadrant of the table, where you are making the right call by rejecting the null hypothesis. This information is gathered in the power of the test, which is a function that tells you for each possible value of the population mean in the alternative hypothesis, the probability of rejecting H0. Remember that the type 2 error probability is the probability of not rejecting H0 when H0 is not true. This was called beta. Now we have introduced the concept of the power of the test, which is the probability of making the right decision and rejecting the null hypothesis when it's not true. These probabilities complement each other. So the power of the test can be written as 1 minus beta. To sum up, for each value of mu in H1, the power of the test is 1 minus the probability of making a type 2 error. This is what a typical power of the test looks like for a right-sided test. At the very left of the plot, you have mu equals 66.7, and the height of the graph is exactly alpha, since it's the probability of rejecting H0 for that particular value of mu. For this plot, alpha equals 0.05 was considered. All other values of mu in the graph correspond to the alternative hypothesis that the population mean is greater than 66.7. Consider mu equals 68. Then the height is the power of the test at mu equals 68, and is exactly the probability of rejecting the null hypothesis if the true value of the population mean was 68. The height between the graph and the value is the complement, and that corresponds the probability of a type 2 error if mu is actually 68 inches. Same thing happens if you consider that the true value of mu is 70. The height of the graph is the power of the test, while the difference between 1 and the curve is the probability of the type 2 error. This graph has an interesting pattern. As the horizontal axis values increase, the curve also increases, getting closer and closer to 1. This makes sense because remember that the value of mu determines the mean of the distribution of the sample mean. So as mu increases, the probability that the sample mean is smaller than the critical value decreases. Let's see how the power of the test looks for 3 different alpha values. On the left, you have the power of the test for alpha equals 0.01. Next for 0.05, which is the one from the previous slide. And finally, you have the power of the test for a significance level of 0.1. From left to right, you have an increasing alpha, which is the type 1 error. Now consider the value of the function for mu equals 70. It turns out that as the value of alpha increases, so does the power of the test for mu equals 70. This is true for every value in the curve. Now in contrast, let's take a look at the type 2 error. This time the behavior is exactly the opposite. If you get too restrictive with the type 1 error, you end up increasing your type 2 error probability. For a fixed sample size, there is always a trade-off between type 1 and type 2 errors. However, if you can have any sample size you need, you can always achieve alpha and beta as small as you want. Let's sum up the steps involved in hypothesis testing. First step is to state your hypothesis. This involves defining the null hypothesis, which is your baseline. For the current example, this is H0, that the population mean of the height of the population is 66.7. You also need to define the alternative hypothesis, which usually corresponds to the statement you wish to prove. In the heights example you've been working on, this could be H1, that mu, the mean of the heights of the population, is bigger than 66.7. The next step is designing the test. This means deciding on the statistic you're going to work with. This could be the sample mean, and defining the significance level of the test. The most common value is alpha equals 0.05. Remember, the significance level is the maximum probability of making a type 1 error and should always be small. Step 3 is computing the observed statistic based on your samples. For all the previous examples, you work with an observed statistic of 68.442. And finally, the last step is the decision making. This is when you make your decision based on your data. One common way of making decisions is based on the p-value. If the p-value is smaller than the significance level you define in step 2, then you can reject the null hypothesis and accept the alternative one. However, reaching a conclusion is not as simple as it seems, and people often make mistakes. Let's take the time to refresh some definitions and facts about the errors in the test. A type 1 error happens when you reject H0 when H0 was actually true, while a type 2 error is when you fail to reject the null hypothesis H0 when the alternative one was true. Your design parameter is the significance level alpha, and by definition it corresponds to the maximum probability of making a type 1 error you want this value to be as small as possible. However, be mindful that for a fixed sample size, the type 1 and type 2 error probabilities are entangled. So be mindful when choosing alpha because you might be forcing a type 2 error probability that is too high. Now that you have the concepts fresh in your mind, let's look at the correct interpretation of the results, as well as some common misconceptions. Let's begin with p-values. P-values are a criterion for making a decision based on the data. If the p-value is smaller than the significance level, then we reject H0 and accept H1. What does the p-value represent? Is it true that p-values represent the probability of H0 being true? Well, this is not the case. While it is true that a small p-value rejects the null hypothesis, it does not represent the probability that the hypothesis is true. The p-value represents the probability of seeing the observed data by chance. Basically, a small p-value tells you that the null hypothesis is not a good model for your data because the chances of observing it are small. Now, let's move to test conclusions. If you reject the null hypothesis, you accept the alternative hypothesis as true. But is it true that not rejecting H0 means that the null hypothesis is true? This is also false. Remember the spam email example. You don't really say that the email is ham. The most you can guarantee is that there was not enough evidence to show that the email was spam. The same principle applies for any hypothesis test you consider. Remember that you learned about the t-distribution in the previous lesson in the context of confidence intervals? Now let's review how t-distribution plays a role in hypothesis testing. Consider the example of sampling the height of 10 18-year-olds. As mentioned in the previous week, people's heights can be modeled as a Gaussian distribution with parameters mu and sigma squared. As a consequence, the sample mean will follow a Gaussian distribution of the same mean but a smaller standard deviation, because now we have 10 samples, so the standard deviation is sigma divided by square root of 10. This is true if you know the parameters of the distribution, but what happens when you don't know the values of mu and sigma? Well, if mu and sigma are known, then you already learned that the sample mean minus mu divided by the sample standard deviation follows standard normal distribution. This is simple standardization. This statistic is called the z-statistic. But what if sigma is unknown, which is a more common case? Then knowing that the sample mean is a Gaussian with standard deviation sigma over square root of 10 is not very useful because you don't know what the value of sigma is. What you do in this case is to replace the value sigma in the standardization formula by its estimate s. Remember that s was defined as almost the variance of the sample, except you divide it by n minus 1 instead of n. So it was the square root of the sum of square difference between each sample and the sample mean divided by n minus 1. The resulting statistic is called the t-statistic. Now, does it follow a standard normal distribution? The answer is sadly no. It turns out that the t-statistics follows something that we've already learned previously, the student t-distribution, or simply the t-distribution. So let me remind you what this looks like. Notice that it's bell-shaped, similar to the Gaussian. However, if you compare the t-distribution PDF to that of the normal distribution, you can see that it has heavier tails. The distribution of probabilities accounts for the uncertainty introduced when replacing the population standard deviation with its estimation. Now, what are the parameters of the t-distribution? It only has one, and it's called the degrees of freedom. It's usually denoted with the Greek letter nu. The degrees of freedom control how heavy the tails of the distribution will be. This notation means that x follows a t-distribution with nu degrees of freedom. And let's see what the distribution looks like as the degrees of freedom increase. Notice that as nu increases and gets closer and closer to 30, the Gaussian PDF and the t-PDF looks almost exactly alike. And that's a reason why we like to have 30 samples, because then the t-distribution and the Gaussian are very similar. Now let's go back to the example from the beginning of the video. In here you have n equals 10 samples. Now you know that the t-statistic x bar minus mu divided by s over square root 10 follows a t-distribution with nu degrees of freedom. But what should the value of nu be? The degree of freedom nu is simply 10 minus 1. That's the number of sample minus 1, which gives us 9 degrees of freedom. In general, if you have a sample size n, then the degrees of freedom is n minus 1. Notice that the degree of freedom is independent of the population mean and variance, and only depends upon the number of samples you collected. The relationship between the sample size and degrees of freedom implies that as n increases, the distribution of the t-statistics looks more and more Gaussian. In conclusion, the t-statistic is used when the population has a Gaussian distribution with unknown sigma. Consider again your sample consisting of the heights of 10 18-year-olds with the mean 68.442 and the three sets of hypotheses that we talked about in the previous videos. In the example from the previous videos, you knew that you had 10 samples and that the population's standard deviation was 3. What this meant is that if H0 is true, then the sample mean distributes normally with a mean of 66.7 and a standard deviation of 3 over square root 10. The difference now is that you don't know sigma, which in turn affects the distribution of the data. It's no longer this normal one over here. So what can you do now? Well, if you remember from the previous lesson, we introduced the t-statistic, which was used in cases just like this one. The small drawback is that all the computations will have to be made in terms of the t-statistic rather than the sample mean directly. So instead of plotting the distributions around 66.7, you will need to draw them around 0. Under H0, this t-statistic follows a t-distribution with 9 degrees of freedom. And this is corresponding PDF. The goal now is to repeat the 3 tests using the t-statistic instead. Let's begin by considering the right tail test for the mean of the Gaussian distribution with unknown sigma. The data now is n equals 10, sample mean of 68.442, and we need to add the sample variance, which when we calculate it is 3.113. The observed t-statistic is then 1.77. To get the p-value for this test, you want the probability that the t-statistic is greater than 1.77 given that H0 is true. This is the shaded area, which has a probability of 0.0552. Since this value is greater than 0.05, you should not reject H0. This is the exact opposite result you got from the right tail test when sigma was known. This has to do with the uncertainty added from not knowing the population's variance. Suddenly, the evidence you had was not enough to reject H0. Now let's repeat the process for the two-tail test. The p-value is now the probability that the t-statistic is in absolute value greater than your observed data. In this case, the observed statistic is positive, so it's correct. In the general case, you would need to add an absolute value in case the observed statistic is negative. You now need to include the left tail because now you're looking at absolute values. This gives the probability of 0.1103. Notice that once again, this is double the p-value you had for the right tail test. This p-value is greater than 0.05, so the conclusion is again to not reject H0. And finally, consider the left tail test. So let's consider again that the sample you had achieved has an average of 64.252. Also imagine that the sample standard deviation remained the same. In the case of the left tail test, the p-value is the probability that the t-statistic is less than the observed value, negative 2.487, given that H0 is true. And that is this shaded area over here, which gives a probability of 0.0173. For this sample, you obtain a p-value smaller than 0.05, so the correct conclusion is that you should reject H0 and accept the hypothesis that the population mean has reduced.
So far, all the hypothesis testing we've done has been with one sample in one population. But what happens if we want to take different samples in different populations? For example, let's say I have 2 countries and I believe that the people in this country are taller than those in this country, but I can only take samples. 2-sample hypothesis testing is going to tell us how to compare samples on different populations.
In the following videos, you're going to learn about comparing 2 populations. Consider, for the example, that you're interested in comparing the heights of 18-year-olds in the US with the heights of 18-year-olds in Argentina. For the first group, you have 10 samples x1 up to x10, which with the values shown above have an observed sample mean of 68.442 inches and a sample standard deviation of 3.113. For the Argentinian group, you have only 9 samples, y1 up to y9, with an observed mean of 65.949 inches and a simple standard deviation of 3.106 inches. Your goal is to determine if the population mean from the US is different than the population mean from Argentina. So just as with sample tests, you can define three types of hypotheses. In all three cases, you will consider the null hypothesis that both population means are the same. First, you can consider the alternative hypothesis that the population mean of 18-year-olds in the US is bigger than that in Argentina. You could also consider the alternative hypothesis that the population mean in the US is smaller than that in Argentina. And finally, there's an alternative hypothesis that both population means are simply different. Writing this hypothesis in terms of the difference mu US minus mu Argentina, you get a right tail test, a left tail test, and a two-tailed test. Now let's use the following assumptions. The first one is that all people in the sample from the two groups are different. That means that there is no one measured that belongs to both groups. The second one is that each height measurement from each person is independent from the other ones. The third one is that the populations for the height in both countries are normally distributed. This means that all measurements x coming from the US have a Gaussian distribution with mean mu US and a standard deviation sigma US, and the same goes for the samples coming from Argentina, which have a mean mu Argentina and standard deviation sigma Argentina. You can then define the sample means for each group. X bar will be the sample mean for the US population and Y bar the one for Argentina. And now the same question is, how does the difference between both sample means distribute? Since it's a linear combination of Gaussian variables, then it will also be a Gaussian, but with which parameters? The mean will be the difference of the population means, and the standard deviation will be the square root of the variances of each sample mean. If you don't quite remember the result, you can go back to week 2 lesson 1 where this result was explained. Of course, you can standardize the difference between x bar and y bar to get a statistic that has a standard normal distribution. However, since we don't know the population standard deviation from any of the two groups, then the best we can do is to replace sigma US and sigma Argentina with the sample standard deviation from each group, so that you have the statistic given by x bar minus y bar minus mu US minus mu Argentina divided by the square root of sx squared over 10 plus sy squared over 9. This statistic also has a t-distribution because it corresponds to a statistic for the mean of a Gaussian population with an unknown sigma. Unfortunately, the formula for finding the degrees of freedom is very cumbersome, but don't worry about it. A bunch of software packages will do this for you. Replacing nx, ny, sx, and xy by the observed values, you actually get that degree of freedom of 16.8. Now, after all that math, let's briefly refresh the problem statement. You have two groups of samples. In this case, one corresponds to 10 samples of heights of 18-year-olds in the US and the other one to 9 samples of height of 18-year-olds from Argentina. From the US sample, you observed a mean of 68.442 inches and a sample standard deviation of 3.113, while the Argentinian sample has an observed mean of 65.949 inches and a sample standard deviation of 3.106. Let's begin with a right tail test with null hypothesis mu US minus mu Argentina equals 0 and alternative hypothesis that mu US minus mu Argentina is positive. This means that the population mean from the US is greater than the one from Argentina. Also, let's consider a significance value of 0.05. From last slide, you know that if H0 is true, then the statistic t equals x bar minus y bar divided by the square root of sx squared divided by 10 plus sy squared divided by 10, where these are the sample variances, has a t-distribution with 16.8 degrees of freedom. Replacing the observed values in the statistic, you get that the observed statistic is 1.7459. But what's the p-value for this sample? Well, because it's a right tail test, the p-value is the probability under the null hypothesis that the statistic t is greater than the observed statistic. This corresponds to this area under the PDF and has a value of 0.0495. Since the p-value is smaller than the significance level of 0.05, then the decision is to reject the null hypothesis and to accept that the population mean in the US is bigger than the one in Argentina. Now let's see what you can say about the two-tailed tests. All sample values are the same, as is the significance level and the test statistic. What changes now is how you calculate the p-value. In this case, you want the probability under H0 that the statistic is in absolute value greater than the observed statistic, which is the sum of these two areas and has a value of 0.0991. In this case, since the p-value is greater than the significance level, you don't have enough evidence to reject the null hypothesis that the population means are the same. In the previous video, you learned about two sample t-tests where you wanted to compare two populations, where the two groups being compared were independent. There's another situation where you also have two groups, but they are not independent. So imagine, let's say that you want to test the effectiveness of a training plan to lose weight. The first group will be the people before the training program. After 4 weeks, you weight each participant again, so these two correspond to another person, and so on. And in this case, you say that the samples are paired. Now, what you're interested here is in the difference between pairs to determine if the training program was good for weight loss. You can do that by studying the mean difference between each member of the group. So you will have the weight before minus the weight after the program for the first person, for the second one, all the way to the 10th. Since you're interested in the average behavior, you will sum all this difference and divide them by the number of samples in each group, which is 10. It is common to define a new variable d to represent the difference between x and y. So you get x1 minus y1 is d1, x2 minus y2 is d2, and so on and so forth, all the way to x10 minus y10 is d10. And this is the number we're going to study. The sample mean of these variables is going to be called d bar. Now, if x and y were to come from a Gaussian population, then d is Gaussian as well. Standardizing d bar, you get a statistic that has a standard Gaussian distribution. However, again, the population standard deviation is unknown. So just as you've been doing in the previous test, the best thing to do is to replace the population standard deviation by the sample standard deviation. And this is again the t-statistic you discovered a few videos back. It has a t-distribution with 10 minus 1, which is 9 degrees of freedom. That's going to be our test statistic. Whether you want to consider a right, left, or two-tailed tests, your null hypothesis will always be that there is no weight difference between the groups. So replacing mu d by 0. This will be your test statistic. So let's figure out what the observed statistic looks like. You have these 10 weight measurements from the before group and then these 10 measurements after the training program. So if you get the xi observations and subtract the yi observations one by one, then you get these differences over here. Those are the difference in weights from before and after for each one of the 10 participants. Now with these values for the observations from the difference, you have an observed sample mean of 1.09, that's the average of all the Ds, and a sample standard deviation of 1.485. And that gives you an observed statistic of 2.321. Now for the first set of hypotheses, consider the right tail test with null hypothesis mu of d equals 0 and alternative hypothesis mu of d is positive. This means that on average, the training program is good for losing weight. Also consider a significance value of 0.05. Now from this last slide, you know that if H0 is true, then the statistic t equals d bar divided by the standard deviation of the sample mean has a t-distribution with 10 minus 1 equals 9 degrees of freedom. But what is the p-value for the sample? Well, because this is a right tail test and the p-value is the probability under the null hypothesis that the statistic t is greater than the observed statistic 2.321, which corresponds to this area under the PDF, and that has a value of 0.0227. Since the p-value is smaller than the significance level of 0.05, then the decision is to reject the null hypothesis and accept that the population mean for the difference in weight is positive. That means that the training program is good for losing weight. If you paid close attention, you might have noticed that once you start working with the variables di, which are the difference of weights before and after the training program, the statistic reduces to the case of a single sample of size n. This means all the results you learn for one sample t-test are valid here.
Now I'm going to tell you about A/B testing, which is a really cool application of two-sample hypothesis testing. Let's say that as a data scientist, you are studying a website, and this website has a particular conversion rate. Now let's say you improve the website and you want to see if the conversion rate went up or down. For this, you can use A/B testing. Let me show you how. Suppose your company has a web page and it wants to test two different placings for the Buy Now button. Let's call each of these strategies A and B, and your goal is to determine if switching to strategy B leads to higher purchase amounts. To do this, you select a group of people. As customers come in, they are randomly assigned to design A or design B. The common rule of A/B testing is to send a smaller proportion of customers to the new design because you don't know how good it will be. So in this case, you selected 80 customers for strategy A and 20 for strategy B. When you look into the purchases of each group, you see that strategy A has an average purchase of $50 with a sample standard deviation of $10, while the group exposed to strategy B has an average purchase of $55 with a sample standard deviation of $15. Now that you've designed your experiment and gathered the data, you can go ahead and use the tests you've already learned to make a decision. Your null hypothesis would be that the mean purchase with option A and the mean for option B are the same, while the alternative hypothesis is that the mean purchase for strategy B is larger than the one for strategy A. This hypothesis can also be written in terms of the difference of means. You also need to set a value for alpha, which in this case is going to be 0.05. Now, suppose for the sake of the example that the purchase amounts follow a Gaussian distribution. In that case, or if the number of samples is large enough, then you can make your decision using a two-sample t-test. Notice that if H0 is true, then according to the t-test, the statistic follows a t-distribution. Following the formulas you learned from the independent two-sample t-tests, the degree of freedom is 23.38. Replacing the observed values in the statistic, you get that the observed statistic is negative 1.414. What is the p-value for the sample? Well, in this case, you have a left tail hypothesis, so it's the probability that the standard normal is smaller than negative 1.414. And that has a value of 0.085. So with this value, you won't reject H0 because the p-value is greater than alpha equals 0.05. So what's the difference between A/B testing and t-tests? Well, A/B testing is broader than just t-tests. It's a methodology for comparing two variations. While the t-tests are a statistical tool, A/B testing encompasses many more steps. This includes proposing the variation to tests, randomly splitting your sample subjects and presenting each group with a different variation, measuring the outcomes and determining metrics to use. This means, are you interested in mean behavior, in proportions, dispersion, etc.? The very last step in A/B testing is using statistics tools to make a decision based on the data gathered. This is where the t-test comes in. Also, in the previous example, you used the t-test because you were comparing means for Gaussian populations. If that were not the case, you would use another statistical test to make the decision. Now imagine that you want to test a whole new website design for your online purchase platform. You have the old version A and the new version B. You're interested in knowing if B has a higher conversion rate, which is simply the proportion of visitors that actually make a purchase. So once again, you need to split your sample randomly between the two groups. One will be exposed to version A of the website and the other one to version B. Suppose that you consider 80 customers for group A and 20 for group B. And 20 customers from group A make a purchase, while the number of group B was 8. So the hypothesis will be quite similar as the previous example. For the null hypothesis, you have that both conversion rates are the same. While for the alternative hypothesis, you have that the conversion rate in strategy B is bigger than in strategy A. If this is the case, then you would like to deploy the new web page. Again, let's consider an alpha of 0.05. You're interested in conversion rates, so you're recording the number of customers that make purchases from each group. These variables actually follow binomial distributions of parameters NA and PA for group A and NB and PB for group B. Now, what is the statistic to use in this case? Let's look into it. Remember that x and y can be seen as a sum of NA and NB Bernoulli variables each, and the mean of a Bernoulli variable is simply the probability of success B. This means that by the law of large numbers, you know that x over NA is similar to PA as the number of samples gets bigger, and the same happens for y over NB. As you learned the previous week, by the central limit theorem, these quotients have a normal distribution. So x over NA has a mean PA and a standard deviation PA times 1 minus PA over NA, and y and b will have parameters mu equals PB and sigma squared equals PB times 1 minus PB divided by NB. And that's because this is the standard deviation for the binomial distribution. These are good approximations for PA and PB. So x over NA minus x over NB will make a good approximation for PA minus PB. Since x over NA and y over NB are approximately Gaussian, then the subtraction of these two should be Gaussian as well. In this case, mu will be the difference PA minus PB, and sigma squared will be the sum of variances of each. And if you're wondering how we get there, take a look at the reading item. One very common way to express this is by standardizing the distribution. Now, if H0 is true, then PA equals PB, which you can directly call P. So you can replace PA and PB by P in these statistics. Now, let's see if we can rewrite the expression into something nicer. First, notice that you have a common term, P times 1 minus P, in both terms. And also, 1 over NA plus 1 over NB can be written as NA plus NB divided by NA times NB. You can now replace it in the statistic, which still has a standard Gaussian distribution because you perform some algebraic manipulations. The problem is that while PA and PB are the same, you still don't know the value of P, so you will need to replace it by an estimation. Since x and y come from the same conversion rate P, the best you can do to estimate P is aggregate all the observations so that x plus y is now divided by NA plus MB. What you're doing here is considering that you have NA plus MB samples from a Bernoulli of parameter P. So the sample proportion now has to consider all these samples. Now replacing P times 1 minus P by P hat times 1 minus P hat, you get the test statistic. After all this math, let's go back to the problem we're solving. You had two web page designs A and B. For the design A group, you have 80 observations with 20 conversions, and for the design B group, you had 20 observations with 8 conversions. Remember also that x and y follow binomial distributions, each with their own sets of parameters. You are interested in determining if the conversion rate for the new design is better, so this gives you the left tail test. You also consider a significance level of alpha equals 0.05. And as you just saw from the previous slides, if H0 is true, then the test statistics follows a Gaussian distribution with the data you have. This means that the observed statistic is negative 1.336. What is the p-value for the sample? Well, it will be the area under this Gaussian PDF, which has a value of 0.091. Since this is bigger than its significance level, you can reject the null hypothesis and accept that as true, that the conversion rate of design B is bigger than the one for design A.
All right, to close out this week, you have a few final activities. First, you'll have the final exploratory data analysis and graded lab. This week, you will be back in the right shared data applying the concepts you've learned around confidence intervals and hypothesis testing. Next, you'll have this week's graded summative quiz, which covers all topics in this week. Finally, you have your final graded programming assignment, which is an application of the A/B testing concepts you just learned about. Good luck with the final activities of the week, and in fact, of this entire specialization. And I'll see you when you're done to bring this week to a close.